a subtle irony in a world so small that violence echoes across its entirety, leaving no corner untouched yet transforming fury into form. These features, mapped by orbiting eyes like messenger, reveal a history of volcanism long quelled, smooth plains of basalt poured from fissures in the planet's youth, now etched with ghost craters half erased by later flows, a layered archive where each stratum speaks of cooling epochs and quiet consolidations. In this geological hush, lobate scarps snake for hundreds of kilometers, thrust faults where contraction wrinkled the surface like cooling wax, their shadows pooling in the low sun as elegant invitations to trace the planet's slow contraction, a gentle yielding to gravity's persistent nudge. As we follow these wrinkles together, let the lines remind you of the faint creases in your palm, maps of a life unfolding with patient grace. Mercury's magnetic field, a relic dynamo from its fluid core frozen in time, wraps the world in a dipole 1% the strength of Earth's, yet sufficient to sculpt the solar wind into a teardrop bow shock, a protective comet tail of plasma that trails sunward, deflecting charged particles in a serene standoff against the stellar gale. This field, tilted just slightly from the rotational axis, generates mini auroras in the exosphere, sodium atoms excited to green luminescence, faint veils that flicker like distant fireflies against the black, a subtle reminder that even in bareness, there lingers a spark of defiance. And the planet's density, highest among terrestrial kin at 5.4 grams per cubic centimeter, hints at a mantle of silicates veined with sulfides, an iron-rich enigma that puzzles astronomers, perhaps the remnant of a stripped outer layer vaporized in the system's violent dawn, leaving behind a core that comprises 60% of its radius, a heavy secret pulsing faintly beneath the regolith's calm. Much like the weight of a well-loved stone in your pocket, smoothed by years of carry, Mercury's core anchors its swift world in enduring poise. As Mercury's swift silhouette fades into the solar haze, our gaze lifts ever so slightly to its neighbor, Venus, the veiled sister that mirrors Earth's form yet cloaks herself in mysteries of heat and haze, orbiting at 108 million kilometers from the Sun in a 225-day circuit, a graceful arc that renders it the third brightest object in our night sky after the Moon and the evening star itself. This world, 1,204 kilometers smaller than home yet nearly identical in mass at 0.815 Earths, spins with a lethargic elegance, its retrograde rotation completing one turn every 243 days, a euro longer than its year, a backward pirouette that sees the sun rise in the west and set in the east, a cosmic contrarian that upends our expectations with serene indifference. From afar, Venus gleams in reflected splendor, its albedo of 0.75 scattering sunlight like a pearl in twilight, a beacon that has guided sailors and dreamers alike, its phases waxing and waning through inferior conjunctions that bring it perilously close, just 42 million kilometers at times, a neighbor's nod across the void. Envision it as the soft glow of a lantern on a foggy path, drawing you forward with its steady, unspoken promise. And beneath that luminous shroud lies an atmosphere 92 times denser than ours, a blanket of carbon dioxide laced with sulfuric acid clouds that swirl in yellowed bands, trapping heat in a runaway greenhouse that elevates surface temperatures to 464 degrees Celsius, hot enough to soften lead into malleable dreams. Yet this furnace breathes with super-rotating winds at 360 kilometers per hour, encircling the globe in 4 Earth days, a zonal jet that races against the sluggish surface spin, carrying heat from day to night in equatorial haste. These clouds, layered from 48 to 70 kilometers high, filter the sun's rays to a diffused amber glow, casting eternal twilight where rain of acid droplets evaporates before touching ground, a precipitation that never falls, suspended in vaporous grace like tears held in abeyance. Feel the subtle empowerment in Venus's resilience, how this pressure cooker euro equivalent to standing under 900 atmospheres a euro has reshaped its crust into tesserae, fractured highlands buckled like rumpled silk, regions where ancient tectonics folded the plains into high-relief terrains, a planetary massage born of internal fires long subdued. Just as a well-worn blanket folds around you on a restless night, offering comfort in its familiar creases, so does Venus's fractured skin hold the memory of its fiery youth. Venus's surface, mapped by radar through the veil, reveals over 1,600 volcanoes, more than any other world, their shields broad and gentle like Hawaii's, with Matmons rising 8 kilometers to cradle a caldera 200 kilometers wide, a slumbering sentinel that may stir with fresh lava flows detected in infrared whispers, suggesting a geology still alive in quiet pulses. These edifices, clustered in volcanic rises like Beta Regio, speak of a youth without plate tectonics, where hot spots bubble upward in stationary plumes, building domes and pancake flows that spread like molten butter across the lowlands, now cooled into radar-bright tesserae interspersed with smooth plains, a mosaic where impact craters a euro scarce at under 1,000 a euro are bowl-shaped relics averaging 20 kilometers wide, their rays subdued by resurfacing events that wiped the slate clean 500 million years ago, leaving a canvas mostly pristine, as if the planet paused to contemplate its own renewal. In this vast renewal, let us pause too, tracing the smooth expanses like the calm surface of a pond after a stone's skip, ripples long faded into stillness. In Venus's ionosphere, lightning crackles in the upper clouds, not from water storms but from sulfuric updrafts that charge particles into electric symphonies, flashes captured by distant probes as radio bursts that hum through the haze, a subterranean thunder that underscores the world's hidden vitality without ever breaking the surface calm. This electricity, generated in convective cells that span thousands of kilometers, mirrors Earth's own but amplified in the dense brew, where whistler waves propagate like echoes in a cavern, carrying signals that whisper of plasma interactions far above the crushing depths. And the planet's core, inferred from seismic hints in orbiting data, likely remains partially molten, driving a weak magnetic field remnant that interacts with solar wind to birth induced currents, a dynamo-less shield that drapes Venus in a comet-like tail, iron stripped and reformed in endless cycles, a serene negotiation with the stellar breeze. Think of these currents as the faint hum of a distant river, flowing unseen yet shaping the valley it carves. Consider the Maxwell Montes, Venus's highest peak at 11 kilometers, a rugged massif radar scarred like continental crust uplifted in some primordial convulsion, its slopes etched with parallel grooves that channel ancient winds, now fossilized in the still air, a terrain of contrasts where it borders the vast Lakshmi Planum, a plateau ringed by chasms that drop 2 kilometers into lava-flooded basins, evoking the quiet drama of a world sculpted by plume-fed volcanism rather than drifting plates. These highlands, comprising 8% of the surface, harbor the oldest rocks, perhaps 4 billion years old, relics of a wetter epoch when oceans may have lapped at basaltic shores, evaporated now into the atmospheric soup, a lost hydrology that lingers in deuterium ratios hinting at ancient rains, a subtle irony in a planet now bone dry yet once kissed by water's gentle touch. In this veiled archive, Coronia Eurocircular features 200 to 600 kilometers wider Euro. The plains like floral wreaths, updomed by mantle upwellings that spread outward in moats and ridges, then collapse into concentric folds, each one a life cycle etched in stone, from birth to quiet repose. As we admire these wreaths together, let them evoke the simple circle of a wedding band, a symbol of enduring cycles in our own lives. Venus's slow spin, retrograde and desynchronized, arises from eons of atmospheric torques and impacts that flipped its axis, a historical tumble that now aligns its day with solar tides, minimizing the Coriolis twist on winds that would otherwise spiral into cyclones, instead fostering a stable zonal flow that equalizes heat across hemispheres, a self-regulating grace that tempers its infernal core. This rotation, measured at 1 rotation per 243 days, means a solar day lasts 117 Earth days, with perpetual daylight zones where the sun hangs low, casting elongated shadows over tesserae that fracture like cracked porcelain under thermal stress, their quartz-rich compositions sparkling in infrared as if dusted with frost. And in the planet's lower atmosphere, where pressure crushes probes in hours, noble gases like argon and neon drift in trace abundances, atmospheric holdovers from accretion that reveal Venus's noble lineage, a chemical serenity amid the corrosive churn, where carbon cycles eternally between rock and air in a carbonate-silicate balance long tipped toward vapor, sustaining the greenhouse in perpetual equilibrium. In this eternal cycle, where rock yields to vapor and back again, let the thought linger like a held breath, a reminder of how even in transformation, there is a profound, unchanging harmony. As we trace the subtle undulations of Venus's radar-mapped Dunisa Euro-transverse ridges of wind-sculpted basalts in the lowlands, elongated east-west in the prevailing flow, each one a meter high, stretching for kilometers like frozen waves on a tranquil sea. These aeolian whispers speak of surface winds that, though gentle at 1 kilometer per hour, persist in shaping the regolith over geologic timescales, a patient artistry that contrasts the fury above. These dunes, clustered in regions like Guinevere Planitia, offer glimpses of basaltic diversity, from smooth Pahoehoe flows to rubbly Aa, remnants of effusive eruptions that blanketed half the surface, now patterned with hematite that tints the plains in subtle reds under the diffused light. Feel the interconnected wonder in how Venus, despite its shroud, mirrors our own volcanic heritage, with impact basins like Meter Euro 270 km wider Euro encircled by peaks 5 km tall, a central uplift that rebounds like a sigh from the crust's compression, its floor flooded by lavas that pooled in quiet repose, preserving a snapshot of bombardment's end. Just as the lava fields of Hawaii cool into fertile soil that nurtures new growth, so does Venus's past invite us to see renewal in the scars of time. The planet's water loss, inferred from isotopic enrichments, suggests a grand evaporation 500 million years past, when solar heating boiled seas into steam that photodissociated into hydrogen fleeing to space, leaving oxygen to bind with rocks in oxidized soils, a transformation that turned a potentially temperate twin into a sterile hothouse, yet one where phosphine traces detected in the clouds hint at possible microbial veils aloft. A controversial whisper that stirs quiet speculation without disrupting the calm. These clouds, composed of sulfuric acid droplets averaging 3 microns across, reflect 75% of incident light, cooling the upper reaches to -45 degrees while trapping infrared below, a radiative blanket that fosters the global average of 464 degrees, where surface rocks glow dull red in the perpetual overcast, a monochromatic serenity broken only by the occasional radar glimpse of fresh flows. In this layered hush, wind speeds peak at the cloud tops, racing at 100 km/h equatorward, a superrotation driven by thermal tides that propel the atmosphere faster than the planet turns, a fluid decoupling that equalizes dayside heat in nocturnal grace. As these winds circle endlessly, let us together imagine the steady turn of a potter's wheel, shaping clay into form with unhurried hands. And as Venus's veiled mysteries fade into the gathering light, our gaze turns homeward, to the blue jewel that cradles us all, a world of balanced breaths and verdant sighs where the sun's touch nurtures rather than scorches, inviting us to reflect on the fragile oasis that blooms between these fiery guardians and the red wanderer beyond. Earth, our shared sanctuary orbiting at 149.6 million kilometers from the Sun in a 365.25-day ellipse, emerges not as an isolated speck but as the solar system's quiet masterpiece, a sphere 12,741 kilometers in girth where plateaus of ocean and land entwine in perpetual conversation, its surface 71% water that gleams like liquid sapphire under the stars' gentle arc. This third rock from the Sun, with a mass 5.97 times 10 to the 24th kilograms, spins on its axis every 23 hours and 56 minutes, a sidereal day that gifts us the illusion of constancy amid flux, while its orbital year aligns seasons in a slow, reassuring cycle, a rhythmic cradle that has sustained life for billions of years in layers of atmosphere, hydrosphere, and biosphere woven into harmonious interdependence. Feel the subtle empowerment in this equilibrium, how Earth's modest density of 5.51 grams per cubic centimeter euro born of a differentiated core, mantle, and crust euro anchors us against the void, its iron-nickel heart generating a dynamo that cloaks the planet in a magnetic embrace, a protective veil that deflects solar wind like a soft shield, preserving the air we breathe and the auroras that paint our polar nights in ethereal veils of green and rose. Just as a familiar quilt wraps around you on a cool evening, offering shelter without effort, so does this field nurture the delicate balance we call home. In Earth's lithospheric dance, 7 major plates drift at fingernail growth speeds Euro 2 to 10 centimeters per year, carving continents and spawning volcanoes in a choreography of subduction and rifting, where the Pacific Ring of Fire encircles like a garland of fire, birthing islands from oceanic trenches that plunge 11 kilometers deep, abyssal realms where pressure forges exotic life in hydrothermal vents, black smokers exhaling minerals like underwater geysers in a symphony of chemosynthesis. These plates, puzzle pieces of granite and basalt, converge at faults like the San Andreas, where stress accumulates in silent build-up before releasing in quakes that ripple through rock like whispers through silk, reshaping landscapes in moments of profound release. Yet over eons, they sculpt mountains like the Himalayas, thrust upward where India nudges Eurasia in inexorable nudge, peaks piercing 38,000 feet into the ionosphere, their snow-caps eternal sentinels catching dawn's first blush. And consider the cryosphere, Earth's frozen fringes where Antarctica's ice sheet, 13 million square kilometers strong, holds 70% of the planet's fresh water locked in crystalline hush, a vast repository that calms sea levels and mirrors the sky in blinding white, its underbelly alive with subglacial lakes like Vostok, sealed for 15 million years, harboring microbes in a timeless soup that hints at life's tenacious cradle beneath the cold. In this icy vault, let the image settle like fresh snow blanketing a winter field, muffling the world in serene stillness, a reminder of how even in the depths, persistence finds a way. Earth's atmosphere, a diaphanous gown of 78% nitrogen and 21% oxygen, extends 50 kilometers before thinning to space, layered from tropospheric turbulence where weather brews in cumulus cathedrals to the mesosphere's noctilucent clouds that shimmer at 80 kilometers, iridescent veils born of meteoric dust and water vapor, silent spectators to shooting stars. This envelope, recycled through photosynthesis that pumps oxygen from oceanic phytoplankton, are tiny architects responsible for half our air, sustains the carbon cycle in a balanced ledger, where volcanoes belch carbon dioxide and forests exhale it back, a global respiration that tempers temperatures between -88 and 58 degrees Celsius, a habitable span where biodiversity flourishes in rainforests that pulse like Earth's lungs, exhaling 70% of its oxygen in verdant whispers. Imagine the thermohaline circulation, that great oceanic conveyor ferrying heat from equator to poles in saline streams, sinking in the North Atlantic to depths of 4 kilometers, a slow-motion river that distributes warmth like a planetary bloodstream, influencing monsoons and droughts in ripples that span seasons, a serene orchestration where salinity and temperature dictate the flow, ensuring no corner grows too parched or fevered. Much like the steady flow of a garden hose watering distant flowerbeds on a summer day, this current connects the globe's far reaches in quiet, unseen care. The Van Allen belts, Twin donuts of trapped radiation encircling Earth from 1,000 to 60,000 kilometers out, capture solar particles in magnetic funnels, inner protons whirling at 90% light speed while outer electrons paint auroral curtains, a protective net that spares the surface from cosmic barrages, much like a forest canopy filtering storms. These belts, discovered in the space age's dawn, vary with solar cycles, swelling during storms to engulf satellites in crackling interference, yet their presence underscores the magnetosphere's quiet vigilance, a bubble that extends sunward 15 Earth radii before draping in a magnetotail that stretches millions of kilometers, ions rebounding in endless loops like thoughts circling in repose. And in Earth's core, a solid iron ball the size of Mars at 6,000 kilometers wide, surrounded by liquid outer layers 2,200 kilometers thick, generates fields through convective swirls that twist like a simmering pot, the geodynamo flipping polarity every 200,000 years on average, a bipolar reversal that leaves compasses adrift yet life unperturbed, a historical archive etched in ocean floor stripes of magnetized basalt, black and white bands recording the planet's magnetic moods. As these stripes unfold across the seafloor, envision them together like the alternating paths of a braided river, each turn a chapter in the story of our world's hidden pulse. Earth's biosphere, a thin veneer no thicker than a soap bubble at 12 kilometers from ocean floor to mountain top, teems with 8 million species in symbiotic webs, where coral reefs are Euro underwater cities built by polyps Euro harbor a quarter of marine life in calcium fortresses that sway with tides, lunar pools that bulge oceans into high and low, a gravitational duet that sculpts coastlines and stirs plankton blooms in nutrient upwellings. These tides, varying from micrometers in closed basins to 16 meters in the Bay of Fundy, whisper of the moon's ancient capture, its orbit widening 4 centimeters yearly and tidal friction's gentle drag, a slow divorce that will one day leave Earth tideless under a shrunken moon, yet for now, they cradle intertidal zones where barnacles cling and anemones wave like undersea flags, ecosystems pulsing in tidal rhythm. Feel the interconnected wonder in the nitrogen cycle, where bacteria in soil and sea convert inert gas to usable forms, legumes nodding in fields as nitrogen fixers, a microbial alchemy that greens the plains and feeds the chain from grass to grazer, a quiet reciprocity that binds flora and fauna in nutrient loops, ensuring abundance flows without end. Just as the compost in your backyard bin turns scraps into rich soil for next spring's planting, so does this cycle renew the green world we tread. As Earth's verdant rhythms breathe in unison with the solar breeze, let us cast our eyes across the void to Mars, the ruddy nomad that follows at 227 million kilometers on average, tracing a 687-day ellipse that renders it our neighbor in opposition every 26 months, a world half Earth's diameter at 6,790 kilometers across, its mass a mere tenth of ours, light enough to leap 3 times higher under the same gravity, a fragile sphere wrapped in carbon dioxide's whisper-thin cloak. This fourth planet, with a density of 3.93 grams per cubic centimeter from a core half its radius, spins every 24 hours and 37 minutes, A day so akin to ours it feels like a mirrored sigh, yet its axial tilt of 25 degrees gifts polar caps that advance and retreat in seasonal veils of dry ice and water frost, white halos that sublimate into summer winds carrying dust in global hazes that veil the ochre plains. Imagine the thin air at 6 millibars a euro, less than 1% Earth's a euro, allowing sunsets in blue because larger dust scatters red light away, a reversed palette where dawn breaks crimson and dusk fades to cerulean, a subtle irony in a world so arid yet painting skies in oceanic hues. In this reversal, let us together picture the way a sunset over a dusty road softens the horizon, turning familiar fields into something strangely beautiful. Mars's surface, a testament to water's ancient kiss, bears the scars of rivers long dry, outflow channels like Valles Marineris, a canyon system 4,000 kilometers long, 7 kilometers deeper, carved by cataclysmic floods from subsurface reservoirs bursting forth like breached dams, now etched into rust-hued plateaus where hematite spheres roll in wind-swept drifts, blueberries born of acidic waters that evaporated in a warmer epoch. These valleys, wider than the Grand Canyon by a factor of 10, snake along the equator in layered walls of basalt and shale, exposing 4 billion years of stratigraphy in colorful bands that whisper of deltaic deltas and alluvial fans frozen in time, remnants of a hydrosphere that pooled in basins like Hellas Planitia, the solar system's deepest at 7 kilometers below datum, a cratered sea floor where ancient waves may have lapped under a thicker sky. And Olympus Mons, the tallest volcano in the system at 26 kilometers, dwarfs Everest thrice over, its shield a gentle slope 18 kilometers wide at base, built from a million-year vigil of basaltic oozes that pooled in the Tharsis Bulge, a volcanic province that warps the crust upward in a plateau 3,000 kilometers across, a gravitational anomaly that tilts the planet's figure like a weighted scale. As these slopes rise steadily, envision the patient climb of a mountain trail at dawn, each step revealing a new vista of quiet vastness. In Mars's polar layered deposits, alternating strata of dust and ice stack kilometers high, seasonal records etched in radar echoes that reveal dust devils tracing ephemeral paths across dunes in the southern highlands, mini tornadoes that sculpt yardangs into fluted spires, wind's patient chisel on softened stone. These vortices, rising to 8 kilometers and spinning at 50 kilometers per hour, clear atmospheric haze in transient clarity, revealing Phobos and Diomedes, Euro-captured asteroids orbiting low at 6,000 kilometers and 23,000, irregular potatoes tumbling end over end every 7 and 30 hours, their craters popped like old walnuts, tidally locked to always show one scarred face to the red world below. Feel the serene discovery in Mars's residual magnetic fields, striped anomalies in the southern crust from a dynamo quelled 4 billion years ago, fossil magnetism that once shielded a wetter clime, now a patchwork quilt of ancient protection amid the unmagnetized north, where solar wind etches the atmosphere away at 100 grams per second, a slow erosion that thins the air over eons, turning rivers to rills and lakes to dust. Much like the way a river carves a canyon over centuries in your local landscape, leaving echoes of its former rush, so does Mars hold the memory of its watery past. The planet's Hellas basin, scarred by an impact larger than Texas, cradles the lowest point at -7 kilometers, where morning frosts of carbon dioxide glitter like diamond dust before sublimating into gales that howl through the basin's rim, channeling energy into dust storms that engulf the globe for months, veils of fine particles lofted to 50 kilometers high, a seasonal tantrum that tempers the poles by redistributing heat in rusty blizzards. These storms, born of baroclinic instabilities where temperature contrasts drive convection, swirl in counterclockwise vortices over the south, their edges frayed like watercolor washes, clearing to reveal albedo features like Syrtis Major, a dark shield volcano that contrasts the lighter Noachian highlands, terrains older than 4 billion years pocked with craters that outnumber the younger plains, a temporal map where impact flux waned like a fading echo. And in the Valles Marineris chasms, chaotic terrains of jumbled blocks suggest groundwater sapping that undermined walls, collapsing into sinkholes that now pool seasonal brines in recurring slope lineae, dark streaks that inch downslope in summer warmth, hints of perchlorate salts deliquescing into transient flows, a whisper of hydration in the desiccated hush. As these streaks trace their slow paths, let us together see them as the faint trails left by rain on a dusty window, brief signs of moisture in an otherwise dry expanse. Mars's thin atmosphere, 95% carbon dioxide with traces of nitrogen and argon, hosts noctilucent clouds at high altitudes, icy wisps that catch twilight in silver threads, while the ionosphere Euro-peaking at 130 km a euro blooms with aurora-like glows from solar protons penetrating the unshielded heights, proton auroras that paint the poles in ultraviolet curtains, silent illuminations captured by orbiters in the planet's rarefied glow. This air, cold at -60 degrees average, supports dust devils that lift a ton of soil daily in the tropics, their shadows racing across the surface like fleeting shades, sculpting bark and dunes into crescent waves that migrate a meter per Earth year, a slow procession across the vastitas borealis, the northern lowlands that may once have been an ocean basin, now a smooth plain of volcanic fill that slopes imperceptibly toward the pole. Consider the seasonal caps, shrinking from polar ice caps a kilometer thick in winter to dusty residues in summer, water vapor feeding transient clouds that rain scant dust, a hydrological ghost where ancient deltas like those in Jezero crater preserve phyllosilicates, clay minerals burst in neutral waters, a chemical serenity that speaks of habitable havens long past. In this ghostly cycle, picture the way frost patterns form on a cold glass, delicate and temporary, yet full of quiet beauty. As Mars's crimson whispers settle like autumn leaves across the inner chorus, let us venture outward to the lords of the middle realm, where gas giants reign in banded splendor, Jupiter's colossal form emerging first as a guardian of abundance, its storms and moons a tapestry of gentle chaos that shields the inner worlds from stray comets, inviting us to immerse in the scale of worlds that dwarf our dreams. This fifth planet from the Sun, residing at 778 million kilometers in a 12-year ellipse, swells to 11 times Earth's diameter and 318 times its mass, a behemoth of hydrogen and helium that comprises 2.5 times the system's planetary total. Its gravity so profound it compresses itself into an oblate spheroid, equator bulging by 7% in a subtle equatorial paunch, a whisper of rotation's inexorable pull. Jupiter, with a density of 1.33 grams per cubic centimeter, a euro lighter than water yet fast enough to sink in a cosmic bat, our euro orbits in quiet dominion, its axial tilt of 3 degrees sparing it the dramatic seasons of its siblings, instead bestowing a stable climb where ammonia clouds stripe the globe in pale tans and creams, zonal bands that flow eastward and westward in alternating rivers of wind racing at 140 km per hour, an atmospheric ballet that segregates colors in chemical gradients, reds from phosphorus compounds drifting poleward like autumn pigments in a stream. Feel the awe in this colossal serenity. How Jupiter's Coria Euro, perhaps 24,000 kilometers wide, a rocky ice seed swaddled in metallic hydrogena europulses with pressures 2 million times Earth's, forging a dynamo that births the solar system's strongest magnetic field, 1 trillion times our own, draping the planet in auroral ovals that flare in ultraviolet symphonies when solar wind kisses its poles. Just as a vast oak shelters a meadow from the gale, so does this field extend its quiet protection across the void. In Jupiter's upper reaches, the tropopause marks a boundary where temperatures hover at -163 degrees Celsius, a frigid shelf above which stratospheric hazes of hydrocarbons glow in infrared, while below, the troposphere churns with updrafts that birth thunderheads towering to 50 kilometers, anvil tops that cast shadows across the banded expanse like fleeting eclipses on a living canvas. These clouds, layered in ammonia crystals at the crown, ammonium hydrosulfide in mid-strata, and water ice at depths where pressures squeeze droplets into hailstones the size of softballs, swirl in polygons at the Palessa Euro 8-sided tempests in the north, 5 in the south, are Euro vortices that spin for years in hexagonal grace, a subtle irony in a world of fluid fury where order emerges from the eddies like frost patterns on a window. And the Great Red Spot, that iconic cyclone larger than Earth itself, has raged for at least 380 years, a high-pressure anticyclone anchored at 30 km per second winds, its brick-hued oval a cauldron where ammonia upwells to react with sunlight, birthing the ruddy hue that gazes back at us like an ancient eye, unblinking in the Jovian storm, a persistent beacon that shrinks imperceptibly over decades, yet endures as a testament to atmospheric longevity. In this enduring gaze, let the spot linger in your mind like the steady eye of a summer storm viewed from a porch swing, powerful yet distant, inviting contemplation rather than haste. Jupiter's magnetosphere, a colossal bubble extending 7 million kilometers sunward and trailing 100 times farther in a magnetotail that lashes like a comet's lash, traps sulfur ions from Io's volcanoes in radiation belts fiercer than Saturn's, electrons whipping at 99.9% light speed, a hazardous halo that probes must skirt in polar plunges, yet this field sculpts auroras brighter than Earth's by a factor of 1,000, rings of light that pulse in sync with Io's orbital dance, plasma tori blooming where the moon's outcast sodium feeds the inner belt like a stellar nursery. These auroras, spanning thousands of kilometers, shimmer in hydrogen's purple and oxygen's green, a polar ballet illuminated by particle bombardment that heats the ionosphere to 4,000 degrees, while the planet's internal heat radiating 1.67 times the solar input from contraction, and helium rain fuels convection that drives the banded jets, equatorial zones expanding and contracting in plumes that ripple the clouds like wind over wheat. Imagine the metallic hydrogen layer, 10,000 kilometers thick under pressures of 3 million atmospheres, where molecules ionize into a conductive fluid, currents swirling to amplify the dynamo, a subterranean ocean that conducts electricity like a vast generator, birthing whistler waves that sing through the radio spectrum in decametric bursts, ethereal choruses captured by earthly antennas as Jupiter hums its inner song. Much like the hum of a distant highway on a quiet night, these waves carry a sense of vast, unhurried motion. The Galilean moons are Io, Europa, Ganymede, Callisto, a Euro circle in resonant lock, a quartet tugging in 4-3-2-1 harmony that stabilizes their orbits against tidal decay, Io innermost at 421,000 kilometers, a volcanic hellscape where 100 times Earth's output erupts in silicate lavas that resurface the globe every million years, sulfur plumes arcing 200 kilometers high before freezing into yellow rafts on the night side, a world so tidally kneaded it flexes like dough under Jupiter's grasp, birthing quakes that propagate as seismic waves through a mantle of rock softened by constant heat. Europa, next at 671,000 kilometers, gleams with an icy crust 10 to 30 kilometers thick over a subsurface ocean deeper than all Earth's seas combined, a salty expanse warmed by tidal friction that flexes the shell in diurnal cracks, red-brown streaks of oxidants from Jupiter's radiation painting the chaos terrains where plates of ice founder into the depths, potential habitats where hydrothermal vents may bubble nutrients in a hidden sea, a serene cradle beneath the frozen lid. And Ganymede, largest moon in the system at 5,260 kilometers across, harbors its own dynamo in a layered ocean sandwiched between ice and rock, a magnetic field that interacts with Jupiter's to birth auroral footprints on the gas giant's poles, while Callisto, outermost at 1,880,000 kilometers, bears a battered crust pocked with craters older than the hills, its faint ring of dust a whisper of impacts that spared Io's fire and Europa's flux, a quiet elder scarred yet enduring in low albedo gray. As these moons tug in their harmonious dance, envision the way siblings play in a backyard, each pool shaping the game without overwhelming the joy. In Jupiter's ring system, gossamer strands of micron dust encircle equatorially, fed by impacts on the moons that grind ejecta into a tenuous belt spanning tens of thousands of kilometers, the main ring dense with silicates from Amalthea and Thebe, a delicate necklace illuminated by forward scattered sunlight that makes it visible only in backlit glances, a subtle veil that Jupiter's gravity shepherds without fanfare. These rings, discovered in Voyager's gaze, vary in optical depth from 0.0001 to 1, ethereal compared to Saturn's, yet they trap charged particles in a plasma sheet that aligns with the magnetic equator, a dynamic layer where ions gyrate in cyclotron frequencies, birthing synchrotron radiation that bathes the system in radio glow. Feel the reassuring scale in how Jupiter's Oblatanessa Euro flattened by a day of 9 hours 55 minutes a Euro creates a gravitational quadrupole that perturbs asteroid belts inward, flinging comets sunward or scattering them to the Oort cloud, a cosmic broom that has swept the inner system clear over 4 billion years, sparing Earth from frequent bombardments in a protective sweep of abundance. Just as a lighthouse beam sweeps the shore to guide ships safely home, so does Jupiter's pull quietly clear the paths for inner travelers. Jupiter's tropospheric ammonia abundance, peaking at 0.26 by mass, seeds clouds that reflect 40% of sunlight, cooling the upper reaches while deeper water layers a Euro reaching pressures of 100 atmospheres a Euro form thunderous storms where lightning flashes 1,000 times brighter than terrestrial bolts, illuminating ammonia cirrus in electric azures that charge the atmosphere to potentials of 10 megavolts. These discharges, captured in Juno's flybys, reveal ammonia plumes rising from below, wet convection that carries heat from the interior in towering cumulonimbi, each storm a localized forge where phosphates react to tint the spot's ruddy heart, a chemical serenity amid the gale. And the planet's helium rain, theorized in the metallic depths, depletes the upper atmosphere by 5% over billions of years, droplets coalescing under gravity to drizzle inward like a stellar shower, a slow redistribution that tempers the heat flux, ensuring the giant's glow remains a steady ember rather than a flare. In this slow drizzle, let the image rest like rain pattering on a tin roof after a long day, a rhythmic easing into peace. Consider the Shoemaker-Levy 9 comet's plunge in 1994, fragments arcing into the southern hemisphere to birth fireballs larger than Earth, scars that lingered months in darkened bands, a rare visitation that scarred the clouds with soot and water, temporarily quenching the spot's edge in a cosmic bruise that healed without trace, underscoring Jupiter's resilience as a gravitational sink for solar system debris. This event, observed from afar, revealed impact energies equivalent to 6 million megatons. Yet the planet absorbed them in atmospheric hush. Fragments vaporized at 60 kilometers depth in shock waves that rippled outward like pebbles in a pond. In this healing hush, where scars fade like morning fog lifting from a valley, it becomes a gentle reminder of the giant's role as sentinel, quietly mending the wounds of the wandering. In the Jovian interior, the 1 bar level at 150 kilometers below clouds marks the reference where pressures align with Earth's sea level, a boundary where helium abundance drops to 0.135, tracing the gradual compression that turns gas to fluid in seamless gradient, a layered serenity from molecular haze to degenerate electron sea. Jupiter's polar cyclones, dozens strong in hexagonal arrays, spin in alternating directions like a vortex garden, their edges sharp as if ruled by invisible compasses, temperatures plunging to -165 degrees in the calm centers where subsidence warms the depths, a polar engine driven by barotropic instabilities that segregate vorticity in the jet streams. These polygons, spanning 5,000 kilometers, host embedded thunderstorms that pump ammonia upward in plumes detected by radio occultations, a convective ballet that maintains the banded contrast, reds deepening where upwelling brings phosphates from below. And the planet's radio emissions, from decimeter waves to kilometer lengths, burst in longitudes aligned with Io's passage, electron beams from the Moon's wake accelerating in the flux tube that maps to Jupiter's surface, a longitudinal beacon that pulses every 42 hours, the System 3 rotation period that clocks the interior's spin independent of the surface winds. As these bursts echo faintly, think of them together like the soft crackle of a radio on a road trip, tuning into distant stations that connect you to the wider world. As Jupiter's banded guardians fade into the outer twilight, our thoughts turn to its ringed kin, Saturn with its iconic halo of ice and rock, a world of even greater delicacy where rings whisper of ancient collisions and moons dance in gravitational pas de deux, beckoning us deeper into the solar symphony with promises of ethereal grace and hidden depths. This sixth planet from the Sun, poised at 1,427,000,000 kilometers in a 29.46-year ellipse, spans 9 times Earth's diameter and 95 times its mass, a hydrogen-helium giant less dense than water at 0.687 grams per cubic centimeter, buoyant enough to float in a mythic bath, its obliqueness pronounced by a 10% equatorial bulge from a 10-hour 39-minute day that spins the clouds in easterly gales up to 1,800 kilometers per hour at the equator, zonal bands of buttery yellows and golds segregated by ammonia cirrus and haze, a stratified serenity where seasonal hexagons cap the poles in six-sided calm, vortices born of baroclinic waves that organize the flow into geometric repose. Saturn, with an axial tilt of 26.7 degrees Euro, the most inclined among the gas giants, Euro bestows solstices that last half its year, northern summers where the pole basks in unending light for 15 years, warming the stratosphere to 0 degrees, while winters plunge to -200, a rhythmic tilt that paints ring shadows across the globe in latticed filigree, evoking the faint poetry of light and absence in balanced measure. Feel the uplifting hush in this golden world, its internal heat Euro twice the solar input from gravitational settling and helium drizzly Euro driving convection that ripples the clouds in wave trains, subtle undulations visible from afar like silk disturbed by a breath, a planet whose core of rock and ice, perhaps 20,000 kilometers wide under metallic hydrogen seas, pulses with the dynamo yielding a magnetic field half Jupiter's, tilted and asymmetrical, birthing auroras that ripple in hydrogen's glow across the poles. Just as a soft blanket settles over a sleeping child, easing the chill of night, so does Saturn's field drape its realms in a comforting, unseen warmth. In Saturn's rings, a vast disk spanning 282,000 kilometers yet mere 10 meters thick in places, billions of icy particles orbit in Keplerian grace, shepherded by moonlets like Prometheus and Pandora that tug the edges into braided streams. The A-ring's dense braid where gaps like the Enka at 130,000 kilometers echo resonances that clear lanes like cosmic combs, particles ranging from dust motes to house-sized bergs tumbling in perpetual motion, reflecting sunlight to 80% albedo and casting shadows that dance across the planet like fleeting lace. These rings, lightly born from a shattered moon 4 billion years past, divide into 7 main bands: Euro A through Ga Euro, with the Cassini division, a 4,700-kilometer void between A and B, carved by Mimas's 2-to-1 resonance that destabilizes orbits, hurling ice sunward in a gravitational sieve, a faint irony in a system so ordered yet sculpted by distant pulls. And the B-ring's spokes, radial shadows streaked across the dense core, arise from electromagnetic charges that align dust with the magnetic field, fleeting phenomena that fade with solar wind's nudge, observed in Voyager's glance as ethereal radials spanning hundreds of kilometers, a magnetic artistry that vanishes and reforms like mist in morning light. Imagine the Phoebe ring, outermost at 12 million kilometers, a dark torus of retrograde dust from the moon's debris, inclined and diffuse, a whisper of cometary heritage that feeds the main system in slow infall, particles spiraling inward over 1 million years to replenish the icy splendor. In this slow spiral, let the motion linger like leaves drifting down a lazy river on an autumn afternoon, each turn a step in the endless renewal. Saturn's atmosphere, layered from the 1 bar level where clouds veil the tropopause at -140 degrees, hosts seasonal storms that brew in the equatorial jet. Hexagons eye a calm within the 6-sided gale where winds drop to 50 kilometers per hour, a high-pressure sanctuary ringed by turbulence that feeds from below in ammonia water convection. Lightning flashes captured in radio howls that echo through the system. These tempests, white ovals marching equatorward like pearl beads on a string, merge in cataclysmic clashes that engulf the globe, yet Saturn's calm demeanor a euro radiating heat from a core perhaps still accreting a euro tempers the fury. Helium rain in the depths depleting the envelope by 1% per billion years, droplets falling through hydrogen like a slow cosmic drizzle that sustains the glow. And Enceladus, innermost moon at 238,000 kilometers, jets water plumes from south polar fissures a euro tiger stripes cracking the ice shell 4 kilometers thick, a euro ejecting 500 kilograms per second into a torus that seeds the E-ring, salty vapors analyzed by Cassini as ocean-sourced, a subsurface sea 30 kilometers deep warmed by tidal flexing, where silicon nanoparticles hint at hydrothermal realms, bubbling minerals in a hidden warmth, a serene possibility of life's quiet cradle beneath the frost. Feel the interconnected insight in Titan's dunes, longitudinal ridges 200 meters high stretching 3,000 kilometers, migrated by easterly winds at 0.3 meters per second, basaltic organics piled like frozen sandcastles, a world where cryovolcanoes may ooze ammonia slurries from warm interiors, their calderae pocked with radar dark flows that whisper of geologic youth amid the ancient chill. Much like the way sand dunes shift in a desert breeze, revealing hidden patterns beneath, Titan's ridges invite us to uncover the subtle movements shaping its timeless landscape. Titan, Saturn's clouded prince at 1,220,000 kilometers, swaddles itself in a nitrogen-methane haze 1.5 times denser than Earth's, its orange veil extending 600 kilometers from a surface of hydrocarbon dunes rippling like wind-sculpted waves across equatorial sands of tholins, organic polymers birthed in stratospheric chemistry that rain as oily droplets into lakes of liquid methane and ethane, the largest at Kraken Mare spanning 1,000 kilometers, a hydrocarbon sea where waves lap ethane shores under a hazy twilight, tides sloshing 5 meters from the Moon's eccentric orbit. This world, larger than Mercury at 5,150 kilometers across, spins retrograde every 16 days, its subsurface ocean of water ammonia perhaps 100 kilometers deep, buoyed by a rocky core that flexes under Saturn's tide, birthing quakes that crack the ice crust into polygonal plains, a dual hydrology where methane cycles seasonally like Earth's water, evaporating from polar lakes in summer to form convective clouds that deluge dunes in a billion-year rhythm. As we trace these cycles together, let them evoke the familiar ebb of tides on a childhood beach, each wave a reminder of rhythms that connect distant shores. Rhea, at 527,000 kilometers, bears faint rings of its own Euro-diffused bands of sodium and dust detected in stellar occultations, the first moon with a ring system, a tenuous halo fed by micrometeorite ejections that orbit in stable resonances, a subtle echo of Saturn's grandeur scaled to lunar whispers. And Iapetus, at 3,560,000 kilometers, splits its leaden face into a Euro-dark trailing hemisphere of phyllosilicates accreted from Phoebe's dust stream, bright leading side of water ice scarred by equatorial ridges 10 kilometers high, a walnut-like equator that girdles the globe like a frozen seam, perhaps born from ring collapse or internal upwelling, a dichotomy that spins every 79 days in synchronous lock, always showing the same fractured visage to its parent. These Cassini division moonlets, like Pan embedded in the Encke gap, orbit within the rings to confine edges, their gravity herding particles into sharp boundaries, a gravitational pas de deux where the Moon's orbit clears a lane 2 kilometers wide, particles on resonant paths perturbed into the Moon's wake like sheep to a shepherd. In this herding grace, picture the way a gentle stream gathers pebbles into smooth beds, each stone finding its place in the flow. Saturn's seasonal rings cast shadows that migrate with the tilt, solstice alignments draping the planet in radial spokes of darkness 100 kilometers long, a light show where the main rings eclipse the globe in a 7,000-kilometer arc, brightness dipping as geometry aligns, a periodic veiling that cools the stratosphere by 10 degrees in the shrouded hemisphere. This interplay, captured in Cassini's grand finale, reveals ring temperatures from -150 in sunlit reaches to -200 in shade, ice crystals sublimating edges into feathery plumes that feed the diffuse E-ring, a particle cascade where micrometeoroids vaporize on impact, injecting oxygen that charges the plasma, birthing electrostatic levitation that keeps the rings dynamic yet enduring. And the planet's radio emissions, Saturn kilometric radiation, burst from auroral cavities where electrons stream along field lines, modulated by moon passages that seed plasma waves, a decametric chorus that hums in longitudes tied to the rotation period of 10 hours 39 minutes, a system 3 clock that ticks the interior serene pulse independent of the windy exterior. As these emissions hum faintly, let us together hear them like the soft static of an old radio tuned to the stars, a distant conversation inviting quiet wonder. As Saturn's luminous arcs dissolve into the deepening void, our reverie extends to the ice giants, Uranus and Neptune, tilted enigmas cloaked in blue mantles of methane, worlds of remote serenity where faint rings and shepherd moons guard secrets of cryogenic grace, drawing us toward the system's frosted frontier with the allure of hushed revolutions and hidden winds. Uranus, seventh wanderer at 2,857,000,000 kilometers, traces an 84-year ellipse with a mass 14.5 times Earth's, its diameter 4 times our own in a sphere of 1.27 grams per cubic centimeter, lighter than Saturn yet compressed by a 17-hour day that flattens it oblate, equatorial radius 10% greater than polar, a spin so rapid it stirs the hydrogen-helium envelope into zonal winds of 500 kilometers per hour, yet subdued compared to Kin, a calm where methane absorbs red light to tint the globe aquamarine. Seasonal poles basking in 21-year days under a 97.8-degree tilt that rolls the planet on its side like a tip-top. This obliquity, perhaps from a colossal impact in youth, aligns rings and moons with the orbital plane, solstices veiling hemispheres in endless night where ethane ices form polar caps, a rhythmic inversion that warms equators to -223 degrees, while poles chill to -224, a thermal whisper across the globe. Just as a top wobbles gently on a wooden floor, finding balance in its spin, so does Uranus reveal a hidden steadiness in its sideways grace. Uranus's rings, 11 narrow bands discovered in occultations, encircle at 85,000 kilometers in dusty silence, epsilon the widest at 20 to 100 kilometers broad, composed of dark organics and ice darkened by micrometeoroid irradiation, a faint halo orbiting in the planet's equatorial plane, inclined 0 degrees to the ecliptic by the tilt's magic, shepherded by Cordelia and Ophelia that confine edges in gravitational tugs, particles ranging centimeters to meters in a tenuous weave that reflects just 20% light. These arcs, clumped in the epsilon ring by resonances, span from zeta to nu in a system born perhaps from moon collisions, their mid-plane haze detected in infrared as a diffuse disk extending to Miranda's orbit, a faint irony in a ring system so ordered yet invisible from afar, revealed only when stars wink through the gaps. And the magnetosphere, tilted 59 degrees from the spin axis and offset from center, wobbles with rotation to birth irregular auroras, hydrogen emissions in far ultraviolet that flicker over poles misaligned with the magnetic equator, a dynamo from the icy mantle's convection where water, ammonia, methane ices conduct under pressures of 100,000 atmospheres, forging a field 8 times Earth's in a lopsided bubble that trails sunward in a compressed bow shock. In this wobbling light, Let the flickers settle like fireflies in a jar, their glow a soft, unpredictable rhythm. Miranda, innermost moon at 129,000 kilometers, fractures in chevron terrains where cliffs 20 kilometers high drop sheer, perhaps reassembled from a shattering impact that hurled crust into orbit, now a patchwork of bright cratered plains and grooved coronas like Arden, a cryovolcanic dome rising 5 kilometers in concentric ridges, evidence of past upheavals where ammonia diapers buoyed through the ice shell 10 kilometers thick over a rocky core. This moon, 15 hours in spin, shows spectral hints of carbon dioxide frost in craters, a volatile serenity trapped in the cold, while Ariel at 190,000 kilometers bears canyons deeper than the ground by a factor of 3, filled with bright material that ponds in lows like frozen mercury, tectonic scars from expansion that cracked the crust in a global net, a world where impact basins like Kachina Chasma expose mantle layers in stepped walls. Feel the peaceful discovery in Umbriel's dark plains, at 266,000 kilometers, the Moon's leading hemisphere splashed with rayless craters averaging 80 kilometers wide, a low albedo patina from E-type asteroids accreted in the outer disk, its trailing side brighter in water ice that gleams under the faint sun, a dichotomous hush like Iapetus scaled small. Much like the way shadows play across a garden path at dusk, lengthening and shortening with the light, so do these contrasts invite us to see beauty in the moon's divided face. Titania, largest Uranian at 738,000 kilometers, cradles a subsurface ocean inferred from tidal heating, its surface edged with fault scarps 10 kilometers high where Messier Rupes traces a rift from ancient freeze, canyons that widen to valleys floored in dark ejecta from impacts that excavated the crust 20 kilometers deep. This moon, synchronous in 8 days, hosts the largest crater at Gertrude, 335 kilometers wide with central peaks rebounding like frozen fountains, a geological archive where cryovolcanism may have resurfaced half the globe in viscous flows of water methane, now hardened into mottled plains that undulate gently under low gravity. And Oberon, outermost at 583,000 kilometers, pogs its trailing hemisphere with fresh craters whose rays splash bright ejecta across the dark leading side, a bombardier's canvas where Momma Chasma gapes 12 kilometers deep, a graben flanked by scarps that hint at crustal thinning, a moon where the faint ringlets beyond may draw from its dusty ejecta, a quiet contributor to the system's hazy fringe. As these scarps flank the chasm, envision the gentle folds in a well-loved blanket, each crease a story of quiet adaptation over time. Neptune, 8th Sentinel at 4,500,000,000 kilometers, completes its 165-year ellipse with a mass 17 times Earth's, diameter 3.8 times our own in a realm of 1.64 grams per cubic centimeter, its deep blue from methane's absorption laced with hydrogen sulfide that tints stratospheric hazes, winds howling at 2,100 kilometers per hora euro, the fastest in the Sistema Euro in retrograde zonal jets that whip clouds into bright wisps, the great dark spot, a vanished anticyclone where now smaller vortices spin like sapphire eddies, observed in Voyager's fleeting glance as high-pressure eyes amid the ammonia cirrus. Neptune's tilt of 28.3 degrees gifts mild seasons, yet internal heat from an unknown source. A Euro, perhaps core crystallization. A Euro doubles the solar input, fueling convection that drives the banded flow, polar clouds of methane ice condensing in summers chill to -218 degrees, a serene counterpoint to the equatorial glaze where temperatures rise 20 degrees above the mean. Imagine the planet's core, rocky at 14 Earth masses, underwater methane oceans 2,000 kilometers deep, pressures forging diamond rain that falls like crystalline petals through the fluid mantle, a conductive brew that generates a dynamo tilted 47 degrees from spin, its field asymmetric and wandering, birthing auroras that pulse in hydrogen's Lyman alpha glow over poles offset from the magnetic equator. In this wandering pulse, let the auroras drift like northern lights seen from a frozen lakeshore, their colors a soft invitation to dream. Neptune's rings, 5 arcs dubbed courage, liberty, equality, fraternity, and the diffuse scala, span 2 million kilometers in dark matter of organic dust and ice, the atom's ring clumped into knots by Galatea's 3:2 resonance that herds particles into dense braids, a faint system inclined 1.8 degrees, particles centimeters across orbiting at 40,000 kilometers out, their mid-plane haze betraying collisions that replenish the haze with ejecta. These arcs, discovered in occultations, vary in optical depth from 0.001 to 0.1, a tenuous jewelry born from moon disruptions, where the Levaria ring's diffuse width spans 100 kilometers, a gravitational sculpture where embedded moonlets like Naiad orbit inside the system at 48,000 kilometers, the innermost regular moon in a prograde flock that dances in mean motion chains, 5 inner moons locked in resonance to maintain the ring's form. And Triton, retrograde giant at 354,000 kilometers captured from the Kuiper belt, spews nitrogen geysers from south polar vents, plumes arcing 8 kilometers high before freezing into red organics on the leading hemisphere, a world where the ice shell 20 kilometers thick over a rocky core flexes in tidal lock, quakes propagating as Cantaloupe Turina Euro polygonal blocks uplifted in convection cells a Euro, while a subsurface ocean of water ammonia may lurk beneath, warmed by radioactive decay and orbital eccentricity. Just as geysers burst from Yellowstone's Earth in rhythmic surprise, so do Triton's vents remind us of hidden energies waiting in the cold. Triton's nitrogen cycle, sublimating from southern caps in summer to form clouds that rain back as frost, drives winds up to 370 kilometers per hour, shaping dunes of dark thelins across the mottled plains, a seasonal hush where the moon's 560-hour day aligns with Neptune's, always showing the scarred face scarred by impacts that birthed basins like Tuonela Fossi, chasms 5 kilometers deep flanked by scarps of upheaval. This moon, larger than Mercury at 2,700 kilometers, trails a plasma tail from ionized nitrogen stripped by the magnetosphere, a comet-like wake that feeds Neptune's Taurus, a subtle reciprocity in Capture's legacy. Proteus, at 117,000 kilometers, pocks its irregular form with Pharos crater 200 kilometers wide, a low albedo wanderer tidally locked in 11 hours, its surface of water, ice and rock tumbling in prograde motion amid Neptune's flock. Feel the quiet insight in Nereid's eccentric orbit, at 5,500,000 kilometers the outermost, swinging from 1.5 to 9 million kilometers in 360 days, a captured irregular moon that dips into the magnetotail to glow in auroral hush, its craters averaging 10 kilometers in a reddish patina of space weathering. As Nereid swings in its wide arc, let us together see it like a pendulum in a grandfather clock, marking time with a steady, unhurried sway. Neptune's troposphere, where pressures double every 16 kilometers, hosts stratocumulus of methane ice at the tropopause, bright wisps scudding over the deeper ammonia layers invisible in blue, while the thermosphere balloons to 5,000 kilometers with temperatures climbing to 1,100 degrees from unknown heating, a puffed envelope that hosts hydrocarbon polymers raining a soot into the lower haze. This heat, perhaps from gravitational waves or ionic drag, sustains the super-rotating winds that circle the globe in 16 hours, faster than rotation, a zonal flow driven by deep convection where water clouds form at 20 atmospheres, lightning birthing exotic chemistry in a serene storm. And the planet's faint rings, embedded with arc moonlets like Despina at 52,000 kilometers, orbit in the equatorial plane tilted 1.8 degrees, a system where the Levaria ring's width of 50 kilometers harbors clumps that resonate with the moon's pools, particles darkened by irradiation to reflect but 5% light, a dark halo that encircles in quiet procession. In this procession, picture the faint glow of fireflies circling a lantern at dusk, each light a small part of the evening's gentle gathering dot. As Neptune's azure veils recede into the solar hush, our contemplation drifts to the scattered kin beyond, dwarf worlds and icy sentinels of the Kuiper fringe where Pluto and its brethren hold court in perpetual twilight, emblems of the system's resilient periphery that echo the grand design in miniature persistence, guiding us toward the reflective horizon of our celestial odyssey. These outliers, demoted yet dignified in their distant orbits, circle the sun in ellipses that stretch decades long, fragile spheres of frozen volatiles, and rock that whisper of the nebula's outer nurseries, where temperatures plummet to -230 degrees and sunlight dims to a star among thousands, a faint lantern casting long shadows across nitrogen ices that gleam like polished marble under the sparse rays. Pluto, ninth wanderer at 5,980,000,000 kilometers in a 248-year path, shrinks to half the moon's girth at 2,370 kilometers across, its mass a mere 0.002 Earths in a body of 1.85 grams per cubic centimeter, tidally locked to Charon in a binary embrace where the two trace a waltz around a common center, the largest moon-to-planet ratio in the system, a gravitational duet that spins every 6.3 days, revealing the same cratered faces in eternal regard. This dwarf, with a heart-shaped glacier of nitrogen and methania Eurotombor Regioa Euro sprawling 1,000 kilometers wide, thaws in southern summer to vent hydrocarbons that paint the surface in rosy hues, a seasonal blush where Sputnik Planetia's convex basin, formed by a glancing impact, hosts convection cells that churn the ice like slow-boiling porridge, polygons emerging as upwellings buoy fresh frost to the surface, a cryogenic renewal that reshapes the plains over 10,000 years. In this renewal, let the polygons form in your mind like the cracking of ice on a winter pond, each line a delicate fracture revealing the depths below. Pluto's thin atmosphere of nitrogen, methane, and carbon monoxide swirls to 160 kilometers in perihelion warmth, then collapses as frost in aphelion chill, a vaporous breath that escapes into a tail of iron stripped by solar wind, a cometary whisper trailing 30,000 kilometers, while its mountains rise 3 kilometers in water ice peaks jagged as frozen sawteeth, unyielding beneath the tenuous pressure of 1 Pascal, a landscape where cryovolcanoes like Right Mons may have oozed ammonia water slurries in geologic youth, their calderas pocked with collapse pits that hint at subsurface reservoirs warmed by tidal friction from Charon's pull. And Charon, Pluto's steadfast shadow at 1,198 kilometers across, bears canyons 600 kilometers long and 7 kilometers deeper. Vulcan Planetia's rifts are carved by tectonic extension as the moon cooled, its reddish poles splashed with thalins from Pluto's outcast haze, a shared chemistry that binds the pair in atmospheric exchange, methane migrating on solar winds to tint the moon's north in organic patina. Feel the serene persistence in this binary's resonance, 5-3 with Pluto's orbit stabilizing their inclinations, a harmonic lock that prevents chaotic tilts, while Nix and Hydra, irregular spuds orbiting at 49,000 and 65,000 kilometers, tumble in synchronous grace, their surfaces pocked with craters 10 kilometers wide, faint moons captured or born from the same collision that birthed Charon, a family forged in impact's hush. Just as siblings gather around a shared hearth during a family gathering, each bringing their own quiet story, so do these moons orbit in a close-knit, enduring circle. Beyond Pluto lies Eris, the distant queen at 10 billion kilometers in a 557-year ellipse, slightly smaller than Pluto at 2,320 kilometers yet 80% more massive, a world of 1.65 grams per cubic centimeter, where a thin methane atmosphere freezes into crystalline caps, its surface a mosaic of bright plains and dark equatorial bands, perhaps cryovolcanic flows of water ammonia that ooze from a rocky core under an ice mantle 30 kilometers thick. This Kuiper Belt monarch, tidally locked to dysnomia its moon 175 kilometers wider spins every 26 hours, the pair's mass anomaly perturbing Neptune's orbit by 2 degrees over millennia, a gravitational nudge that echoes through the outer reaches like a pebble's ripple in a vast pond. And Haumea, elongated spinner at 6 billion kilometers in a 283-year path, stretches 1,500 by 1,000 kilometers in a triaxial egg, its rapid 3.5-hour rotation fastest in the Systema born of a smash that ejected daughters Hiaka and Namaka, moons orbiting at 50,000 and 40 kilometers in a family of water, ice and rock, the parent dwarf's red spectrum from irradiation organics that darken the equator while poles gleam in fresh frost, a collisional relic where ringlets of icy dust encircle at 2,000 kilometers, a faint halo fed by moon impacts. In this familial spin, let the rapid turn settle like the whirl of a child's top on the floor, wobbling yet holding its shape with joyful determination, much like the way a spinning top in a quiet room draws the eye to its balanced grace. Makemake, at 6,600,000,000 kilometers in a 306-year ellipse, cloaks itself in methane ices that sublime into a transient atmosphere during perihelion, its reddish hue from tholins baked by cosmic rays on a surface of cratered plains and cryovolcanic plateaus, a dwarf of 1.5 grams per cubic centimeter with no detected moons, yet hinted by orbital wobbles, its low density suggesting a porous mantle of frozen organics over a rocky heart. This Easter egg, named for fertility rites, tilts at an unknown angle, its spin period of 22 hours stirring faint winds that sculpt dunes of dark material across the bright fields, a world where impact basins like those on Pluto mirror in scale, yet Makemake's isolation a Euro farthest dwarf in the classical Belter Euro lens it a solitary grace, sunlight 1,000 times dimmer than at Earth casting a perpetual gloaming. Sears, innermost dwarf at 413 million kilometers in the asteroid belt's embrace, swells to 946 kilometers across with a mass 0.012% Earth's, a sphere of 2.16 grams per cubic centimeter, where a rocky core yields to a muddy mantle that birthed Ahuna Mons, a 5-kilometer cryovolcano rising in bright salts, its flanks streaked with flows of briny water that seep from subsurface aquifers warmed by radioactive decay. As Sears's salts gleam faintly, envision the way morning dew sparkles on a garden path after a gentle rain, each drop a small mirror to the rising sun, connecting the dwarf's quiet springs to the simple wonders of our own mornings. Sears's surface, a patchwork of craters averaging 100 kilometers wide with bright faculae like a Cartora Euro exposing sodium carbonate in a 40-kilometer basin a Euro gleams with organics and clays that hint at hydrothermal pasts, impacts excavating mantle material that ponds in lows as reflective brine, while its weak gravity of 300 meters per second squared allows ejecta to linger in faint exosphere of water vapor and hydroxyl, a tenuous veil detected in ultraviolet glow. And in the Kuiper belt, a donut of primordial ices from 40 to 50 astronomical units, spanning the ecliptic in a disk 100 astronomical units wide, swarms with 100,000 objects larger than 100 kilometers, Quawa at 1,100 kilometers dancing with its moon Waywat in a 44-day waltz, Sedna's extreme ellipse arcing 957 years from 46 to 937 astronomical units, a inner Oort interloper with a red mantle of ethane ices. These planetesimals, sculpted by Neptune's migration that scattered the belt like spilled marbles, collide in slow-motion ballets every billion years, birthing dust bands that feed zodiacal light, a faint glow along the ecliptic from micrometeoroids vaporizing in sunlight. In this scattered dance, let us together see the belt as a quiet marketplace of ancient wares, each collision a gentle exchange preserving the nebula's legacy, much like the way old books in a dusty attic hold stories waiting for a curious hand. The scattered disk, flung by Neptune's gravitational shepherding, populates with detached orbits like Eris's kin, where Gong at 1230 kilometers tilts 44 degrees with its moon Xianglu, a resonant pair that echoes the giant's pull, while the Oort cloud, a spherical shell from 2000 to 100,000 astronomical units a euro, envelops the system in a trillion comets, icy nuclei 10 kilometers wide perturbed by passing stars into long-period visitors. Halley's nucleus, a peanut-shaped relic shedding dust in 2006 tails of sodium and iron. This cloud, born from the nebula's outer fringe scattered by gas giants, responds to galactic tides in a slow churn, comets arcing inward every million years to seed water and organics on inner worlds, a cosmic pantry that delivered Earth's oceans in gentle bombardments 4 billion years past. Feel the empowering vastness in this reservoir, how the Oort's density of 1 comet per cubic astronomical unit spans a volume larger than the Sun's to Pluto, a diffuse guardian where Hill's cloud bridges the gap, detached comets on elliptical flights that whisper of the system's birth, each nucleus a frozen time capsule of pre-solar chemistry, amino acids locked in ices that may have sparked life's dawn. Just as a seed bank in a distant valley holds the potential for future blooms, so does the Oort nurture the quiet possibilities of renewal, a distant echo of the gardens we tend under brighter skies. In the Kuiper's classical belt, low-inclination circles host Orcus at 945 kilometers with its moon Vanth, a binary that resonates 3-2 with Neptune, stabilizing the orbit in harmonic hush, while Verona at 660 kilometers spins every 6 hours, its red surface from space weathering that darkens the ices to 5% albedo. These bodies, accreted from pebbles in the disk's chill, collide at 1 centimeter per second, impacts that crater without shatter, building regoliths meters deep over eons, a patient accumulation where spectra reveal crystalline water and complex organics, thalins from cosmic ray bombardment that polymerize methane into reddish tars. And Sedna's perihelion at 76 astronomical units brings it sunward in 11,000 years, its surface warmed briefly to -240 degrees, sublimating volatiles that form a coma too faint for tales, a lone traveler whose orbit hints at an undiscovered planet 9, a super-Earth shepherding the extremes in unseen gravity. In this lone path, picture the way a solitary bird glides on thermals high above a plain, unseen currents guiding its graceful arc, much like the faint drafts that lift a kite on a breezy afternoon. The Oort cloud structure, inner hills at 20,000 astronomical units feeding the short-period flux, outer shell perturbed by Proxima Centauri's close passes every 50,000 years, loosens comets into parabolic flights that grace our skies as Hyakutake's green tail or Lovejoy's solar grays, nuclei shedding layers in comas 10,000 kilometers wide, dust trains that paint meteor showers in August's Perseids or December's Geminids, echoes of asteroid origins in the belt's ancient rubble. These visitations, peaking every 33 years for sun-grazers like Kreutz fragments, remind us of the system's dynamic edge, where gravity's web extends to the heliosphere's current sheet, a wavy boundary where magnetic fields reverse in 12-year flips, Voyager measuring the plasma's hum as it crosses into local fluff, a low-density interstellar cloud that cradles our bubble in diffuse hydrogen. In this grace, where tails streak the night like fleeting wishes, let the comets fade like a dream half-remembered at dawn, their passage a soft bridge between the familiar and the far. Pluto's haze, layered from tholins at 100 kilometers to methane at 300, scatters blue light to tint the dwarf indigo, organic polymers raining as soot that darkens the mid-latitudes, a photochemical serenity where ultraviolet from the young Sunday may have sparked prebiotic soups in ancient ponds, a dwarf's quiet legacy to the inner bloom. Eris's surface, mapped in infrared to reveal crystalline methane over amorphous water, thaws every 257 years at perihelion, venting gases that form a temporary disk 40,000 kilometers wide, a dwarf's exhalation that seeds dysnomia's orbit with fresh ices, the moon's craters averaging 50 kilometers in a patina of irradiation organics. Haumea's daughters, Hi'aka at 160 kilometers and Namaka at 160, orbit in 49 and 30 days, their tilts matching the parents' 28 degrees in a collisional aftermath that spun the family into resonance, moons that capture ring particles in their wakes, perpetuating the dwarf's faint halo. Maki's equatorial dark band, 100 kilometers wide, contrasts the bright poles in a dichotomy born of seasonal deposition, methane condensing at aphelion to frost the caps while equator bakes in tholins, a world where the absent moon leaves its spin untalked, a solitary whirl in the classical hush. In this solitary whirl, let us together hear the faint echo of a music box winding down, its melody lingering in the air long after the last note, much like the way a forgotten tune from childhood surfaces in quiet moments, connecting us to the distant past. The Oort's long-period comets, with eccentricities above 0.99, hail from random quadrants, their orbits randomized by the cloud's isotropy, Hale-Bopp's nucleus 10 kilometers wide shedding a coma that spanned half a degree in 97, its dust train persisting as a zodiacal enhancement for years. Ison's sun grays in 13, fragmenting at perihelion to a headless tail of iron and sodium, a comet's sacrifice that enriched the inner dust, while Lovejoy's 21 loop dipped to 3 solar radii, surviving the corona's million-degree kiss to emerge with a bent tail, a resilient arc from the cloud's depths. And in Sedna's isolation, the dwarf's possible ring at 50,000 kilometers a euro hinted by light curves a euro would encircle in a faint band of Kuiper dust, a solitary adornment for a world whose orbit, perturbed by an unseen ninth, hints at the system's undiscovered harmonies. In Sedna's faint band, picture the delicate circle of soap bubbles floating on a breeze, each one a fragile world unto itself, drifting with unspoken grace, evoking the simple joy of bubbles chased in a sunny yard, where laughter mingles with the pop of bursting dreams. Sears's bright spots, numbering over 130, gleam with sodium carbonates in craters like Cerealia facula, where impacts pierced the crust to expose brines that effloresced in vacuum, salts crystallizing in hexagonal patterns like desert blooms after rain, a dwarf's luminous reply to the sun's distant call. The main belt's density waves, sculpted by Jupiter's resonances at 2.5 and 3.3 units, populate Kirkwood gaps with empty orbits, asteroids clustering in families from collisions like Flora's thousand members, a shattered parent that seeded the belt with S-types of stony silicates. Vesta's Ria Silvia Basin, 500 kilometers wide at the South Pole, cradles a central peak 23 kilometers tall, the remnant of a 20-kilometer impactor that excavated the head meteorites that rain to Earth, a Vestan whisper in our skies. This scar, formed 1 billion years ago, exposes the dwarf's differentiated layers in radial grooves that stretch 200 kilometers from center, ejecta that mantles the south in bright rays now faded to a subtle patina, a wound that reshaped half the surface yet left the core intact, iron nickel heart pulsing faintly under a mantle of olivine and pyroxene. As Vesta's peak rises steadfastly, let it stand in your thoughts like the enduring spire of a lighthouse on a stormy coast, guiding through the dark with unyielding light, a beacon from the belt's ancient forge, much like the steadfast oak in a neighborhood park that weathers every season, its branches a quiet testament to time's patient hand. In this culmination of orbits and ices, the solar system reveals itself as a fragile orrery, its dwarf sentinels the punctuation to the giant's prose, each fact a note in the score of gravitational grace that has played uninterrupted since the nebula's collapse, a symphony where human curiosity are Euro telescopes piercing the Kuiper's veil, probes kissing comets, dust a Euro extends the melody into the unknown, reminding us that in the quiet spaces between worlds, we find not emptiness but the echo of our own becoming, a place within the whole where rest comes not from answers but from the endless, soothing question of what lies just beyond the light. And now, with the final facts softly settled into place, let the worlds grow quiet around you. We've wandered through glowing hearts and ringed halos, crimson deserts and azure storms, mountain peaks and ancient ices. Through it all, a single truth echoes gently beneath the surface. The solar system is extraordinary. Not because it is perfect, but because it persists. It adapts. It endures. And it continues to surprise us. Somewhere, right now, a comet arcs in its sleep. A ring particle tumbles in silent orbit. A dwarf moon counts the footsteps of a passing probe. You are part of this story too. Not separate from the cosmos, but made of it. Dust and dreams, memories and motion. A living thread in the long, unfolding pattern of the stars. So, wherever you are, allow your mind to rest. Let your breath slow. Let your thoughts grow soft at the edges. The journey doesn't end, it simply pauses here until curiosity calls again. Sleep well. Welcome, dear friend, to this gentle journey into the heart of one of nature's most breathtaking phenomena. The Aurora Borealis. The Northern Lights. Those shimmering curtains of color that dance across the polar skies like whispered secrets from the cosmos itself. If you find peace in this exploration, if these soft words and cosmic wonders bring you comfort, please consider subscribing and leaving a gentle like. It helps others discover this tranquil space for rest and wonder. Now, Take a slow, easy breath. Let your shoulders soften, and allow yourself to settle into this moment of calm. Because tonight, we're going to explore the science and beauty of the aurora in a way that invites deep, restorative sleep. Imagine, if you will, standing beneath a vast northern sky, the air crisp and still, darkness wrapping around you like a soft blanket, and then, slowly, almost imperceptibly at first, a faint glow begins to emerge on the horizon. A whisper of green light, barely there, like the first hint of dawn, but softer, gentler, more mysterious. This is the aurora beginning its nightly dance, and understanding how this celestial ballet comes to be is a journey that starts not here on Earth, but 93 million miles away, on the surface of our Sun. The Sun, that brilliant star at the center of our solar system, is not the calm, steady sphere of light it appears to be from our distant vantage point. No, the Sun is a roiling, churning ball of plasma, a cosmic furnace where temperatures soar to millions of degrees, where magnetic fields twist and writhe like living things, where energy is released in ways both subtle and spectacular. The Sun breathes, in a sense. It exhales streams of charged particles into the vast emptiness of space. And this breath, this solar wind, is where our story truly begins. Picture the Sun's surface, the photosphere, glowing with that familiar golden light we see each day. But above this visible surface lies the corona, the Sun's outer atmosphere, a region so hot that it defies easy explanation. Temperatures here reach not thousands but millions of degrees Celsius, a fact that puzzled scientists for decades. How could the atmosphere of the Sun be hotter than its surface? It's like standing near a campfire and finding that the air 10 feet away is hotter than the flames themselves. The answer lies in magnetic fields and wave heating, in processes that channel energy upward and outward, processes that we're only now beginning to fully understand through missions like NASA's Parker Solar Probe, which has ventured closer to the Sun than any spacecraft before it. From this superheated corona, particles escape. Protons, electrons, alpha particles. They stream away from the Sun at speeds ranging from 250 to over 750 kilometers per second. That's fast. Incredibly fast. Fast enough to cross the distance from the Sun to Earth in just a few days during particularly energetic events. This is the solar wind, and it carries with it something invisible but crucial. The interplanetary magnetic field, or IMF, threads of magnetic force that extend from the Sun and weave through the solar system like gossamer strands in a cosmic web. Now, let's pause here for just a moment. Notice your breathing, how it's perhaps already beginning to slow, to deepen. Feel the weight of your body wherever you're resting, and imagine those solar winds as gentle exhalations, soft breaths from the sun reaching across the void. There's something deeply calming about this image, isn't there? The sun breathing, the universe breathing, and you, here, breathing along with it all. Just rest in that thought for a few peaceful moments. These solar winds don't travel through empty space in a uniform stream. No, they're structured, variable, ever-changing. Sometimes the wind is slow, moving at a leisurely 400 kilometers per second, emerging from the sun's equatorial regions during quiet periods. Other times, particularly from coronal holes, those dark regions in the sun's atmosphere where magnetic field lines open into space rather than looping back. The wind rushes out at speeds exceeding 700 kilometers per second. And occasionally, dramatically, the sun releases what's called a coronal mass ejection, or CME, a massive burst of plasma and magnetic field that erupts from the solar surface and hurtles through space like a cosmic tsunami. Recent research from 2024, published in the journal Geophysical Research Letters, documented a particularly fascinating CME event from April 2023. During this event, something extraordinary happened. The solar wind conditions changed so dramatically that Earth's magnetosphere, that protective magnetic bubble surrounding our planet, temporarily lost its usual wind-sock shape. The bow shock that normally stands upstream from Earth, like the wave that forms in front of a boat moving through water, simply disappeared for about 2 hours. Instead, structures called alpha copyright N wings formed, creating a direct connection between Earth's magnetic field and the recently erupted region of the Sun. It was as if Earth grew temporary wings, reaching back toward the Sun, and along these wings, plasma and energy flowed like rivers of light. This discovery, made by Dr. Li Jian and colleagues using NASA's magnetospheric multiscale mission satellites, revealed something profound about the dynamic relationship between our star and our planet. The boundary between the solar wind and Earth's magnetosphere isn't a solid wall. It's more like a membrane, sometimes permeable, sometimes not, always responding to the conditions around it, always in motion, always dancing to the rhythm of solar activity. As these solar winds journey across the 93 million miles of space between Sun and Earth, they carry their energy, their particles, their magnetic fields. And when they arrive at Earth, they encounter something remarkable. Our planet's magnetosphere, that invisible shield generated by the churning of molten iron in Earth's outer core, a magnetic field that extends tens of thousands of kilometers into space, protecting us from the full force of the solar wind. The magnetosphere is shaped like a teardrop, compressed on the side facing the sun and stretched into a long tail on the night side, extending far beyond the moon's orbit. This shape is carved by the solar wind itself, by the constant pressure of those streaming particles pushing against Earth's magnetic field. Where the solar wind first encounters the magnetosphere, a boundary forms called the magnetopause, and it's here, at this boundary, that some of the most important processes for aurora formation begin. One of these processes is called magnetic reconnection, and it's absolutely crucial to understanding how energy from the solar wind enters Earth's magnetic environment. Imagine two magnetic field lines approaching each other. One from the sun, carried by the solar wind, and one from Earth, extending outward from the magnetosphere. When these field lines meet under the right conditions, they can break and reconnect in a new configuration, like cutting two ropes and tying the ends together in a different way. This reconnection releases enormous amounts of energy and creates a direct pathway for solar wind particles to enter the magnetosphere. The conditions have to be just right for this reconnection to occur efficiently. The interplanetary magnetic field carried by the solar wind needs to be oriented southward, opposite to Earth's northward pointing magnetic field in the northern hemisphere. When this happens, when the fields are anti-parallel, reconnection proceeds rapidly, and the magnetosphere opens up, allowing solar wind energy to pour in. It's like opening a door in a storm. Suddenly, energy that was outside is now inside, and it has to go somewhere. Where does it go? Much of it is directed along Earth's magnetic field lines toward the poles. These field lines act like highways, guiding charged particles from the magnetosphere down into the upper atmosphere, into regions above the Arctic and Antarctic circles where the magnetic field lines converge and dive down toward Earth's surface. And it's here, in the upper atmosphere, at altitudes between about 80 and 500 kilometers above the ground, that the magic happens, that the aurora is born. But before we descend into the atmosphere to witness that birth, let's linger for a moment in the space between, in the magnetosphere itself. Because this region is far from empty. It's filled with plasma, with charged particles trapped by Earth's magnetic field, particles that bounce back and forth between the northern and southern hemispheres, spiraling along magnetic field lines in a complex dance governed by the laws of physics. There are different populations of particles here, some relatively cool and dense, others hot and sparse, and they occupy different regions with names like the plasmasphere, the ring current, and the plasma sheet. The plasma sheet is particularly important for auroras. It's a region in the magnetotail, that stretched out portion of the magnetosphere on Earth's night side, where plasma is stored like water behind a dam. During periods of enhanced solar wind activity, this plasma sheet becomes energized, and through processes that scientists are still working to fully understand. Processes with names like substorms and magnetic reconnection in the tail. Energy is suddenly released, and particles are accelerated to high speeds, sent streaming down magnetic field lines toward the polar regions. Take another slow breath here. Feel how your body is perhaps growing heavier, more relaxed. Imagine those magnetic field lines as gentle slides, as soft pathways guiding particles downward. There's no urgency here, no rush. Just a slow, inevitable descent, like falling softly into sleep. Rest with that image. Let it carry you deeper into calm. The particles that create auroras, primarily electrons, though protons play a role too, are traveling at tremendous speeds by the time they reach the upper atmosphere. They've been accelerated by electric fields in the magnetosphere, gaining energy, and now they're plunging downward, following the magnetic field lines, heading toward a collision with the atoms and molecules that make up Earth's atmosphere. Earth's atmosphere is a layered thing, a delicate envelope of gases held close to the planet by gravity. At sea level, where we live and breathe, the atmosphere is dense, composed primarily of nitrogen, about 78%, and oxygen, about 21%, with trace amounts of argon, carbon dioxide, and other gases. But as you ascend, the atmosphere thins. By the time you reach the altitudes where auroras occur, the air is so thin that it would be considered a vacuum by everyday standards. Yet even here, there are enough atoms and molecules to create the spectacular light shows we call the Northern Lights. When a high-speed electron from the magnetosphere collides with an atom or molecule in the upper atmosphere, something fascinating happens at the quantum level. The collision transfers energy to the atmospheric particle, exciting it, bumping one of its electrons to a higher energy state. This is an unstable configuration. The atom or molecule wants to return to its ground state, its lowest energy configuration. And to do so, it must release the excess energy it gained from the collision. And how does it release this energy? As light, as a photon, as a tiny packet of electromagnetic radiation that our eyes can detect as color. The color of that light, the specific wavelength of the photon emitted, depends on several factors. It depends on what kind of atom or molecule was struck. Oxygen produces different colors than nitrogen. It depends on which energy levels were involved in the transition. Different transitions produce different wavelengths. And it depends on the altitude, because the density of the atmosphere affects which transitions are possible and which are suppressed by collisions. Let's start with the most common auroral color, that beautiful, luminous green that dominates so many aurora photographs and that appears so frequently in auroral displays. This green light, with a wavelength of 557.7 nanometers, comes from atomic oxygen. Not molecular oxygen, the O2 that we breathe, but individual oxygen atoms, which are abundant at altitudes between about 100 and 250 kilometers. Here's what happens. An energetic electron strikes an oxygen atom, exciting it to a state called 1s. This is a metastable state, meaning the atom can remain in this excited configuration for a relatively long time before emitting a photon. About 0.7 seconds, which might not sound like much, but in the quantum world, it's an eternity. Most atomic transitions happen in nanoseconds or microseconds. But this particular transition is forbidden by certain quantum mechanical selection rules, which means it proceeds slowly, by magnetic dipole radiation rather than the faster electric dipole radiation. That 0.7-second lifetime is crucial. It means that at lower altitudes, where the atmosphere is denser and collisions between particles are more frequent, an excited oxygen atom is likely to collide with another particle before it has a chance to emit its green photon. The collision steals the energy away, converting it to heat instead of light, and no green glow appears. This is why the green aurora has a fairly sharp lower boundary, typically around 95 to 100 kilometers altitude. Below this, collisions are too frequent, and the green emission is quenched. But at higher altitudes, where the air is thinner and collisions are less frequent, the excited oxygen atoms have time to emit their photons before being disturbed. And so the green light appears, that characteristic auroral green that has captivated observers for millennia. It's the color most easily seen by human eyes, partly because our eyes are particularly sensitive to green wavelengths, and partly because it's simply the most common auroral emission under typical conditions. Now, imagine that green glow spreading across the sky. Soft at first, like a faint mist of light, then growing brighter, more defined. forming into curtains, into arcs, into rays that seem to stretch from the horizon up toward the zenith. And as you watch, as you imagine this display, feel how your eyelids might be growing heavier, how your thoughts might be slowing down, how the boundary between waking and sleeping might be growing softer, more permeable. Just like that boundary between the solar wind and the magnetosphere. Just rest here. Let the green light wash over you. But the aurora isn't always green. Sometimes, particularly during intense displays or at different altitudes, other colors appear, and each tells a story about the conditions in the upper atmosphere and the energy of the incoming particles. Red auroras, for instance, come from oxygen as well, but from a different transition. When an oxygen atom is excited to a state called 1D, it can emit a photon at 630 nanometers, which we perceive as red. This transition has an even longer lifetime than the green emission. About 110 seconds. Yes, nearly 2 minutes. This means that red oxygen emissions can only occur at very high altitudes, typically above 200 kilometers, where the atmosphere is so thin that an atom can wait for almost 2 minutes without colliding with another particle. During major geomagnetic storms, when the aurora is particularly intense and extends to lower latitudes than usual, observers often report seeing red auroras. This is because the high-altitude red emissions can be seen from farther away, and also because during intense storms, the energy deposition extends to higher altitudes. The great auroral displays of May 2024, which were visible as far south as the Mediterranean and across much of the United States, featured prominent red colors. People who had never seen an aurora before looked up to see the sky glowing crimson, and many thought they were witnessing fires on the horizon or some other terrestrial phenomenon, not realizing they were seeing light generated hundreds of kilometers above Earth's surface. The red aurora has a diffuse, soft quality to it, because those long-lived excited oxygen atoms can drift with the wind during their 110-second wait before emitting. This means the structure of the aurora, the fine details of curtains and rays, gets blurred out in the red emissions. It's like taking a long exposure photograph of something moving. The motion creates a soft, smeared appearance. So while green auroras can show sharp, intricate structures, red auroras tend to look more like gentle glows, like watercolor washes across the sky. Nitrogen, the other major component of Earth's atmosphere, also contributes to auroral colors, though in different ways. Molecular nitrogen, N2, can produce blue and purple hues, particularly at the lower edges of auroral displays. When energetic electrons penetrate deep into the atmosphere, below about 100 kilometers, they encounter denser air where nitrogen molecules are abundant. These collisions can ionize the nitrogen, creating N2+ ions, and these ions emit light in the blue and violet parts of the spectrum, around 428 nanometers. The blue and purple colors are often seen as a fringe at the bottom of green auroral curtains, especially during very active displays when the incoming electrons have particularly high energies. High-energy electrons can penetrate deeper into the atmosphere before they're stopped by collisions, and so they reach the altitudes where nitrogen emissions dominate. Photographers who capture these displays often note the beautiful color gradients. Green in the main body of the aurora, fading to blue or purple at the lower edge, sometimes with hints of red at the top. It's a vertical rainbow of sorts, each color band telling us about the altitude and the atmospheric composition at that height. There's something deeply soothing about understanding these colors, isn't there? Knowing that each hue has a reason, a cause, a story written in a language of physics and chemistry. The universe follows rules, patterns, and even something as ethereal and magical seeming as the aurora is governed by principles we can understand, can study, can appreciate. And yet, understanding doesn't diminish the wonder. If anything, it deepens it. To know that the green light dancing across the sky is the result of oxygen atoms excited by electrons that traveled from the sun, guided by magnetic fields, colliding in the thin upper atmosphere. It's a connection, a thread linking the sun to the earth to your eyes, a cosmic chain of cause and effect that spans millions of miles and involves processes at every scale from the quantum to the planetary. Let yourself rest in that connection now. Feel how you're part of this cosmic dance. How the same atoms that glow in the aurora are present in your body. How the same forces that shape the magnetosphere are related to the forces that hold atoms together. Everything connected, everything flowing. And you, here, breathing slowly, sinking deeper into rest, into peace, into the gentle embrace of sleep. The intensity of the aurora, how bright it appears, depends on how many energetic particles are precipitating into the atmosphere. More particles mean more collisions, more excited atoms, more photons emitted, and thus a brighter display. The brightness can vary enormously, from faint glows barely visible to the naked eye to brilliant displays that can cast shadows on the ground and allow you to read a book by auroral light alone. Scientists measure auroral brightness in units called Rayleighs, named after the physicist Lord Rayleigh. A faint aurora might be a few hundred Rayleighs, while a bright display can reach tens of thousands of Rayleighs. For context, the airglow, that faint natural luminescence of the upper atmosphere that's always present, even without auroras, is typically around 250 Rayleighs in green wavelengths. So even a modest aurora is significantly brighter than the background airglow. The structure of the aurora, those curtains, arcs, rays, and spirals, reflects the structure of the magnetic field and the electric currents flowing in the magnetosphere and ionosphere. Auroral curtains tend to align with magnetic field lines, which is why they often appear to hang vertically in the sky, like luminous drapes. The curtains can be thin, just a few kilometers wide, or broad, extending for hundreds of kilometers. They can be smooth and uniform, or they can show intricate folds and waves, rippling and undulating as if blown by an invisible wind. Auroral rays are even more aligned with the magnetic field. These are narrow, beam-like structures that appear to shoot upward from the horizon toward the zenith, or sometimes downward from above. They're created when the precipitating electrons are tightly focused along particular field lines, creating narrow columns of light. When you're standing beneath an active aurora and you see rays converging overhead, you're looking along the magnetic field lines, seeing the three-dimensional structure of the aurora projected onto the dome of the sky. The motion of the aurora is mesmerizing. Auroras can appear static for minutes at a time, then suddenly burst into rapid motion, with curtains waving, rays flickering, colors shifting. This motion reflects changes in the magnetosphere, changes in the electric fields that accelerate the particles, changes in the magnetic field configuration. During substorms, those periodic releases of energy from the magnetotail, the aurora can become incredibly dynamic, with waves of light sweeping across the sky, brightening and fading, breaking apart and reforming. Time-lapse videos of auroras reveal patterns that are hard to see in real time. You can see waves propagating along auroral arcs, moving at speeds of several kilometers per second. You can see the aurora expanding equatorward during the growth phase of a substorm, then suddenly brightening and breaking up during the expansion phase. You can see the recovery as the aurora gradually fades and returns to a quieter state. It's like watching the breathing of the magnetosphere, the inhale and exhale of energy, the rhythm of the Sun-Earth connection. Researchers have found that auroral displays follow patterns related to the solar wind conditions. When the interplanetary magnetic field turns southward, favoring magnetic reconnection, the aurora tends to intensify and move to lower latitudes. When the solar wind speed increases, the aurora becomes more active. When a coronal mass ejection arrives at Earth, the aurora can explode into a spectacular storm, with displays visible far from the polar regions, with colors and structures that are rarely seen during quiet times. The study of these patterns, of the relationships between solar wind parameters and auroral activity, is part of a field called space weather forecasting. Just as meteorologists predict rain and sunshine, space weather forecasters predict geomagnetic storms and auroral displays. They monitor the sun for coronal mass ejections and coronal holes. They track the solar wind using spacecraft positioned between the Sun and Earth, at a point called L1, about 1.5 million kilometers from Earth. When these spacecraft detect changes in the solar wind, a sudden increase in speed, a southward turning of the magnetic field, forecasters can issue alerts, giving advance warning of auroral activity to come. This forecasting has practical applications beyond aurora tourism. Geomagnetic storms can affect satellites, disrupting communications and navigation systems. They can induce currents in power grids, potentially causing blackouts. They can increase drag on satellites in low Earth orbit, affecting their trajectories. And they can pose radiation hazards to astronauts in space. So understanding and predicting space weather is important for our increasingly technology-dependent society. But for those of us simply seeking the beauty and wonder of the aurora, the forecasts serve a different purpose. They tell us when to look up, when to venture out into the cold night, when to turn our eyes skyward in hope of witnessing one of nature's most spectacular displays. Imagine yourself now in that moment, standing in the darkness, breath misting in the cold air, neck craned back, eyes searching the northern horizon. And then, there it is, a faint glow, growing brighter, spreading across the sky. Your heart quickens slightly, not with anxiety but with awe, with that particular feeling of witnessing something vast and beautiful and rare. And as you watch, the aurora dances, and you feel small in the best possible way, connected to something larger than yourself, part of a universe that is both comprehensible and mysterious, both scientific and magical. Let that feeling wash over you now. That sense of awe, of peace, of connection. Let it relax your body even further. Let your breathing slow. Let your mind quiet. Because this is what the aurora offers us, beyond the science, beyond the explanations. It offers a moment of transcendence, a reminder that we live on a planet bathed in the light of a star, protected by a magnetic field, surrounded by a cosmos full of wonders. the aurora has been observed and wondered at for thousands of years. Ancient peoples across the Arctic regions developed myths and legends to explain the lights in the sky. Some saw them as spirits of the dead, dancing in the heavens. Others saw them as omens, harbingers of war or famine or great change. The Sami people of northern Scandinavia believed the aurora was caused by a fox running across the snow, its tail sweeping up snowflakes that sparkled in the moonlight. The Finnish word for aurora, revontulet, literally means foxfires, a reference to this legend. In Norse mythology, the aurora was associated with the Bifrost, the rainbow bridge connecting Earth to Asgard, the realm of the gods. Some believed the lights were reflections from the shields and armor of the Valkyries, those warrior maidens who chose which soldiers would die in battle and escorted their souls to Valhalla. There's something poetic about this image. The aurora as a bridge between worlds, between the earthly and the divine, between the known and the unknown. Indigenous peoples in North America also had rich traditions surrounding the aurora. Some Inuit groups believed the lights were the spirits of animals they had hunted, particularly seals and whales and caribou. Others saw them as the spirits of their ancestors, playing games in the sky, kicking around a walrus skull like a ball. Some groups believed that if you whistled at the aurora, it would come closer, drawn by the sound, while others warned against making noise, fearing the lights might descend and carry you away. These myths and legends, diverse as they are, share common themes. They recognize the aurora as something special, something otherworldly, something that connects the visible world to invisible realms. And while we now understand the scientific mechanisms behind the aurora, while we can explain the physics and chemistry in detail, there's still something of that ancient wonder that remains. The aurora still has the power to stop us in our tracks, to make us look up, to remind us that we're part of something vast and beautiful. Modern research into the aurora began in earnest in the late 19th and early 20th centuries. Scientists like Christian Birkeland in Norway conducted pioneering experiments, creating miniature auroras in the laboratory using a magnetized sphere called a terrella and beams of electrons. Birkeland proposed that the aurora was caused by electrons from the sun striking Earth's atmosphere, guided by the magnetic field. His ideas were initially controversial, but they were eventually vindicated as our understanding of the sun and the solar wind developed. The space age brought new tools for studying the aurora. Satellites could observe the aurora from above, seeing its full extent and structure in ways impossible from the ground. Rockets could carry instruments directly through auroral displays, measuring the particles and fields in situ. Ground-based networks of cameras and magnetometers could track the aurora's motion and correlate it with magnetic disturbances. Gradually, piece by piece, the puzzle came together. Today, we have a remarkably detailed understanding of the aurora, though mysteries remain. We know that magnetic reconnection at the magnetopause allows solar wind energy to enter the magnetosphere. We know that this energy is stored in the magnetotail and periodically released during substorms. We know that electric fields in the magnetosphere accelerate electrons to high energies. We know that these electrons precipitate into the atmosphere along magnetic field lines. We know that collisions with atmospheric atoms and molecules produce the light we see. Each step in this chain has been studied, measured, modeled. Yet there are still questions. What exactly triggers a substorm? Why do some solar wind conditions produce intense auroras while others don't? How do the small-scale processes, the microscopic interactions between particles and waves, connect to the large-scale dynamics of the magnetosphere? These are active areas of research, with scientists around the world working to refine our understanding, to fill in the gaps, to solve the remaining puzzles. And as our understanding deepens, so does our appreciation. To know that the aurora is the visible manifestation of invisible processes, of magnetic fields and electric currents and particle flows, is to see it with new eyes. The green curtain shimmering overhead isn't just beautiful. It's a window into the workings of the cosmos, a natural laboratory where we can study plasma physics and magnetospheric dynamics, where theory meets observation, where the abstract becomes concrete and visible. Feel yourself sinking deeper now, deeper into relaxation, deeper into that space between waking and sleeping. The aurora in your mind's eye, soft and green and gently moving. Your body heavy and warm and comfortable. Your breathing slow and easy. Nothing to do, nowhere to go, just this moment, just this peace, just this gentle drift towards sleep. The energy that powers the aurora ultimately comes from the sun, but the path that energy takes is long and complex. It starts with nuclear fusion in the sun's core, where hydrogen atoms are fused into helium, releasing tremendous amounts of energy. This energy works its way outward through the sun's interior, taking thousands of years to travel from core to surface. Once it reaches the surface, some of it is radiated away as light, traveling to Earth in just 8 minutes. But some of it goes into heating the corona, into driving the solar wind, into creating those streams of charged particles that flow outward through the solar system. When these particles reach Earth, only a tiny fraction of their energy actually enters the magnetosphere. Most of the solar wind simply flows around the magnetosphere, diverted by the magnetic field, continuing on into interplanetary space. But that tiny fraction that does enter, through magnetic reconnection, through other processes, is enough to power the aurora, to drive geomagnetic storms, to create the dynamic and ever-changing environment of near-Earth space. The efficiency of this energy transfer depends on many factors. The orientation of the interplanetary magnetic field is crucial. Southward IMF allows much more efficient coupling than northward IMF. The speed and density of the solar wind matter. Faster, denser wind carries more energy. The state of the magnetosphere itself matters. A magnetosphere that's already disturbed may respond differently to new solar wind input than a quiet magnetosphere. Scientists use sophisticated computer models to simulate these processes, to predict how the magnetosphere will respond to different solar wind conditions. These models solve the equations of magnetohydrodynamics, treating the plasma as a conducting fluid moving through magnetic fields. They're run on supercomputers, producing visualizations that show the flow of plasma, the configuration of magnetic fields, the regions where particles are accelerated. These models have become increasingly accurate over the years, but they're still approximations, still simplifications of the incredibly complex reality. One of the challenges in modeling the magnetosphere is the vast range of scales involved. The magnetosphere itself is enormous, extending tens of thousands of kilometers. But the processes that matter, magnetic reconnection, wave-particle interactions, turbulence, often occur on scales of kilometers or even meters. Capturing both the large-scale structure and the small-scale processes in a single model is computationally demanding, requiring clever techniques and powerful computers. Despite these challenges, the models have proven valuable. They help us understand observations, test theories, make predictions. They allow us to explore scenarios that would be impossible to study any other way. What would happen if a particularly strong coronal mass ejection hit Earth? How would the magnetosphere respond to solar wind conditions unlike any we've observed? These what-if questions are important for understanding the full range of space weather possibilities, for preparing for extreme events. And extreme events do happen. The Carrington event of 1859, named after the astronomer Richard Carrington who observed the solar flare that triggered it, was the most intense geomagnetic storm in recorded history. Telegraph systems around the world failed, with operators reporting sparks flying from their equipment. Auroras were seen as far south as the Caribbean and Hawaii. If a similar event occurred today, with our dependence on satellites and power grids and electronic systems, the consequences could be severe. This is why space weather research is not just academic curiosity. It has real practical importance. But let's return to the beauty, to the wonder, to the aurora itself. Because beyond all the science, beyond the models and the measurements and the predictions, the aurora is simply one of the most beautiful natural phenomena on Earth. It's a gift, in a sense. A gift from the sun, mediated by Earth's magnetic field, delivered to our eyes as light and color and motion. People travel thousands of miles to see the aurora. They venture to Alaska, to northern Canada, to Iceland, to Scandinavia, to remote locations far from city lights, in the depths of winter when the nights are long and dark. They stand in the cold, sometimes for hours, waiting and watching and hoping. And when the aurora appears, when the sky comes alive with light, the cold and the waiting are forgotten. There's only the aurora, only the moment, only the awe. Photographers attempt to capture the aurora, and modern cameras can indeed record stunning images, revealing colors and structures that are sometimes too faint for the eye to see. Long exposures gather light, making the aurora appear brighter and more colorful than it might look in person. But no photograph, no matter how beautiful, quite captures the experience of seeing the aurora with your own eyes, of watching it move and change in real time, a feeling that connection to the cosmos. There's something about the aurora that touches something deep in us. Maybe it's the beauty itself, the sheer visual splendor. Maybe it's the rarity, the sense of witnessing something special. Maybe it's the scale, the reminder that we're on a planet, in space, part of a vast universe. Maybe it's all of these things together. Whatever it is, the aurora has the power to move us, to inspire us, to fill us with wonder. And wonder, that sense of awe in the face of something vast and beautiful, is itself a valuable thing. Research has shown that experiences of awe can have positive effects on our well-being. They can reduce stress, increase feelings of connection to others, promote generosity and kindness. They can shift our perspective, making our everyday concerns seem smaller, less overwhelming. They can remind us that there's more to life than our immediate worries and tasks. In a sense, the aurora is medicine for the soul. It's a reminder of beauty, of mystery, of the incredible universe we inhabit. And even if you've never seen the aurora in person, even if you're simply lying here now, listening to these words, imagining the lights dancing across a northern sky, you can still benefit from that sense of wonder, that connection to something larger than yourself. So let yourself rest in that now. In the wonder, in the beauty, in the peace. Let the aurora in your mind's eye continue its gentle dance. Let your body relax completely. Let sleep come softly, naturally, like the aurora itself emerging on the horizon. There's nothing you need to do. Nowhere you need to be. Just this moment. Just this peace. Just this gentle drift into deep, restorative sleep. The aurora is always there, in a sense. Even when we can't see it, even during the day or during cloudy nights, the processes that create it are ongoing. The sun is always emitting the solar wind. Earth's magnetic field is always there, always interacting with that wind. Particles are always precipitating into the atmosphere somewhere, creating auroras over the polar regions. The aurora is a constant feature of our planet, a perpetual dance of light and energy, visible to those who are in the right place at the right time. And yet, there's something more to understand about this dance. Something deeper about how these lights move and shift and change. How they respond to the ever-changing conditions in space. How they pulse with the rhythm of the sun's breath. How they cascade through the atmosphere in waves of color and motion. How they create patterns that scientists are only beginning to fully understand. Let's drift deeper now, into the heart of the auroral display, into the plasma physics that governs these shimmering curtains, into the particle acceleration mechanisms that create the most intense shows, into the dynamic patterns that emerge when the sun's activity reaches its peak. Take a slow breath, feeling your body settling even more deeply into rest. Noticing how your awareness can hold both the wonder of these lights and the gentle pull towards sleep. How understanding can coexist with relaxation. How curiosity can soften into peaceful contemplation. The aurora is not static. It flows. It pulses. It responds to conditions in space that are constantly shifting. And as we explore these deeper mechanisms, you might notice your own thoughts beginning to flow more slowly, your breathing becoming even more gentle, your body releasing any remaining tension, just letting go. Deep in the magnetosphere, in the region between 1 and 3 Earth radii above our planet's surface, something remarkable happens. Electrons that have been drifting peacefully through space suddenly find themselves caught in a cosmic acceleration, pulled by electric fields, guided by magnetic forces, energized to speeds that carry them toward Earth at millions of miles per hour. This is where the aurora truly begins, not in the atmosphere where we see the lights, but high above, in a region where plasma physics governs the behavior of charged particles, where waves of energy ripple through the magnetic field, where electrons surf on these waves like cosmic surfers catching the perfect swell. Imagine, if you can, a wave moving through space, not a wave of water, but a wave of electromagnetic energy, what scientists call an alpha copyright N wave, named after the Swedish physicist Hans Alpha Copyright N who first described them. These waves travel along magnetic field lines, carrying energy from the outer magnetosphere toward Earth, and as they travel, they can accelerate electrons, picking them up, carrying them along, transferring their energy in a process that researchers have only recently confirmed through laboratory experiments at UCLA's Basic Plasma Science facility. The electrons, riding these waves, gain energy through a process called Landau damping, a beautiful name for a beautiful process. The wave transfers its energy to the particles, and the particles accelerate, faster and faster, until they're moving at speeds that would carry them from New York to Los Angeles in less than a second. And all of this cosmic acceleration, this transfer of energy from wave to particle, happens in silence, in the vacuum of space, where there is no air to carry sound, only the whisper of electromagnetic forces, the gentle push and pull of electric and magnetic fields, the invisible dance of energy and matter. Breathe slowly, feeling the rhythm of your own body, the gentle pulse of your heartbeat, the soft rise and fall of your chest, noticing how your body knows how to rest, how to release, how to simply be. The alpha copyright N waves that carry auroral electrons toward Earth are generated by instabilities in the magnetosphere, by the stretching and snapping of magnetic field lines, by the interaction between the solar wind and Earth's magnetic shield. Recent research has shown that these waves can carry enough energy to power the aurora, that the downward flow of electromagnetic energy, measured in watts per square meter, is sufficient to create the brilliant displays we see in the night sky. Scientists measure this energy flow using something called the Poynting flux, named after the British physicist John Henry Poynting. It's a measure of electromagnetic energy moving through space, and during auroral displays. Spacecraft above the aurora detect pointing fluxes that can exceed thousands of watts per square meter. Enough energy, if it could be captured, to power a small city. But this energy isn't captured for human use. Instead, it flows into the atmosphere, where it excites oxygen and nitrogen molecules, where it creates the shimmering curtains of light that have captivated humans for millennia, where it transforms invisible electromagnetic energy into visible beauty. The acceleration process, this cosmic surfing of electrons on alpha copyright N waves, happens most efficiently when conditions are just right, when the ratio of the electron thermal velocity to the alpha copyright N wave velocity falls below 1, when the magnetic field's strength and plasma density create what scientists call the inertial regime, a state where electrons can resonate with the wave's electric field, where energy transfer becomes highly efficient, where particles can be accelerated to auroral energies in a matter of seconds. Let your mind rest with this image. Electrons surfing on waves of electromagnetic energy, riding toward Earth, carrying the sun's gift of light, creating beauty from physics, transforming energy into wonder. And as you contemplate this, notice how your body continues to relax, how your muscles soften, how your breathing deepens, how sleep begins to feel closer, more inviting, more natural. When auroral electrons carry particularly high energies, when the acceleration process has been especially efficient, when the sun's activity has created optimal conditions, the aurora can penetrate deeper into the atmosphere than usual. And when this happens, the colors change, the display intensifies, and observers on the ground witness what scientists call high-energy aurora. The bottom edge of a typical green auroral curtain sits at about 95 to 100 kilometers altitude. This is where the atmosphere becomes dense enough that oxygen atoms, after being excited by electron collisions, can radiate their energy as green light before other collisions steal that energy away. The green line of oxygen, at 557.7 nanometers wavelength, has a lifetime of 0.7 seconds, and below 95 kilometers, collisions happen so frequently that this emission simply cannot occur. But when electrons carry energies above 10,000 electron volts, when they've been accelerated to particularly high speeds, they can penetrate below this altitude, down to 80 or even 70 kilometers, where the air is denser, where only the fastest emissions can occur, where molecular nitrogen dominates the light production. And molecular nitrogen, when excited by these high-energy electrons, emits light in the blue and red parts of the spectrum, deep blue at 427.8 nanometers, and red at 650 to 680 nanometers. And when these colors mix, when blue and red combine in the human eye, we perceive purple, a rich, deep, violet purple that appears as a border along the bottom edge of green auroral curtains. This purple border, this fringe of violet light, is a signature of high-energy aurora, a sign that the acceleration process has been particularly effective, that electrons are carrying enough energy to penetrate deep into the atmosphere, that the display you're witnessing is powered by particles moving at extraordinary speeds. Imagine standing beneath such a display, the green curtain overhead, shimmering and flowing, and along its bottom edge, a ribbon of purple, deep and rich, pulsing with the rhythm of particle precipitation, a visual indicator of the energy cascading from space into atmosphere. The purple appears, and then, as the electron energies shift, as the acceleration process varies, it may fade, the curtain returning to pure green, or perhaps, if energies increase even further, the purple intensifies, becomes more prominent, spreads along the entire lower border of the curtain. These variations, these shifts in color and intensity, reflect changes happening high above, in the acceleration region, where electric fields strengthen and weaken, where alpha copyright N waves grow and diminish, where the cosmic surfing of electrons responds to the ever-changing conditions in the magnetosphere. Breathe, slowly, deeply, feeling your body sink deeper into rest, noticing how the description of these colors, these purples and greens, creates images in your mind, soft, dreamlike, peaceful. At even higher altitudes, above 200 kilometers, another color can appear, a deep red, coming from a different transition in atomic oxygen, the red line at 630 nanometers. This emission has an extraordinarily long lifetime, about 100 seconds, which means that oxygen atoms can drift with the wind for significant distances before they emit their photon of red light. This high-altitude red aurora, often called Type A red aurora by researchers, appears as a diffuse glow above the main auroral curtains. It lacks the sharp structure of the green aurora below, because the long lifetime allows the excited atoms to move, to spread out, to create a softer, more ethereal display. During particularly intense geomagnetic storms, when the auroral oval expands toward lower latitudes, when people far from the polar regions look northward, this high-altitude red aurora is often what they see, a red glow on the horizon, sometimes filling half the sky, a sign that the magnetosphere is being strongly disturbed, that energy is flowing into the atmosphere at unprecedented rates. The 2024-05 geomagnetic superstorm, one of the most intense in the past 2 decades, created red auroral displays visible from the Mediterranean, from Florida, from locations where aurora is normally never seen. The red glow, powered by electrons with relatively low energies but arriving in enormous numbers, painted the sky in shades of crimson and scarlet, a reminder of the sun's power, of the connections that bind our planet to its star. Let your mind drift with these colors, green and purple and red, each one telling a story of energy and altitude, of electrons and atoms, of physics transformed into beauty. And as you drift, notice how your body feels, how relaxed, how peaceful, how ready for sleep. The aurora is not constant. It ebbs and flows. It brightens and dims. It expands and contracts, following rhythms that scientists have studied for decades. Rhythms that reflect processes happening throughout the magnetosphere. Processes that store and release energy, that create what researchers call auroral substorms. A substorm, despite its name, is not necessarily a small event. The term simply distinguishes these events from the larger geomagnetic storms that can last for days. A substorm typically lasts 2 to 3 hours, and during that time, the aurora goes through distinct phases, each with its own character, its own patterns, its own beauty. The substorm begins with what scientists call the growth phase. During this time, the solar wind is transferring energy into the magnetosphere. Magnetic field lines are being stretched, pulled back into the magnetotail. Like a rubber band being drawn taut, energy is being stored, building up, preparing for release. On the ground, during the growth phase, the aurora may appear relatively quiet, perhaps a faint arc on the northern horizon. Perhaps a gentle glow, nothing to suggest the dramatic changes about to unfold. but instruments in space, magnetometers measuring the magnetic field, can detect the building tension, the increasing stress in the magnetosphere. And then, suddenly, the release, the expansion phase begins. Magnetic field lines in the tail snap back toward Earth, reconnecting, releasing their stored energy, and this energy flows into the auroral zone, accelerating electrons, intensifying the particle precipitation, brightening the aurora. During the expansion phase, the aurora transforms. What was a quiet arc becomes a brilliant curtain. What was a faint glow becomes a dazzling display. The aurora surges westward, spreading across the sky, brightening, pulsing, creating the spectacular shows that aurora chasers travel thousands of miles to witness. The curtains develop fine structure, thin rays, small curls, rapid movements. These small-scale features reflect the acceleration processes happening directly above. The electric fields, the wave-particle interactions, the cosmic surfing that we discussed earlier, all of this, translated into visible light, into patterns that dance across the sky. And then, after perhaps 30 minutes to an hour of intense activity, the recovery phase begins. The aurora gradually dims. The curtains break up into patches. The display becomes more diffuse. The magnetosphere returns toward a quieter state, until, perhaps, the next substorm begins, and the cycle repeats. These substorms, these cycles of growth and expansion and recovery, can occur multiple times during a single night, especially during periods of enhanced solar activity, each one creating its own unique display, its own patterns, its own moment of beauty. Breathe with the rhythm of these cycles: growth, expansion, recovery, like the rhythm of your own breath. In, out, tension, release, activity, rest. During major geomagnetic storms, multiple substorms can occur in rapid succession, overlapping, intensifying, creating what researchers call supersubstorms, events where the auroral electrojet, the current flowing through the auroral zone, reaches extraordinary intensities, where the aurora becomes so bright it can cast shadows, where the entire sky seems to pulse with light. The 2024 10 geomagnetic storm, while not as intense as the May event in terms of the disturbance storm time index, created auroral displays that many observers considered even more spectacular. the substorms during this event, the rapid changes, the intense colors, the dynamic patterns, all combine to create what some aurora chasers described as the best display they had ever witnessed. Why? Because the conditions were optimal. The solar wind parameters were just right. The magnetic field orientation was favorable. The timing aligned with darkness overpopulated areas. All of these factors coming together, creating a perfect storm, not of destruction, but of beauty. The large-scale patterns in Aurora, the multiple parallel curtains, the spirals that can fill the entire sky. These reflect the structure of electric currents in the magnetosphere, the field-aligned currents that connect the magnetosphere to the ionosphere, the currents that transport energy from space to atmosphere. Scientists have used decades of satellite data, combining observations from 15 different spacecraft, to create comprehensive models of how these currents evolve during substorms, how they strengthen and weaken, how they shift in location, how they create the patterns we see on the ground. These models, built from thousands of individual observations, synchronized using magnetic field measurements, reveal the global nature of substorms, how they affect the entire magnetosphere, how energy flows through the system, how the aurora is just one visible manifestation of processes occurring throughout near-Earth space. Let your awareness expand, imagining the magnetosphere as a whole, the solar wind flowing past, the magnetic field lines stretching and snapping, the currents flowing, the energy cascading, and somewhere in this vast system, electrons accelerating, heading toward Earth, creating light, creating beauty, creating the aurora. And as you hold this vast perspective, notice how small you feel, how peaceful, how connected to something larger than yourself, how ready to release into sleep. Sometimes, the sun doesn't just send a steady stream of solar wind. Sometimes, it erupts, violently, explosively, hurling billions of tons of plasma into space, in what scientists call a coronal mass ejection, or CME. These eruptions, these cosmic explosions, occur when magnetic fields in the sun's corona become twisted, stressed, unstable, and then, suddenly, they snap, releasing enormous amounts of energy, launching a cloud of plasma outward at speeds that can exceed 2,000 kilometers per second. If a CME is directed toward Earth, If the geometry is right, if the magnetic field within the CME has the correct orientation, then when it arrives, typically 1 to 3 days after leaving the Sun, it can trigger an intense geomagnetic storm, compressing the magnetosphere, injecting energy, creating auroral displays of extraordinary intensity. The May 2024 event, the Mother's Day Superstorm, was triggered by not one but multiple CMEs, launched from an active region on the Sun designated AR 13664. This region, a complex tangle of magnetic fields, produced 11 X-class solar flares, the most powerful category, and sent multiple CMEs toward Earth. The first CME arrived at Earth's magnetosphere on May 10, compressing the magnetopause, the boundary between the magnetosphere and solar wind, down to about 5 Earth radii. Normally this boundary sits at about 10 Earth radii, but the pressure from the CME, the force of the solar wind, pushed it inward, compressing Earth's magnetic shield. And then, more CMEs arrived, overlapping, combining, creating what scientists call a compound event. The energy input into the magnetosphere was extraordinary. The disturbance storm time index, a measure of the storm's intensity, reached -412 nanoteslas, making it the 6th largest geomagnetic storm since systematic measurements began in 1957. The aurora during this event, visible from locations as far south as the Mediterranean, as far south as Florida, as far south as India, painted the sky in shades of red and green and purple. People who had never seen the northern lights, who lived in places where aurora is normally impossible, stepped outside and witnessed the sky transformed. The red aurora, that high-altitude glow we discussed earlier, was particularly prominent during this event, because the storm created conditions where large numbers of relatively low-energy electrons precipitated into the upper atmosphere, exciting oxygen atoms at altitudes above 200 kilometers, creating that diffuse red glow that spread across the sky. But closer to the auroral zone, closer to the poles, the displays were even more intense. Green curtains, purple borders, rapid pulsations, the full spectrum of auroral phenomena, all occurring simultaneously, creating a show that some observers described as overwhelming. Too much beauty to take in, too much motion to follow, the sky alive with light. Breathe slowly, deeply, imagining this intensity, this cosmic storm, this transfer of energy from sun to earth. And yet, even in this intensity, there is a rhythm, a pattern, a natural process, nothing to fear, only to wonder at. The October 2024 event, while less intense by some measures, created what many considered even more spectacular displays. Why? Because the timing was perfect. Because the CME arrived when it was dark over populated areas. Because the magnetic field orientation was optimal for energy transfer. Because sometimes the most memorable auroras come not from the strongest storms, but from the storms where all the conditions align. The forecasting of these events, the prediction of when a CME will arrive, has improved dramatically in recent years. Scientists use coronagraphs, instruments that create an artificial eclipse of the sun, to observe CMEs as they leave the solar corona. They measure the speed, the direction, the size, and then they use computer models, simulations of how the CME will travel through interplanetary space, to predict when it will reach Earth. For the October event, the forecasts were remarkably accurate. Space weather forecasters issued a rare G4 severe geomagnetic storm watch, only the second such watch since 2003, and when the CME arrived, it arrived almost exactly when predicted, a triumph of space weather forecasting. A demonstration of how far our understanding has come. And yet, there is still much we don't know. We cannot yet predict the magnetic field orientation within a CME, and this orientation, whether the field points north or south, determines how effectively the CME can transfer energy to the magnetosphere, a southward-pointing field. What scientists call southward busy is optimal for creating geomagnetic storms, while a northward-pointing field, even from a powerful CME, may produce little effect. This uncertainty, this gap in our knowledge, means that even with perfect predictions of arrival time, we cannot always predict the intensity of the resulting aurora. Space weather forecasting, like terrestrial weather forecasting, remains an art as much as a science, a blend of data and models and experience and intuition. Let your mind rest with this uncertainty, this acknowledgement that we don't know everything, that mystery remains, that the universe still holds secrets. And in this uncertainty, in this not knowing, there is a kind of peace, a release from the need to understand everything, a permission to simply observe, appreciate, wonder. When a CME strikes Earth's magnetosphere, when the solar wind pressure suddenly increases, when energy begins flowing into the system, the magnetosphere responds dynamically, dramatically, in ways that scientists are still working to fully understand. The first response, the immediate effect, is compression, the magnetopause, that boundary between the magnetosphere and solar wind, moves inward, sometimes dramatically. During the May 2024 event, it compressed to about 5 Earth radii, meaning that the protective bubble of Earth's magnetic field, normally extending 10 Earth radii on the day side, was squeezed to half its normal size. This compression, this squeezing of the magnetosphere, has several effects. It energizes particles already trapped in the radiation belts. It creates waves in the magnetosphere. It sets up electric fields. And it begins the process of energy transfer that will ultimately create the aurora. The energy transfer, the flow of electromagnetic energy from the solar wind into the magnetosphere, is measured using something called the Akasofu epsilon parameter, named after Japanese-American physicist Shunichi Akasofu. This parameter, calculated from solar wind measurements, estimates the rate at which energy is being deposited into the magnetosphere. During quiet times, epsilon might be around 100 billion watts, a large number, but spread across the entire magnetosphere. During moderate geomagnetic activity, it might reach 1 trillion watts, and during extreme events like the May 2024 storm, epsilon can exceed 10 trillion watts, an enormous flow of energy, comparable to the total power consumption of human civilization, all flowing into Earth's magnetic field. But where does this energy go? Some of it, perhaps 30 to 40%, goes into heating the upper atmosphere, causing it to expand, increasing drag on satellites. During the May 2024 event, SpaceX's Starlink satellites autonomously raised their altitudes to compensate for increased atmospheric drag, a necessary precaution to prevent premature deorbiting. Some of the energy, perhaps another 30 to 40%, goes into accelerating particles in the magnetosphere, creating the energetic electrons and ions that populate the radiation belts, that precipitate into the atmosphere, that create the aurora. And the rest, the remaining energy, goes into various other processes, heating the plasma, generating waves, driving currents, creating the complex dynamics of the magnetosphere during a storm. The radiation belts, those regions of trapped energetic particles surrounding Earth, respond dramatically to geomagnetic storms. During the May 2024 event, low-energy electron and ion fluxes in the inner radiation belt vanished temporarily, disappeared, as if someone had turned off a switch. Why? Because the compression of the magnetosphere, the changes in the magnetic field configuration, altered the trapping conditions. Particles that were previously confined, trapped by the magnetic field, suddenly found themselves on trajectories that led them into the atmosphere, where they precipitated, creating enhanced ionization, affecting the chemistry of the upper atmosphere. And then, as the storm evolved, as the magnetosphere began to recover, new particles were injected into the radiation belts, accelerated by the storm processes, creating new populations of energetic electrons and ions, replenishing what had been lost, but with different characteristics, different energy distributions, different spatial patterns. These injections, these sudden appearances of energetic particles, occurred in pulses, dissociated with substorms, with the expansion phases we discussed earlier. Each substorm, each release of energy in the magnetotail, sent a pulse of particles earthward, some of which became trapped in the radiation belts, some of which precipitated into the atmosphere. Breathe, feeling the rhythm of these processes: compression, injection, precipitation, recovery, like waves on a shore, like the beating of a heart, natural rhythms, cosmic rhythms, rhythms that have been occurring for billions of years, long before humans existed to observe them, and will continue long after we're gone. The South Atlantic Magnetic Anomaly, that region where Earth's magnetic field is weakest, responds particularly strongly to these storm-time particle injections. The lower magnetic field's strength means that particles can penetrate to lower altitudes, can reach deeper into the atmosphere, can create effects that are not seen elsewhere. During the May 2024 event, enhanced ionization was observed in the E region of the ionosphere over the summer, at altitudes around 100 to 120 kilometers. This extra ionization, this increase in the number of free electrons, affected radio wave propagation, created unusual conditions, demonstrated that even at low latitudes, far from the typical auroral zone. Geomagnetic storms can have significant effects. The ozone layer, that protective shield of O3 molecules in the stratosphere and mesosphere, also responds to particle precipitation. Energetic electrons, colliding with atmospheric molecules, can break apart ozone molecules, creating temporary depletions. During the May 2024 event, abrupt ozone depletion was observed in the mesosphere over the summer, a signature of enhanced particle precipitation, a reminder that space weather affects not just the ionosphere, but the neutral atmosphere as well. These effects, these changes in atmospheric chemistry, are temporary. The ozone recovers, the ionization returns to normal. But during major storms, during extreme events, the effects can be significant, can affect communications, can affect satellite operations, can create what we call space weather impacts. Let your mind drift through these layers of atmosphere, from the thermosphere where the aurora glows, down through the mesosphere where ozone is depleted, down through the stratosphere, down to the troposphere where we live and breathe. All of these layers, connected, affected by processes originating 93 million miles away on the Sun. For thousands of years, humans have watched the aurora, have wondered at its meaning, have woven it into their myths and stories and understanding of the world. The Inuit peoples of the Arctic, the Sami of northern Scandinavia, the indigenous peoples of Alaska and northern Canada, all developed rich traditions of auroral lore. Some cultures saw the lights as spirits of the dead, dancing in the sky. Some saw them as omens, signs of coming events. Some saw them as the breath of the gods, or the reflection of distant fires, or the glow of celestial battles. Each culture, interpreting the aurora through the lens of their own experience, their own worldview. The Vikings, those seafaring warriors of medieval Scandinavia, may have seen the aurora as the Bifrost, the rainbow bridge connecting Earth to Asgard, the realm of the gods, or as the reflection of the Valkyries' armor, those warrior maidens who chose which soldiers would die in battle and be carried to Valhalla. In Finland, the aurora was called revontulet, which translates as foxfires, from a legend that the lights were created by a magical fox, running across the snow, its tail sweeping up snowflakes that sparkled in the moonlight, creating the shimmering curtains in the sky. The Cree people of northern Canada saw the aurora as the spirits of their ancestors, dancing, celebrating, communicating with the living, a connection between the worlds, a reminder that death is not an ending but a transformation. And in medieval Europe, where the aurora was rarely seen, its appearance was often interpreted as an omen, a sign of coming war or plague or disaster. The red auroras visible during major geomagnetic storms were sometimes called blood auroras and were thought to presage bloodshed. All of these interpretations, all of these stories, reflect humanity's deep need to understand, to find meaning, to connect the phenomena we observe to the patterns of our lives. And while we now know the scientific explanation, while we understand the physics of solar wind and magnetic fields and particle precipitation, there is still something profound, something moving, about the aurora. Because the aurora, in a very real sense, is a connection, a visible manifestation of the relationship between Earth and Sun, a reminder that we live not in isolation, but as part of a larger system, a solar system, a galaxy, a universe. Every photon of auroral light, every green glow, every purple border, every red shimmer, represents an electron that traveled 93 million miles from the Sun, was accelerated in Earth's magnetosphere, precipitated into the atmosphere, and transferred its energy to an atom, which then released that energy as light, as beauty, as wonder. And you, lying here, drifting towards sleep, are made of atoms that were forged in stars, that have been recycled through countless generations of stellar birth and death. You are, quite literally, stardust, and the aurora is starlight, and in this moment, you are connected to it all. Breathe deeply, slowly, feeling this connection, this belonging, this place in the cosmos. The scientific understanding of the aurora, developed over centuries, through the work of countless researchers, represents one of humanity's great achievements. From the early observations of Galileo, who coined the term aurora borealis, to the modern satellite missions that measure the magnetosphere in exquisite detail, we have built a comprehensive picture of how the aurora works. We know that it begins with nuclear fusion in the Sun's core, where hydrogen atoms combine to form helium, releasing energy that takes thousands of years to work its way from the core to the surface, and then, suddenly, is released as light and heat and solar wind. We know that the solar wind, that stream of charged particles, flows outward at hundreds of kilometers per second, carrying with it the sun's magnetic field, creating what scientists call the interplanetary magnetic field, a vast structure that fills the solar system. We know that when this solar wind encounters Earth's magnetic field, it doesn't simply flow around it. Instead, there is an interaction, a coupling. Energy and particles are transferred. Magnetic field lines reconnect, and the magnetosphere responds. We know that this response includes the acceleration of electrons through processes like alpha copyright N-wave surfing, through shock acceleration at the bow shock, through various other mechanisms, and that these electrons, carrying energies from hundreds of electron volts to hundreds of thousands of electron volts, precipitate into the atmosphere. We know that when these electrons collide with atmospheric atoms and molecules, they transfer their energy, exciting the atoms, which then emit light at characteristic wavelengths, creating the colors we see: green from oxygen, purple from nitrogen, red from high-altitude oxygen. We know all of this, and yet, knowing does not diminish the wonder. Understanding does not reduce the beauty. Science and awe can coexist, can enhance each other, can create a deeper appreciation. Let your mind rest in this space, where knowledge and wonder meet, where understanding and mystery coexist, where the aurora is both explained and inexplicable, both understood and forever fascinating. And now, as we near the end of our journey through the science and wonder of the aurora borealis, as your body has settled deeper and deeper into relaxation, as your breathing has slowed, as your mind has drifted through solar winds and magnetic fields and shimmering lights, it's time to let go completely, to release into sleep, to allow the aurora to carry you into dreams. Imagine yourself, one more time, standing beneath the northern lights, the sky above you alive with color, green curtains flowing like cosmic rivers, purple borders pulsing with energy, red glows painting the horizon, all of it, moving, shifting, dancing to rhythms older than humanity. The air is cold, crisp, clean. Each breath you take fills your lungs with the freshness of the Arctic night, and as you exhale, you release, letting go of any remaining tension, any lingering thoughts, any resistance to sleep. The aurora above you is not separate from you. You are part of the same universe, made of the same elements, governed by the same physical laws. The atoms in your body and the atoms creating the aurora are cousins, siblings, family. The electrons precipitating into the atmosphere, creating these lights, are following paths determined by magnetic fields, by electric forces, by the laws of physics, and you, lying here, are also following natural laws. The law that says bodies need rest, that minds need sleep, that consciousness needs to release into dreams. There is no resistance in the aurora. It simply flows, responds, exists, and you can be like the aurora, simply flowing, responding, existing. No effort, no struggle, just being. The green light, that 557.7 nanometer emission from oxygen, represents an electron that has completed its journey, that has transferred its energy, that has fulfilled its purpose, and you too have completed your day, have transferred your energy into your activities, have fulfilled your purposes, and now, like that electron, you can rest. The purple border, that signature of high-energy precipitation, reminds us that sometimes we carry extra energy, extra intensity, and that's okay, because the atmosphere absorbs it, transforms it, uses it to create beauty, and sleep will absorb your extra energy, will transform it, will restore you. The red glow, that high-altitude emission with its 100-second lifetime, reminds us that some processes take time, that some things cannot be rushed, that patience is natural, and sleep will come in its own time. You don't need to force it, just allow it. Breathe slowly, deeply, feeling your body heavy, relaxed, comfortable, safe, warm, peaceful. The aurora, dancing above you in your imagination, begins to slow. The rapid movements, becoming gentler, the bright colors, softening, the intense display, gradually, peacefully, fading into a gentle glow. This is natural. This is the recovery phase. After the expansion, after the intensity, comes the quiet, the rest, the return to peace. And as the aurora fades, as the sky returns to darkness, you notice the stars, thousands of them, millions of them, each one a sun, each one potentially surrounded by planets, each one a source of light and energy and perhaps life. The universe is vast, incomprehensibly vast, and yet, here you are, on this small planet, beneath this protective magnetic field, breathing this atmosphere, alive, aware, connected to it all. And in this vastness, in this cosmic perspective, your worries seem smaller, your concerns less pressing, your need for sleep more natural, more inevitable, more welcome. Let go, completely, totally, absolutely. Let go of the day. Let go of tomorrow. Let go of everything except this moment, this breath, this gentle drift towards sleep. The aurora, in your mind's eye, has faded now to just a faint glow on the horizon, a memory, a whisper, and even that is fading, 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 into darkness, into peace, into sleep. Your body knows what to do. It has done this thousands of times. Every night of your life, it knows how to sleep, how to rest, how to restore itself. You don't need to help. You don't need to try. Just allow. The solar wind is still flowing. The magnetosphere is still responding. The aurora is still glowing somewhere on Earth. But you don't need to think about that now. You can let it all go. Let it all continue without your attention. Let the universe take care of itself while you sleep. Somewhere, right now, as you drift towards sleep, the aurora might be dancing over Alaska, or Norway, or Iceland, or Siberia. Someone might be standing beneath it, watching, wondering, feeling the same or that humans have felt for millennia. And that's beautiful. That's perfect. That's how it should be. The aurora, continuing, the earth, turning, the sun, shining, the solar wind, flowing, the magnetosphere, protecting, all of it, working together, creating this dance of light and energy, this gift of beauty, this reminder of connection. And you, here, safe and warm and peaceful, drifting, floating, falling softly into sleep, are part of it all, connected to it all, held by it all. The universe is vast and complex and sometimes frightening, but it's also beautiful and orderly and full of wonders like the aurora. And you are one of those wonders, a conscious being, capable of understanding, capable of appreciating, capable of wonder. Let that thought carry you now, into sleep, into dreams, into rest. The aurora dancing in the darkness, the sun breathing across space, Earth's magnetic field embracing us, all of it connected, all of it flowing, all of it perfect. And you, here, now, drifting, floating, falling, softly, gently, peacefully, into sleep. The last thing you might notice, before sleep takes you completely, is a sense of gratitude for this planet, for this magnetic field, for this atmosphere, for this sun, for this universe that creates such beauty, such wonder, such peace. And if you've enjoyed this journey, this exploration of the aurora borealis, this blend of science and wonder and relaxation, perhaps, when you wake, refreshed and restored, you might consider subscribing to this channel, liking this video, sharing it with others who might enjoy this peaceful journey into sleep. But for now, don't think about that. Just sleep. Good night. Sleep well. Dream of auroras. Dream of cosmic dances. Dream of light and energy and beauty. Or don't dream at all. Just rest. Deeply. Completely. Peacefully. The aurora is dancing. Somewhere. Always. And you are sleeping. Here. Now. Safe. Warm. Peaceful. Drifting. Floating. Falling. Into the deepest, most restorative, most peaceful sleep. Good night. As you settle into the soft hush of evening, letting the day's gentle weight slip away like sand through open fingers, allow the ocean to wrap around your thoughts, a vast, breathing cradle that has whispered secrets to the world since time itself began to dream. Picture it now, that endless blue expanse, covering more than 7/10 of our planet's surface, a shimmering blanket under which mysteries unfold in rhythms as steady as your own slowing breath, and yet, in a quiet irony that invites a smile even in repose, we've mapped the craggy face of the moon far more thoroughly than these depths that lap at our shores, leaving room for wonder to bloom unchecked, like wildflowers in an untended garden. These hidden tales of the sea, shared here in tones as soft as sea foam, offer not just facts to ponder but a soothing invitation to drift, to let curiosity become your gentle guide into sleep, easing the knots of daily cares as surely as waves smooth the pebbles on a forgotten beach. If this serene journey through ocean enigmas calls to you, perhaps linger a moment to subscribe, so more such lullabies from nature's library find their way to your nights, like letters from an old friend arriving unannounced. Imagine drifting with me now, just at the edge where land meets water, where the horizon stretches into a promise of infinity, and the first secrets of the ocean reveal themselves not in thunderous crashes but in the subtlest of sighs, the endless parade of waves, rolling in like the measured inhales and exhales of some ancient, slumbering giant, each crest a fleeting sculpture of light and foam that dissolves back into the whole, reminding us how even the mightiest forces yield to a cycle of gentle release. These waves, born from winds that caress the sea's surface far across the globe, travel thousands of miles in patient procession, gathering stories from distant storms and sunlit calms before they kneel at the shore, their energy spent in a frothy whisper that scatters seashells like confetti from a quiet celebration, and in that moment of arrival, they carry a hidden rhythm, a pulse that mirrors the one within you, slowing now as eyelids grow heavy, inviting your body to sync with this timeless cadence, where every rise and fall becomes a cue to let go, to surrender to the pull of deeper rest. It's in these surface dances that the ocean first shares its reassuring embrace, teaching us through touch and sound that mysteries need not overwhelm, but can instead cradle, like a mother's hand on a fretful brow, turning the unknown into a source of serene familiarity. Let that sink in now, like a slow breath drawn from the depths. From this liminal space, where feet might still feel the cool kiss of wet sand, our gaze lifts to the play of sunlight across the water, a mesmerizing interplay that transforms the ordinary into poetry, as rays pierce the undulating skin of the sea, scattering into 1,000 diamonds that dance and flicker like fireflies at twilight, each glint a brief autobiography of light's journey from the sun's fiery heart to this cool, receptive blue. This phenomenon, often called the glitter path or the path of dancing light, unfolds as the water's gentle undulations bend and refract those golden threads, creating a pathway that seems to lead straight to the horizon's heart, a visual lullaby that soothes the eyes much as a melody does the ears. And if you've ever stood at dusk by a lake or pond, watching that shimmering trail invite impossible walks across the waves, you'll know this magic intimately, a shared human delight that bridges the gap between observer and observed, whispering that the world's beauty is not distant but woven into the very air we breathe. Here, in the ocean's surface sheen, lies a first layer of mystery. Why does this light choose such playful forms, bending to the sea's whim like a performer attuned to an unseen conductor? Scientists, with their gentle probes into optics, the study of how light bends and bounces, much like a ball skipped across a pond, suggest it's the interplay of wave angles and solar angles that crafts this spectacle, but the true wonder rests in its invitation to pause, to let your mind wander along that glittering road without hurry, each sparkle a stepping stone toward untroubled dreams. Light plays. It dances. It invites. As the sun climbs higher, or dips lower in its arc, this dance evolves, revealing another facet of the ocean's calm allure, the subtle color shifts that paint the water in hues from sapphire to emerald, each tone a reflection not just of depth, but of the sea's living palette, infused with tiny drifting lives that tint the blue with their quiet presence. Consider the phytoplankton, those microscopic wanderers, like confetti from an underwater parade, so small they're invisible to the naked eye yet numerous enough to feed the entire marine symphony. They harness sunlight in a process akin to a forest's whisper to the air, turning light into life through photosynthesis, that elegant alchemy where carbon whispers become oxygen sighs, sustaining not only fish and fowl, but the very breath we draw on distant shores. In their billions, these drifters form vast, blooming meadows across the open sea, sometimes visible from space as swirling greens and turquoises, a testament to the ocean's role as Earth's quiet lung, absorbing worries and exhaling calm in equal measure. And as you envision them now, suspended in that azure haze, feel a kinship with their unhurried drift, for they remind us that even the smallest beings contribute to the grand, soothing flow. Their mysteries, how they synchronize blooms across oceans, guided by unseen cues of tide and temperature, offering a philosophical nudge toward trust in life's interconnected rhythms, where your own evening unwind is but one thread in the tapestry. Let that sink in now, like sunlight filtering through leaves. Let this surface serenity draw us a touch further into the realm of floating forests that bob like dream catchers on the waves, places where the ocean's mysteries take root not in soil, but in the sway of currents, cradling lives that seem plucked from fable. Foremost among these is the Sargasso Sea, a tranquil basin in the midst of the Atlantic, bounded not by land but by swirling gyres, those vast, circling flows of water, like a slow-motion carousel spun by wind and earth's gentle spin, gathering flotsam and dreams into a central calm. Here, golden sargassum weeds tangle into a buoyant jungle, their fronds waving lazily like banners in a breeze that never quite arrives, providing nurseries for baby sea turtles who hatch unseen and paddle toward this haven, and way stations for eels embarking on migrations as epic and enigmatic as any hero's quest. These slender serpents, born in the deep Sargasso cradle, slip away as glassy larvae, transparent as forgotten thoughts, to journey across oceans for years before returning, drawn by some internal compass we can only marvel at, a homing instinct woven into their very scales. The wonder of it all lies in the patience required. The eel's odyssey spans a decade, a lifetime in human terms, yet unfolds with the serene inevitability of seasons turning, mirroring how our own paths, though winding, lead inexorably toward rest. And in contemplating this, a subtle reassurance emerges that mysteries like these are not puzzles to solve but companions to carry into sleep. their unresolved grace a balm for the soul's quiet corners, just as the tides teach us to accept the pull and release. Drifting alongside these seaweed realms are the ocean's nomadic islands of plastic and driftwood, gentle reminders of our own hand in the sea's story. Yet even here, nature weaves redemption. Barnacles and bryozoans, those tiny architects, like patient decorators, claim these wanderers as homes, transforming refuse into reefs adrift, where fish dart in exploratory schools, their silver bodies flashing like punctuation in an unfinished sentence. This interconnected web, from weed to wreckage, illustrates the ocean's forgiving philosophy, how it gathers and reshapes what comes its way, much as a good night's rest gathers the fragments of the day into coherent piece. And if you've ever watched debris bob on a river or tide pool, you'll sense that shared pulse, the way the water holds without judgment, inviting us to do the same for our wandering minds. As sunlight filters through this floating mosaic, it casts elongated shadows that sway like pendulums, marking time in a clockwork of currents too slow for urgency, each gyre a chapter in the sea's endless narrative, where the mystery of their formation, born from the Coriolis effect, that subtle deflection due to Earth's rotation, like a dancer's spin influencing the whole troupe, becomes less a riddle than a revelation, underscoring the planet's harmonious spin, a grand waltz that lulls us all toward equilibrium. Let that turn gently now, like a leaf in the breeze. Now, as the light begins to soften toward afternoon's golden haze, consider the tides themselves, those majestic ebbs and flows that sculpt coastlines with the patience of poets etching verse, rising and falling in obedience to the moon's distant pull. A gravitational conversation across void and water that spans the globe in synchronized swells. Twice daily, this tidal ballet lifts the sea's skirt to reveal hidden worlds, mudflats alive with burrowing clams that squelch like secrets unearthed, rock pools cradling anemones in their pastel grasp. Each a microcosm of resilience where the incoming rush deposits nutrients like gifts from the deep, fostering blooms of life that thrive in the brief window of exposure. The moon, our silvery nightlight in the sky, exerts this influence through gravity's tender tug, creating bulges in the ocean's skin that chase each other around the earth, a phenomenon explained simply as the water's response to celestial embrace, yet laced with enigma in places like the Bay of Fundy, where tides climb 30 feet or more, transforming narrow inlets into thundering cataracts one moment and tranquil mirrors the next. In their predictability laced with power, tides offer a reassuring metaphor for sleep's own cycles, the slow build of drowsiness, the peak of surrender, the gentle recede into morning, reminding us that even the wildest forces operate in cycles of care, inviting a philosophical drift toward acceptance, where the ocean's rhythms become our own, washing away the residue of wakeful striving, just as the earlier waves sync with our breaths to guide us deeper. From these tidal whispers, our thoughts lap toward the wind's role in the surface symphony, those breezes that skim the waves like fingers trailing over silk, birthing white caps that froth and fade in effervescent brevity, each one a fleeting sculpture born of friction between air and water, carrying scents of salt and distant storms to mingle with the shore's earthy breath. Winds, shaped by temperature gradients across the globe, warm air rising like a sigh, cool air rushing to fill the void, pattern the ocean into trade winds and westerlies, steady companions that propel sails and seed clouds, yet harbor mysteries in their sudden shifts, like the doldrums, those becalmed belts near the equator where sailors once languished, staring into glassy stillness that mirrored their inner calms or tempests. Here, in the absence of motion, the sea reveals its meditative core, a vast plate of blue holding the sky's reflection like a promise kept, and in that stillness, subtle currents stir beneath, invisible rivers that transport warmth from tropics to poles, balancing the planet's fevers with cool deliberation. This thermohaline circulation, often likened to a global conveyor belt driven by heat and salt's density dances, underscores the ocean's role as Earth's thermostat, a quiet guardian whose enigmas, how it might shift with warming airs, altering rain patterns far inland, invite not alarm but awe at its enduring poise, much as a deep breath steadies the heart before sleep claims it. Winds whisper. They stir. They balance. As these surface tales intertwine, painting the ocean as a canvas of calm motion, we glimpse the first hints of what lies beneath. The way waves, in their endless march, sometimes curl into rogue forms, solitary giants that rise without warning, born from constructive interference, where swells from varied storms align their crests like synchronized swimmers, amplifying height and force into something momentarily majestic. These rogues, towering to 100 feet in rare fury, have been chronicled by mariners as harbingers of humility, yet in retelling, they become emblems of the sea's wild poetry, reminding us that even in repose, nature holds depths of surprise, much like the subconscious stirrings that flavor our dreams. And yet, for every dramatic swell, there are countless microwaves, capillary ripples too fine to see but felt in the skin's prickle, generated by the merest zephyr, illustrating the fractal beauty of the sea, patterns repeating from grand to infinitesimal, a philosophical echo of how small worries, when viewed from afar, dissolve into the greater flow. In this layered dance, the ocean teaches surrender, its surface a gateway to the profound hush below, where light fades and imagination awakens. Let that fractal unfold now, small to vast. Let us linger a moment on the foam itself, that bridal veil of bubbles born when air entrains into wave crests, collapsing in iridescent pops that release a fresh, ozone-kissed scent, a natural perfume distilled from chaos into clarity, each bubble a tiny universe, its skin a thin film of water molecules stretched taut, reflecting rainbows in prismatic promise before bursting back to the whole, a cycle as poignant as a sigh released. This effervescence, laced with organic whispers from planktonic feasts, carries the sea's voice to our nostrils, evoking memories of childhood paddles or stormy walks, those shared human threads that bind us to the blue, and in its transience, foam embodies the gentle philosophy of letting go, where mysteries like the exact chemistry of its persistence, surface tension's delicate balance, akin to the skin holding a water droplet's shape, serve not to perplex but to poeticize the everyday, turning the act of watching waves into a meditative rite, priming the mind for the velvet descent into slumber. Bubbles rise. They shimmer. They fade. As the sun traces its languid arc, casting the water in amber glows that deepen toward indigo, the surface begins to hush, mirroring the world's winding down, and in that transition, another vignette emerges, the mirages that tease the horizon, those shimmering veils where sea and sky bleed into illusion, born of temperature inversions that bend light like a funhouse mirror, conjuring distant ships hull up or upside down, as if the ocean dreams in reflections. Sailors of old spun yarns from these apparitions, tales of phantom islands or beckoning ghosts, yet science softens them into wonder, refractione Euro TM's playful warp, where warmer air over cooler water curves raise earthward, revealing what's hidden miles away, a natural telescope unveiling the curve of the planet itself. For you, reclining now in the hush of your sanctuary, these optical enigmas offer a reassuring parallel to the mind's own illusions at day's end, those fleeting thoughts that distort then dissolve, leaving clarity in their wake. Imagine drifting towards such a mirage, not in pursuit but in acceptance, letting it blur into the broader blue, a subtle call to release the grasp on certainties. Mirages tease. They reveal. They dissolve. With these illusions fading into the reliable vastness, we turn our gaze to the seabirds that skim the swells, their wings slicing air with effortless grace, dipping to snatch silver flashes from the brine, gulls with cries like laughter muffled by wind, albatrosses gliding on invisible thermals for hours without a flap, masters of the boundary where ocean meets atmosphere. These aerial nomads, attuned to the sea's moods, follow currents rich in forage, their migrations mapping invisible highways across the globe, enigmas in their navigation. How do they sense magnetic fields, like living compasses, or read the stars' subtle script through cloud? In their poised sovereignty, they embody the uplift of freedom within limits, soaring above the waves that buoy them indirectly, a reminder that mysteries elevate rather than ensnare, much as pondering them now lifts the spirit toward serene altitudes, where worries scatter like wake from a passing skiff. Wings lift. They glide. They return. Yet even these sky-dwellers hint at the depth's pull, for their prey often rises from below, schooling fish that breach in acrobatic leaps, arcs of muscle and scale catching light in midair, a burst of life against the monotone blue. These leaps, propelled by lateral lines, sensory canals along their sides, like underwater whiskers attuned to pressure waves, serve escapes from shadows beneath or joyful communications, their synchronized ballets evoking the ocean's hidden choreography, where surface vivacity is but the overture to submerged symphonies. In witnessing such moments, perhaps from memory of a pier or beach, feel the shared thrill tempered by calm, the way the sea orchestrates without fanfare, inviting us to harmonize in our own quiet way, breaths deepening as the narrative unfolds. Leaps arc. They flash. They submerge. As twilight's fingers brush the waves, turning crests to molten silver, the ocean's surface yields one more gift, the phosphorescence that awakens in stirred waters, a soft glow from disturbed plankton, dinoflagellates, those spinning specks that ignite in chemical courtesy when waves jostle them, like stars shaken from a blanket, trailing comet tails in the wake of oars or dolphins' leaps. This bioluminescence, a gentle term for living light crafted from luciferin and oxygen's spark within the cell, transforms night swims into milky constellations, a mystery rooted in defense or allure, yet universally soothing in its ethereal hush, evoking fireflies over meadows or city lights from a hilltop view. Here, at the cusp of dark, it bridges surface and shadow, a luminous threshold that reassures, even as light wanes, wonder persists, a philosophical lantern guiding toward the profound unknowns below, where greater glows await. Glows awaken. They trail. They bridge. And so, as the surface whispers its secrets in waves and glows, in drifts and dances that cradle the world in ceaseless care, what gentle currents might carry us deeper into the blue, where twilight zones bloom with lanterns of their own? Imagine drifting further now, layer by layer, into the sea's embracing arms, each revelation a step toward that peaceful discovery where sleep and mystery entwine like kelp in the tide. Those gentle currents, soft as the sigh of forgotten lullabies, begin their subtle guidance just beneath the skin of the sea, where the shallows unfold like pages in an open book, inviting us to linger in realms where light still reigns but begins to share its throne with shadow, a transition as natural as breath deepening into evening's hush. Here, in these sun-dappled fringes where water kisses the continental shelves, those broad, submerged plateaus extending from land like welcoming arms, life clusters in vibrant tapestries that pulse with the quiet energy of creation, reminding us through their gentle bustle that the ocean's mysteries are not solitary enigmas but woven communities, each thread a story of adaptation and grace that echoes the interconnected rhythms of our own resting forms. As you allow your thoughts to settle into this liminal glow, feel the reassurance of these shallows. They are the sea's threshold, a place of emergence where the raw pulse of the deep tempers into something approachable, like the first stars pricking the dusk sky, offering points of light to navigate by without overwhelming the gathering dark. Let that threshold open now, like a door to a familiar room. Drifting now into the embrace of coral realms, envision the Great Barrier Reefs that fringe tropical coasts like living jewelry, vast structures built not by stone but by the patient labor of polyps, tiny, flower-like builders, cousins to jellyfish, that secrete calcium homes in slow, accretive devotion, layer upon layer over millennia, forming underwater cities that rival the grandeur of ancient ruins, yet breathe with the subtlety of a garden in bloom. These reefs, the largest living things on Earth, stretching for thousands of miles off Australia's edge, harbor a symphony of colors and forms, branching staghorns like antlers caught in eternal freeze-frame, brain corals ridged as convoluted thoughts, and tabletops flat as forgotten altars, all awash in schools of fish that weave through the lattice like threads in a loom, their scales flashing turquoise and crimson in the filtered sun. The wonder here lies in the symbiosis that sustains them, a gentle pact where zooxanthellae, microscopic algae living within the coral's tissues, like friendly roommates sharing sunlight for a cozy home, trade the sun's captured energy for shelter, their photosynthetic dance turning barren skeletons into riotous life, a ripple effect that feeds predators and prey alike. From nibbling parrotfish grinding rubble into sand to majestic manta rays gliding overhead like shadows of contentment. In this balanced exchange, much as a deep inhale nourishes the body toward repose, the reefs teach a philosophical serenity, that strength blooms from partnership, inviting you to reflect on how your own evening unwind draws from unseen supports, the quiet alliances of breath and heartbeat that cradle you towards sleep, just as the tides earlier pulled us toward acceptance. Let that partnership breathe now, shared and steady. Yet even as these coral citadels thrive in the shallow's embrace, they whisper of vulnerabilities that add depth to their allure, for rising warmth in the surrounding waters, subtle shifts in ocean temperatures, like a blanket grown too heavy, can prompt bleaching, where the coral evicts its algal partners in a pale protest, standing skeletal and stark until cooler currents restore the bond, a cycle of loss and renewal that mirrors the ebb of worries in a fretful mind, reminding us that resilience is not absence of change but the capacity to mend, softly and without fanfare. Imagine paddling above such a recovering reef, the water clear as thought, where the first green tinges return like hope's tentative buds, and in that vision, a reassuring uplift emerges. These shallows, for all their fragility, endure as cradles of biodiversity, home to a quarter of marine species in waters no deeper than a dive bell's reach. Their mysteries, how they engineer ecosystems from mere minerals, fostering a sense of empowered wonder, as if the sea confides that even in our most tender states, creation persists, layer by gentle layer. Colors fade. They mend. They return. From the reef's structured splendor, our drift carries us toward the open shallows where currents weave more freely, those invisible rivers within the sea that sculpt the surface into patterns of serene chaos, like eddies in a stream that tangle leaves into lazy spirals, gathering and releasing with impartial calm. These ocean eddies, born where swift flows meet obstacles or meander in their paths, much like the twist of bedsheets in a restless night, coiling around the form they hold, can span miles, trapping nutrients and drifters in rotating arms that spin clockwise or counter in obedience to Earth's gentle spin, creating ephemeral oases amid the vast blue. Scientists track them via altimetry, gentle measurements from satellites that gauge sea height subtle swells, revealing how these vortices, often 10 kilometers wide and lasting weeks, ferry warmth or cold across basins, influencing whether far ashore in ripples too faint for alarm but profound in their reach. Picture one now, a slow whirl off the Gulf Stream's edge, where sargassum fronds circle like dancers in a ring, drawing in larval fish that mistake the gyre for home, a natural nursery spun from motion alone. In their unhurried turn, eddies offer a meditative analogy to the mind's own swirls at day's end, those circling thoughts that, given space, resolve into clarity, inviting a soft repetition. Let them turn, let them gather, and in time, they release, carrying forward only what serves the greater flow. Let that whirl settle now, like leaves in still water. Interwoven with these eddies are the grander gyres that command the ocean's basins, those planetary scale circulations where trade winds and westerlies conspire with Earth's spin to form clockwise carousels in the subtropics, counterclockwise in the north, vast loops that encircle like patient guardians, collecting the sea's flotsam into central calms. The North Pacific Gyre, for instance, a sprawling vortex twice Texas's size, draws plastics and twigs from distant rivers, amassing them in the Great Pacific Garbage Patch, not a solid island but a soupy mosaic, where debris fragments into microbits that mimic plankton, fooling filter feeders into unwitting meals. Yet even here, the gyre's philosophy shines through adaptation. Barnacles encrust the wanderers, turning trash into habitats, and seabirds nestle amid the tangle, their webs of life persisting in quiet defiance. This gathering, explained simply as the Coriolis forces deflection, like kids twirling on a playground merry-go-round, nudging riders outward, connects hemispheres in unseen threads, ferrying heat from equator to poles, moderating climates with a thermostat's steady hand, and as you contemplate this global embrace, feel the serenity of belonging to such a web, where your own drift into rest is echoed in the current's impartial hold, a reminder that mysteries of scale, from the eddy's curl to the gyre's sweep, unite us all in harmonious motion, just as the earlier winds balanced the surface's stir. Loops encircle. They gather. They connect. Let this circling grace lead us to the floating worlds they cradle, expansions of the Sargasso's whisper into other nomadic havens where the sea's surface becomes a canvas for emergent ecosystems, untethered and adrift like thoughts freed from anchor. Beyond the Atlantic's golden meadows lies the ephemeral raft of the Southern Ocean, where Antarctic krill swarm in clouds billions strong, their bioluminescent pulses, soft chemical glows akin to underwater fireflies, lighting the underbelly of ice floes that carve and drift northward, carrying penguin colonies on seasonal voyages, each berg a mobile arc sculpted by wind and wave into fantastical shapes, arches and spires that melt into the brine over months, releasing freshwater kisses to warmer climes. These ice islands, born from glacial tongues that creep seaward like slow exhalations, harbor mysteries in their stratified layers, blue veins of ancient air bubbles trapped millennia ago, whispering of climates passed through isotopes, those atomic fingerprints that scientists read like diaries in ice cores, revealing how the ocean's drifts have buffered Earth's fevers since the last ice age. In their majestic passage, much as a deep breath carries tension away, these flows invite philosophical reflection. What burdens do they bear for us, these silent couriers, and in their dissolution, what renewal do they promise, fostering a quiet empowerment to release our own held weights into the flow? Let that passage melt now, slow and renewing. Shifting with the subtlety of a tide's turn, consider the kelp forests that fringe colder shallows, towering canopies of brown algae that sway like underwater bamboo groves, reaching 40 meters from seafloor to surface in California's Monterey Bay, where holdfasts grip rocky beds with root-like tenacity, and fronds unfurl in current-kissed ballets, providing corridors for sea otters to twirl in playful hunts, cracking urchins on stones like nuts in a velvet pouch. These kelp realms, ecosystems unto themselves, teem with the hush of hidden lives, abalone grazing in shadowed nooks, wolf eels coiling in lairs woven from detritus, and Garibaldi fish patrolling neon territories, their orange flash a punctuation in the green gloom, the mystery of their rapid growth, up to 0.5 meter a day, fueled by nutrient upwellings that bubble cold waters to the sun, lies in a carbon sponge's devotion, absorbing CO2 like a forest sigh, yet vulnerable to warming's unraveling, where warmer seas stunt the blades, a gentle warning echoed in everyday wilts of garden greens under summer's gaze, yet reminding us, as the tides did, that even in change's pull, new growth waits in the current's turn. Here, In the kelp's rhythmic undulation, repetition finds its place, sway and hold, release and grasp, a cadence that soothes the senses, drawing parallels to the body's own tidal unwind, where each breath mirrors the frond's flex, empowering a sense of fluid strength amid flux. Sway gently, hold steady, release soft. As light filters through these verdant veils, casting dappled mosaics on the sand below, another vignette emerges from the shallow's palette, the seagrass meadows that carpet bays and estuaries like submerged lawns, their blade-like leaves flowing in shallow currents, oxygenating the water through photosynthesis that rivals rainforests per acre, roots stabilizing sediments against erosion's whisper, creating nurseries where juvenile fish, hammerheads wheeling in miniature pods, seahorses clinging to stems like living ornaments, find sanctuary from the open sea's vastness. These meadows, often called the ocean's kidneys for their filtration of murky inflows, harbor enigmas in their pollination, underwater flowers releasing pollen on buoyant grains that drift with the tide, a reproductive drift as improbable as dandelion seeds on wind, ensuring genetic mingling across fragmented beds. And in their quiet industry, much like the unsung labor of sleep's repair, they purify and propagate, their decline in warming bays a poignant call to cherish the subtle workers, yet their persistence a uplifting testament to nature's resilient weave, inviting you to envision lying amid such a meadow, weightless and held, as worries filter away like silt in the current. Blades flow, roots hold, sanctuary blooms. From these rooted drifts, our path meanders to the pelagic wanderers, those true nomads of the shallows where surface and midwater blur, the loggerhead turtles that navigate gyre-bound routes, their ancient shells etched with barnacle maps of journeys spanning hemispheres, hatching on moonlit sands to paddle instinctively seaward, drawn by magnetic inclinations, like an inner needle pointing to natal beaches after decades adrift, a homing etched in neural clay we scarcely comprehend. These voyages, tracked by satellite tags that relay faint pings across oceans, reveal circuits synced to jellyfish blooms, those gelatinous drifters pulsing like inverted umbrellas, their sting a veiled defense in the food web's chain, where turtles harvest them with leathery indifference, recycling the sea's plastic mimics that fool the eye but not the gut. In the turtle's patient arc, a philosophical serenity unfolds. What compels such fidelity to origin, amid endless blue, but the same quiet pull that draws us back to rest's familiar shore, reinforcing through repetition the theme of circuits closed in grace, where migration's mystery becomes a metaphor for the soul's return, serene and unhurried. Paths arc. They return. They grace. Let the turtles glide inspire a pause, a moment to reflect on how these shallow symphonies connect not just lives but lands, for the currents that bear them northward carry seeds and spores, fertilizing distant coasts with tropical largesse, or southward with polar chills, a global exchange that tempers extremes into habitable means, as seen in the Augustus current's warm leak into the Atlantic, seeding hurricanes or soothing droughts in butterfly ripples of climate's dance. This interconnected drift, explained in terms of Ekman transport, the wind's surface shear that veers water 90 degrees from intent, like a leaf skewed in breeze, underscores the ocean's role as planetary mediator, its enigmas in predicting leaks or leaks' effects a call to humble wonder rather than haste, fostering empowerment in the knowledge that we, too, are born by such flows, our evenings a node in the greater calm, just as the gyre's earlier united scales in harmonious motion. Let that exchange ripple now, far and connecting. As sunlight softens toward the horizon's amber hush, filtering through the shallows in elongated rays that gild the drifting worlds below, the play of light evolves once more, now dappling the water column with caustics, those shifting mosaics of brightness and shade, like sunlight through a bottle's curve, dancing across kelp and coral in hypnotic patterns that guide plankton toward the glow, a natural spotlight in the theater of life. These beams, bent by refraction at the surface's undulating lens, create safe havens from predators in the flicker, where shrimp and copepods, tiny crustacean sprites, dart in evasive ballets, their world a strobe of sanctuary, the sensory immersion here, evoking the prickle of light on closed lids, invites a rhetorical whisper, what quieter illuminations might we seek in our own shadowed thoughts, allowing the shallows dance to mirror the mind's gradual unclenching? In this luminous interplay, repetition of light's gift reinforces the theme, it reveals, it conceals, it sustains, a poetic flourish that ties the vignettes into wholeness. Light dapples. It guides. It shelters. Yet as the day wanes, these shallows yield their brightest secrets to the encroaching twilight, where the water holds its breath in anticipation, the golden haze deepening to sapphire veils that hint at the profounder hush below, and in that suspended breath, a subtle irony touches the scene. The very light that animated the drifts now fades, not in loss but in invitation, drawing the eye and the imagination toward realms where shadows bloom into living lights, those bioluminescent whispers that turn the dusk into a canvas of gentle sparks. Imagine, then, the transition as a velvet curtain parting slowly, each fading ray a cue to lean into the unknown, where the sea's floating worlds give way to twilight's lanterns, their glow a bridge to deeper serenities, fostering that peaceful discovery where curiosity and repose entwine, much as the last light merges with the first stars. And so, with the shallows' gifts lingering like echoes in the mind, what soft illuminations might await in the gathering blue, ready to cradle your drifting thoughts further still? Those soft illuminations, emerging like timid stars from the twilight's deepening fold, reveal themselves in the ocean's mesopelagic zone, that vast, crepuscular realm between 200 and 1,000 meters deep, where sunlight surrenders its last whispers to an eternal dusky blue, a place as liminal as the moment between wakefulness and dream, where the water's embrace grows cooler and more intimate, cradling forms adapted to a world of subtle gradients and profound quiet. Here, in this twilight expanse that envelops the globe like a silken shroud, bioluminescence blooms not as spectacle but as necessity, a living light woven from chemical poetry within the very tissues of its bearers, turning the void into a canvas of gentle flickers that speak of resilience and hidden kinship, much as the faint glow of a bedside lamp invites the eye to linger without strain. As you allow your imagination to descend with these currents, feel the reassurance of this zone. It is the sea's transitional hymn, where darkness is not absence but a canvas for creation, each spark a reminder that even in obscurity, wonder persists, softly illuminating the path toward deeper repose. Let that hush settle now, like dusk on a quiet lake. Envision first the jellyfish that drift through these shadowed waters, their bells pulsing with the unhurried rhythm of a slowing heart, translucent orbs that contract and expand like breaths drawn in velvet silence, propelling them upward in nightly migrations that span hundreds of meters, a vertical odyssey synced to the sun's unseen arc. These ethereal wanderers, from the luminous moon jelly with its four-lobed glow to the deeper dwelling helmet jellies crowned in crimson veils, harness bioluminescence through proteins called equorins, simple molecules that, when stirred by calcium's touch within the cell, release blue-green photons in a cascade akin to a firework's quiet unraveling in the night sky, or the quiet pop of a glow stick cracked in a dark room, turning chemistry into a soft, steady shine that lasts just long enough, a light born not of fire but of life's intimate alchemy. This glow serves as both beacon and veil, luring prey with false promises of planktonic feasts or startling predators with explosive bursts, flashes that ripple outward like ripples from a pebble in a still pond, scattering threats into the gloom. And if you've ever watched fireflies weave their Morse code across a summer meadow, or city lights pulse from a distant skyline at dusk, you'll sense that shared poetry, the way these jellies transform isolation into communion, their trails etching temporary constellations that foster a philosophical serenity. In the vast alone, connection flickers eternal, much as your own thoughts, adrift in evening's hush, find solace in remembered gleams. Let that cascade glow now, soft and inviting. From the jelly's nomadic grace, our descent lingers on the siphonophores, those colonial ghosts that masquerade as single entities but unfold as floating cities of specialized polyps, each tendril a dedicated artisan in the symphony of survival, trailing silken nets that snare copepods and krill in unsuspecting drifts. Among them, the Portuguese man-o'-war's deep-sea kin deploy bioluminescent lures like dangling jewels, their blue sparks, photons sparked by luciferin oxidizing in the presence of luciferase, an enzyme that acts as nature's gentle match, drawing in the curious with hypnotic pulses, only to ensnare in nematocyst barbs that fire like whispered accusations, tiny harpoon-like stingers injecting venom that paralyzes in seconds. Yet in this predation lies no cruelty but elegant economy, a ripple effect that recycles the twilight's bounty upward to surface feeders and downward to scavengers, sustaining the food web's delicate poise. Picture one now, a chain of light undulating through the blue-black, its glow a subtle irony, beauty as both invitation and trap, echoing how the mind, in quiet reflection, ensnares distractions to release them transformed, inviting an uplifting pause. What hidden lures might your own depths hold, ready to illuminate paths long overlooked? Let that chain undulate now, pulsing in the quiet. Interwoven with these drifters are the squid that claim the twilight as their canvas, masters of ink and illusion whose mantles shimmer with chromatophores, pigment cells that expand and contract like living pixels, blending camouflage with covert signals, yet it is their photophores, those embedded light organs lining the body like a constellation's map, that truly enchant, emitting synchronized flashes in codes we can only intuit, perhaps mating dances or schooling cues passed in the dark. The Hawaiian bobtail squid, for instance, hosts symbiotic bacteria in its light organ, a ventral glow that mimics moonlight filtering from above, erasing the silhouette's shadow to full watchful eyes below, a mutualism where the microbes thrive in nutrient-rich haven while gifting the squid invisibility's cloak. This bacterial bioluminescence, a bacterial luciferase igniting the same luciferin spark, unfolds as a nightly ritual, the squid expelling most guests at dawn to reset the colony, a cycle of hospitality and renewal that mirrors the body's own nocturnal housekeeping, purging the day's debris and sleep's gentle tide. In their elusive artistry, squid embody the zone's empowering whisper, adaptability as artistry, where light becomes both shield and signature, fostering quiet insight into how our vulnerabilities, when tended, bloom into strengths that navigate the unseen. Let that chemical poetry simmer now, a quiet spark in the dark. As these lights weave their subtle web, consider the hatchetfish that slice the midwaters with asymmetric bodies, their upturned eyes scanning the gloom like vigilant sentinels, ventral photophores arrayed in rows that emit a downward beam to match the faint blue penetration from above, a counter-illumination that renders them ghosts amid the blue, invisible to the hunt below. These silver slivers, named for their blade-like profiles, descend by day and ascend at night in the largest animal migration on Earth, trillions strong, a silent exodus that pumps carbon to depths, sequestering it from the air in oceanic vaults, their glow a vigilant adaptation, tuned to the spectrum's edge where blue dominates, like city dwellers blending into neon haze. The mystery here, laced with wonder, lies in the precision of this mimicry. How do they calibrate intensity to the variable veil of surface light, a neural artistry we glimpse through submersible eyes, yet one that reassures through its ingenuity, turning potential peril into poised evasion, much as a deep breath in uncertainty steadies the soul. Repetition in their nightly rise a rhythmic affirmation of endurance's grace. Beams match. They hide. They rise. Let this ascent's echo draw us to the lanternfish, those myriads of midwater minnows whose flanks sparkle with an orchestra of lights, photophores dotting like freckles on a twilight sky, flashing in patterns that school them into protective clouds, baffling predators with a disco of distraction. Numbering perhaps 10,000 species, they form the mesopelagic's backbone, their upwellings at dusk fertilizing surface blooms in nutrient rain, a vertical ferry that connects realms in unseen reciprocity. Each flash, a brief enzymatic burst, serves communication's hush, perhaps warnings of approaching shadows or invitations to kin, evoking the firework displays of holiday nights, where bursts of color unite the gathered in shared awe. In their collective shimmer, a gently philosophical thread emerges, individuality yields to harmony, lights merging into a greater glow that sustains the whole, inviting you to reflect on how your own evening solitude, dotted with memory sparks, contributes to an inner constellation, serene and self-sustaining. Flashes school. They baffle. They unite. Shifting with the subtlety of a fading ember, the twilight zone reveals its anglers, those patient architects of allure whose dorsal spines bear escalures, fleshy beacons tipped with bacterial glow, dangling like fisherman's bait in the void, pulsing with rhythmic enticement to mimic copepod twitches. The frogfish, squat and fringed like a deep-sea friar, or the dragonfish with fangs curved in predatory prayer, wait motionless for hours, their lures light a chemical siren call, luciferin luciferase duet drawing the unwary into jaws agape, this bioluminescence, often bacterial symbiosis where the host provides sugars for the tenant's spark, underscores the zone's quiet drama, predation as performance, where the hunter's patience mirrors the prey's fleeting trust, a balance that ripples through the ecosystem, ensuring no excess dominates the hush. Imagine one such vigil now, the lure's blue pulse the only motion in ink, a relatable vigil akin to awaiting dawn's first light from a window seat, and in that parallel, empowerment stirs, mysteries of motive, whether lure or lesson, teach that waiting, too, is a form of luminous presence, turning stillness into strategy. Lures dangle. They pulse. They wait. Yet not all lights serve the hunt, some whisper alliance, as in the flashlight fish of Indo-Pacific depths, whose subocular pouches house symbiotic bacteria that flare on demand, lids like built-in shutters modulating the beam for schooling signals or startling escapes, a glow ventrally directed to scan the seafloor for crustacean morsels. These pouches, refilled nightly with fresh microbes from surrounding waters, pulse in codes that bind the shoal, much like neighbors' porch lights flickering welcome across a quiet street. The enzymatic magic here, a luciferase variant tuned to green hues for deeper penetration, evokes the Aurora's shy dance, fostering awe at evolution's palette. How light, borrowed from unseen partners, forges bonds in isolation, a reassuring motif that echoes in human gatherings, where shared glances illuminate the unspoken. Beams flare. They signal. They bind. As vignettes of glow accumulate like fireflies in a jar, consider the comb jellies that ribbon the twilight with iridescent rows of cilia, combs refracting ambient light into rainbow shimmers, augmented by true bioluminescence in stressed bursts, milky trails that deter or dazzle, their gelatinous forms collapsing and reforming with amoebic fluidity, 80% water yet harboring the sea's quiet might. These ctenophores, often mistaken for jelly-kin but propelled by or like beats rather than jet pulses, filter plankton in voracious grace, their light's a secondary defense, sparked by photoproteins that release energy sans oxygen, a anaerobic elegance suited to low oxygen layers, much like the quiet pop of a glow stick in a stuffy room. In their prismatic drift, a subtle observational touch arises, the irony of being so fragile yet so radiant, mirroring how our own vulnerabilities, when expressed, draw empathy's gentle orbit, inviting a rhetorical pause. What inner rainbows might flicker in your twilight thoughts, ready to refract the day's dim into dream's spectrum? Rainbows refract. Trails dazzle. Defenses weave. Repetition finds its rhythm in the zone's pervasive blue, the dominant wavelength that penetrates deepest, shaping all illuminations to its hue, a spectral signature that unites disparate glows in harmonious understatement, like a chorus tuned to one key, ensuring signals travel farthest in the murk. This monochromatic mandate, born of water's selective absorption, reds fading first, blues lingering like loyal echoes, philosophically underscores unity in diversity, myriad forms, one light, a serene reminder that beneath surface variances, shared essence binds, much as breaths align in a room of sleepers, fostering interconnected calm. Blues linger. They unite. They bind. From these communal sparks, our gaze turns to solitary enigmas, the vampire squid that cloak the oxygen minimum layers with webbed arms fringed in fleshy sails, their bioluminescent pearls, photocytes lining the skin that eject in defensive clouds, mimicking a larger threat to confound pursuers. Not true vampires but detritivores sifting marine snow, organic flakes drifting from above like manna in the void, their glow, a photoprotein flash sans ongoing fuel, serves escapes poetry, arms curling inward to cloak the body in living shadow. This adaptation, to a realm where oxygen dips perilously low, evokes the hush of high-altitude nights, where thin air sharpens the stars, and in their veiled retreat, uplift blooms, even in scarcity. Invention thrives, lights as life's defiant poetry, empowering the spirit to find luminescence in lean times. Pearls eject. They mimic. They cloak. Let the squid's retreat inspire a sensory immersion, the faint chemical scent of luciferin imagined as ozone after rain, a crispness that clears the mind, while the visual of ejected gleams, fleeting orbs tumbling into dark, mirrors fireflies released from cupped hands, a gesture of release that soothes. Here, in the twilight's lantern-lit hush, another layer unfolds, the deep-sea shrimp that snap claws to spark cavitation bubbles, implosions yielding sonoluminescent flashes, a mechanical light born of pressure's collapse, like thunder's visual twin, startling foes with acoustic visual 1-2. This pistol shrimp's trick, amplified in pairs for burrowing duets, highlights the zone's ingenuity, light from sound, motion from stillness, a ripple that connects physics' whisper to biology's song, reassuring in its multiplicity, wonders compound, each discovery a doorway to more. Snaps spark. Bubbles burst. Wonders compound. As these illuminations interplay, building a nocturnal economy where light begets life in cascading chains, from lure to catch, flash to flock, the twilight zone emerges as the ocean's resilient heart, its bioluminescent ballet a testament to hidden vigor, turning potential void into veiled vitality. Yet even as sparks dance and fade, a gradual dimming invites further yield. These fleeting gleams, so vital in their vigil, give way to the profound hush below, where silence cradles the ocean's most ancient guardians, forms sculpted by unrelenting embrace into embodiments of quiet endurance. Imagine descending now a velvet staircase, step by hushed step, into realms where light's legacy lingers not in flash but in form, adaptations that whisper of survival's serene art, ready to enfold your contemplations deeper still, where the blue yields to black and mysteries deepen like dreams unspooling in the night. That profound hush, enveloping like the softest down quilt drawn over the world's weary edges, welcomes us into the abyssal plains and trenches where the ocean's ancient guardians dwell, realms below 4,000 meters where light's memory fades to an absolute, starless black, and the water's weight presses with the steady insistence of time itself, shaping existence into forms of exquisite economy and unspoken poise. Here, in the bathypelagic and hadal zones, those deepest folds of the sea, cradling 90% of the ocean's volume yet explored by humanity in slivers thinner than a whisper. The pressure mounts to hundreds of times that of the surface, a hydrostatic embrace explained simply as the cumulative hug of water molecules stacked mile upon mile, compressing gases and fluids into denser harmonies, much like the gentle squeeze of a loved one's hand that steadies the fluttering heart. As you envision this descent, feel the serenity of such unyielding care. It is not a crush but a forge, molding life into resilient transparencies and gelatinous graces that remind us, in our own cocooned rests, how constraint can birth profound freedom, each adaptation a quiet testament to the sea's philosophy of endurance without complaint, inviting your thoughts to settle deeper, layer by yielding layer, into this cradle of calm. Let that forge warm now, steady and shaping. Consider first the Mariana Trench, that sinuous scar in the Pacific's floor plunging nearly 11 kilometers, deeper than Mount Everest towers above the plains, a chasm born from tectonic plates grinding in slow, continental ballets, their subduction swallowing crust like a patient swallow of Earth's restless fire. Within this hadal vestibule, where temperatures hover near freezing and darkness reigns absolute, life persists not in defiance but in delicate accord, with amphipods, scavenging crustaceans the size of a hand, armored in translucent chitin that yields to pressure's mold like clay under a sculptor's palm, scuttling across sediments in opportunistic feasts, their bodies bloated with lipids for buoyancy in the brine, a fatty float akin to the insulating warmth of a winter blanket drawn close. These tiny nomads, thriving where land dwellers would shatter, embody the abyss's reassuring irony. What seems inhospitable blooms with vigor, their scavenging webs recycling fallen matter from surface rains, marine snow, those organic flakes drifting like confetti from shallower banquets into sustenance that sustains the deep sparse economy, a ripple effect that connects the sunlit shallows to this lightless larder, fostering a philosophical uplift. In our moments of deepest quiet, do we not, too, draw nourishment from unseen falls, transforming descent into quiet renewal? Let that snow drift now, soft and sustaining. From the trench's echoing vaults, our gaze drifts to the extremophiles that speckle these depths, those microbial marvels, archaea and bacteria, single-celled sentinels smaller than a pinprick, that harness chemosynthesis, a dark alchemy where chemical bonds from vent fluids, rich in hydrogen sulfide, replace sunlight's kiss, forging sugars from the earth's volcanic breath much as a hearth draws warmth from hidden coals. At hydrothermal vents, black smokers spewing mineral-laden plumes like underwater geysers, these pioneers cluster in mats that carpet chimneys of rock, their enzymes, heat-loving proteins that coil and unfold without denaturing, like resilient springs in a forgotten clock, enabling life at 90 degrees Celsius and crushing tons per square inch. a pressure that would pulp our bones yet here molds membranes into flexible fortresses. The wonder lies in their ubiquity, from alkaline seeps mimicking primordial soups to icy brine pockets in seafloor sediments. These microbes underpin entire oases, feeding tube worms that wave crimson plumes like blood-red flags, their sulfur-storing tissues a symbiotic bargain where host and guest trade toxins for nourishment. Imagine them now, invisible architects in the gloom, and sense the empowerment they whisper. In the harshest voids, invention thrives, a gentle reminder that our own inner fortitudes, forged in trials, harbor similar unyielding sparks, ready to illuminate the soul's quieter chambers as sleep approaches, much as the twilight's lanterns above turned void into veiled vitality. Let that alchemy brew now, warm in the dark. Interlaced with these microbial foundations are the larger guardians, like the colossal squid that prowls the southern ocean's ink, its mantle stretching to 14 meters in mythic elongation, eyes the size of dinner plates, the largest in the animal kingdom, globes of gelatinous acuity tuned to detect the faintest bioluminescent flickers from depths where photons are as rare as thoughts in repose. This leviathan, once dismissed as sailor's fancy but affirmed by hooked beaks washed ashore, hunts with arms fringed in rotating hooks that swivel like living barbs, ensnaring prey in a graceful grapple that echoes ancient kraken lore yet grounds in elegant survival, a diet of Patagonian toothfish snatched in ambushes, its body streamlined for jet propulsion bursts, siphoning water through a funnel like a whispered exhale propelling a leaf boat. The mystery of its hunts, glimpsed in rare submersible footage where tentacles unfurl in slow-motion poetry, reveals adaptations to the cold's embrace, antifreeze proteins in the blood that prevent ice crystal blades from piercing cells, tiny bodyguards that latch onto forming ice bits, preventing them from growing sharp, like wrapping fragile gifts in bubble wrap before a freeze, much like the subtle warmth of shared stories thawing winter nights. And in this predator's poised predation, a subtle observational touch arises, the irony of a giant so elusive, mirroring how our deepest strengths often lurk unseen, inviting reflection. What colossal graces might coil within your evening unwind, waiting to extend in quiet command? Hooks swivel. They ensnare. They grace. Let this squid's shadowy ballet draw us toward the giant isopods that scavenge the abyssal plains, those armored isopods, relatives of the pillbug curling in garden soil, but here bloated to 1/2 meter, their segmented shells calcified against the pressure's unremitting press, like knights in forgotten plate mail patrolling silted battlefields. Bathynomus giganteus, with antennae waving like divining rods through the murk, endures months without food in torpid waits, their low metabolism a candle flickering in vast cathedral draughts, oxygen gleaned from sparse currents via gills feathered for maximal harvest. These detritivores, feasting on whale falls, carcasses that sink like manna, seeding oases of bone and blubber where communities bloom in sequenced feasts, from hagfish burrowing in frenzy to later arriving crabs picking remnants, illustrate the deep's patient philosophy, where scarcity hones efficiency into art, a cycle that reassures through its rhythm. Even in famine's hush, abundance circles back, much as rest replenishes the spirit after wakeful labors, repetition in their opportunistic drifts reinforcing the theme of timely grace. Shells armor. They wait. They feast. Shifting with the unhurried flow of thermohaline currents, those deep rivers of cold, salty brine that cascade from polar sinks like slow elevators, carrying oxygen and whispers from surface to abyss, our contemplation turns to the snailfish of the Hadal slopes, translucent ghosts with jelly-like bodies that yield to pressure without brittle fracture, their swim bladders vestigial or absent, replaced by fluid-filled cavities that equalize the crush, allowing undulating glides over trench walls pocked with manganese nodules, those potato-sized concretions accruing minerals over millions of years like Earth's patient savings. Pseudoliparis sway, filmed at 8 kilometers in the Marianas Embrace, lays eggs in gelatinous clusters anchored to rocks, their offspring hatching into miniatures that school in protective veils, feeding on brittle stars and amphipods in a diet of delicate opportunism. The wonder here, laced with everyday kinship, lies in their soft-bellied resilience, bodies 9/10 water, compressible as a sigh, evoking the way we, too, soften under night's blanket, hydrostatic ties becoming metaphors for emotional pliancy, where yielding invites flow rather than fracture, empowering a serene acceptance of life's deeper squeezes. Glides undulate. They yield. They flow. As these forms interconnect in the abyss's sparse tapestry, consider the fangtooth fish that lurks in mid to deep transitions but claims the eternal black as kin, its needle jaws jutting in disproportionate menace, teeth interlocking like a zipper's vigilant guard, piercing prey larger than itself in snaps powered by slow-building muscle twitches suited to low-oxygen realms. Anaplogaster cornuta, with a head bulbous as a lantern unlit, navigates by lateral lines, sensory canals rippling with neuromasts that detect pressure waves like whispers on skin, a sixth sense compensating vision's loss. This diminutive terror, no longer than a handspan yet armed for giants, embodies the deep subtle irony, fierceness in fragility, where bioluminescent lures dangle from Elysium stalks to entice in the void, a bacterial glow mirroring twilight's legacies above, and in their predatory poise, a philosophical nudge emerges, what hidden fangs guard our own tranquil cause, ready to assert in moments of need, yet retract into peaceful repose? Jaws snap. They pierce. They poise. From such vigilant hunters, the narrative meanders to the transparent marvels, like the barrel-eye fish whose dome-skulled cranium, clear as finest glass, exposes tubular eyes swiveling within, scanning upward for silhouettes against faint blue remnants or sideways for lateral frets, an adaptation that turns the head into a periscope for the perpetual night. Macropinna microstoma, drifting in Monterey Canyon's depths, feeds on jellies snared by pipe-like mouths, its ethereal form a ghost in the gloom, pressure-resistant fluids maintaining the dome's integrity like a snow globe untouched by thaw. This optical ingenuity, allowing 360-degree vigilance without turning the body, evokes the mind's own panoramic drifts in meditation, eyes closed yet awareness expansive, fostering uplift in the realization that clarity persists beyond sight's narrow beam, a gentle repetition, see without seeing, endure without strain. Domes scan, eyes swivel, clarity persists. Let the barrel-eye's gaze inspire a pause amid the cold's crystalline hush, where temperatures stabilize at 2 degrees Celsius, a uniform chill that slows metabolisms to crawls, conserving energy in realms where food falls infrequent as shooting stars. Here, the giant amphipods of the trenches balloon with gas-filled sacs for neutral buoyancy, their exoskeletons thin to avoid pressure's brittle kiss, scavenging in packs that echo wolfish loyalties translated to the brine. These Hirondelia higus, with legs jointed for seafloor scrambles, dismantle organic windfalls with mandibles grinding like millstones in the quiet, their communal feasts a ripple-sustaining bacterial blooms on the detritus, interconnecting the macro with micro in life's persistent web. And if you've ever huddled under covers against winter's bite, sharing warmth in silent company, you'll feel that shared human thread, the deep's guardians, in their clustered calms, whispering that solidarity softens the severest colds, inviting a rhetorical breath, in your own enveloping dark. What kinships might gather to guard the hush? Packs settle. They share. They soften. Repetition echoes in the abyss's uniformity, that vast plain carpeted in ooze, calcareous muds and silicious clays accumulating millimeters per millennium. A seafloor diary of planktonic ghosts from eons past, where sea cucumbers inch along like living bellows, their tube feet probing for nutrients in the silt, bodies aversible in stress to expel indigestible loads, a self-cleaning grace suited to the sparse. These holothurians, with respiratory trees branching like coral's memory, oxygenate blood in low ambient flows, their leathery hides laced with Cuverian tubules that tangle predators in sticky webs, a defense as passive as fog's veil. In their languid trails, etched faintly in the sediment before currents erase them, lies a meditative allure, the impermanence of motion in eternity's frame, mirroring how dreams trace paths on the mind's blank canvas, only to dissolve into dawn's renewal, empowering us to embrace the transient as teacher. Trails inch. They probe. They dissolve as vignettes of gelatinous ghosts and armored wanderers accumulate, painting the abyss as a gallery of quiet triumphs. Another sentinel emerges, the zombie worm that bores into sunken whale bones, its acidic secretions, enzymes dissolving calcium phosphate like a slow rain on limestone, tunneling habitats for symbiotic bacteria that chemosynthesize from bone lipids, plumes waving from boreholes like pale feathers in the current. Osidax mucofloris, the bone-eater blooming in crimson clusters on skeletons that sustain life for decades, transforms death's anchor into vitality's perch, a cycle where scavengers yield to colonizers in ecological relay. This osseous oasis, far from vent's fury, underscores the deep's opportunistic heart, life from loss, much as reflection from repose yields insight, and in contemplating these floral drills, a subtle irony touches. What buried bones in our stories might harbor such unexpected gardens, ready to flourish in patient hindsight, turning bone's shadow into a garden's glow, much as the twilight's lanterns above remind us that even in endings, new sparks emerge? Drills bore, plumes wave, gardens bloom. The pressure's loving hug, ever present, sculpts even the eggs and larvae that pepper the deep, from opalescent pearls of deep-sea angler young, hatching with yolk sacs inflated for neutral poise, to the gelatinous clusters of rat-tails, grenadiers with tails tapering like rats, their swim bladders gas-filled yet reinforced against collapse, allowing slope-side drifts where they hoover detritus in vacuum mouths. These coryphenoids, with barbels whiskering the chin like a philosopher's beard, sense chemical trails in the current's faint kiss, navigating to spawning grounds in trench rims. Their adaptations, from slow growth spans of decades to low egg outputs honed for survival's lottery, evoke the long breaths of yogic calm, each cycle a reinforcement, persists softly, and the deep rewards with space to be. Eggs cluster. They hatch. They persist. Yet amid these solitary elegies, communal whispers arise in the abyssal's rare aggregations, like the swarms of copepods, microcrustaceans no larger than rice grains, that pulse in deal migrations, descending to avoid daytime predators only to ascend in nutrient clouds, their exoskeletons laced with antifreeze glycoproteins that bind ice nuclei like merciful chains, tiny bodyguards in the blood that latch onto forming ice bits, preventing them from growing sharp, like wrapping fragile gifts in bubble wrap before a freeze. These fodder for all, from filter-feeding sponges to opportunistic fish, bind the food web in unheralded threads, a ripple that fertilizes the ooze with fecal pellets sinking like mannas in verse. In their trillion-strong tides, a philosophical serenity unfolds. The small, in multitude, sustain the vast, much as fleeting worries, when viewed in life's expanse, nourish growth's greater arc, inviting you to let such swarms soothe the mind's busier currents into harmonious drift. Swarms pulse. They descend. They sustain. As the hush deepens, sensory tapestries reveal themselves beyond sight's eclipse. The elephant seals that dive to 2 kilometers on foraging plunges, their blood rich in myoglobin, oxygen-storing proteins that tint muscles burgundy, like wine deepened in cask, storing extra air in the muscles for the long haul, enduring breath holds of 2 hours, collapsing lung lobes to shunt blood to vitals under pressure's vice, a mammalian foray into the guardian's realm that bridges surface and deep in evolutionary echo. These mirror, surfacing with tails etched in blubber, remind us of apnea's voluntary surrender. The way holding breath in meditation mirrors their plunge, fostering empowerment. What depths might we plumb, in controlled release, to harvest inner abundances? Dives plunge. Breaths hold. Depths harvest. From mammalian visitors, the eternal residents reclaim the narrative with the sea spider's spindly sprawl, pycnogonids with legs elongated to meter spans in polar abysses, their proboscises piercing sponges for fluid sips, bodies reduced to mere frames housing ovaries or stomachs, pressure-tolerant hydraulics pumping hemolymph in slow pulses like a heart at rest. Nymphen, with eggs brooded on the male's frame like jewels in a velvet case, evokes the tenderness of cradled vulnerabilities. Their slow motion lives a counterpoint to shallower hurries, and in this arachnid grace, repetition reinforces, extend, partake, withdraw, a cadence of minimalism that lulls, much as evening's rituals pair the day to essence. Legs extend. They pierce. They brood. Let these extensions inspire a vivid immersion, the faint sulfur tang of vents imagined on the tongue, or the silty whisper against skin in dreams approximation, where the abyss's guardians, from microbial mats to colossal coils, interweave in a symphony sans sound. Their adaptations not mere survivals but celebrations of form's poetry, turning extremity into elegance. In their quiet endurance, then, echoes of our own restful depths emerge, those inner silences where strength simmers unseen, leading us toward the ocean's unsolved songs, faint melodies carried on currents too subtle for haste. These forms, silent yet singing in their poise, prelude the melodies below, where sound takes the stage in the sea's grand hush. Listen closely now, as the water holds its breath and exhales in acoustic veils. What harmonious enigmas might resonate from the profounder blue, inviting your drifting awareness to attune, note by softening note, to the sea's whispered orchestra? Those harmonious enigmas, rising like faint breaths from the profounder blue, unfold in the ocean's acoustic tapestry, where sound travels not as intruder but as intimate messenger, rippling through water's dense embrace, at speeds 4 times that of air, carrying secrets across basins in waves that bend around curves and seep through sediments, a symphony composed in pressures too subtle for sight yet resonant enough to stir the bones. Here, in realms where visibility yields to vibration, the sea confides its unsolved songs through echoes and calls that have puzzled listeners from ancient mariners to modern hydrophonies. Those underwater ears, arrays of microphones strung like pearl necklaces along cables, capturing frequencies from infrasonic rumbles to ultrasonic chirps. Offering not riddles to unravel in haste, but invitations to ponder in peaceful attunement, much as the hush before a melody invites the ear to lean closer, fostering a gentle philosophy. In the unknown's murmur, fear dissolves into curiosity's calm, each tone a thread weaving the listener deeper into the web of wonder, where your own evening quiet might echo these submerged refrains, softening the edges of wakeful striving into dream's receptive flow. Let that murmur rise now, soft and inviting. Envision first the bloop, that enigmatic bellow recorded in 1997 by NOAA's hydrophones across the Pacific's breadth, a low-frequency ultra-low groan spanning 50 seconds, rising and falling like the protracted sigh of some colossal, unseen beast stirring from millennial slumber, its amplitude so vast it drowned out shipping noise for thousands of miles, a sound profile akin to a blue whale's but amplified to orchestral thunder, rumbling at frequencies below 20 Hz that vibrate the chest like distant thunder rolling through a storm-veiled valley. Scientists, poring over spectrograms those colorful maps of sound's anatomy, where pitches paint peaks and valleys once speculated hidden leviathans or seismic whispers, yet gentler explanations emerged, perhaps isoquakes, the cracking of bergs carving from Antarctic shelves, their fractures propagating through ocean waveguides like cracks in a vast pane of glass, channels that funnel low tones with minimal loss, turning geophysical sighs into global murmurs. In this resolution laced with lingering allure, the bloop becomes a reassuring emblem. The ocean's voice, vast yet vulnerable, echoing how our own unspoken depths, when given space, reveal not monsters but the quiet tectonics of release, inviting a reflective pause. What personal bloops, those deep-seated rumbles of unresolved emotion, might find harmony in the listening, transforming tremor into tranquil wave? Let that bellow fade now, echoing into calm. From the bloop's expansive echo, our attunement shifts to the upsweep, another spectral signature chronicled yearly from 1991 in the Pacific's far reaches, a series of 15-second sweeps rising in pitch like a kettle's patient whistle building toward boil, repeating seasonally as if the sea rehearsed its spring arias, detected only by distant arrays too remote for visual corroboration. These ascending tones, climbing from 50 to 200 Hz in harmonic grace, puzzled acousticians until correlations surfaced with underwater volcanoes' subtle stirrings or eurodiatremes venting gas in rhythmic pulses, or fault lines sighing under tectonic tension, their vibrations modulating through water's prism into melodic escalations, much like wind through canyon flutes crafting unforeseen harmonies from stone's unyielding hush. The wonder here lies in the seasonality's subtlety, a cycle tied perhaps to solar-driven currents that flex the seafloor's strings, a ripple effect connecting celestial pools to subterranean songs. And in contemplating this, a subtle irony touches. What we deem anomalous often aligns with nature's patient score, mirroring the way evenings accumulating fatigues crescendo into sleep's resolving chord, empowering us to embrace the sweep not as chaos, but as prelude to peace. Repetition in its annual return, a soothing reinforcement of rhythms beyond our grasp. Tones climb. They rehearse. They align. Interwoven with these grand groans are the intimate choruses of the deep, like the Antarctic's underwater waterfalls or Euro cascades of dense brine sinking from ice shelves, their plunge-churning sediments into turbid plumes that roar at broadband frequencies, a submerged Niagara veiled in cold, where salinity gradients are Euro layers of saltier water heavier than fresh, like oil atop vinegar in a shaken Viala Euro drive the descent, sculpting seafloor canyons over eons in hydrodynamic artistry. These falls, imaged by multi-beam sonars that bounce pings off contours like bats' echolocation in cave cathedrals, reveal ecosystems blooming at their bases, where nutrient avalanches feed chemosynthetic kin to vent communities, tube worms and clams filtering the fallout in symbiotic hush. Picture the sound now. A muffled thunder muffled further by depth's muffler, evoking the rush of a distant shower heard through a closed door, a white noise that lulls rather than startles. And in this auditory veil, philosophical insight blooms, such forceful flows, in their inexorable path, teach surrender's grace, much as we yield to the waterfall of drowsiness, letting heavier thoughts sink away to fertilize clearer dreams. Cascades plunge. They roar. They teach. Let this cascading chorus lead us to the Julia set, those ephemeral sand spirals etched on abyssal plains off Japan, vast geometric mandalas spanning kilometers, captured by RAW cameras in 1990s surveys, their arms radiating like a galaxy's frozen spin. Born not from cosmic whim, but the patient artistry of sea cucumbers depositing radial trails in sediment fans, their tube feet tracing logarithmic curves as they burrow for meals, a natural crop circle sculpted in ooze over days, then erased by currents like chalk drawings on a tidal board. These patterns, analyzed through fractal mathematics, are Euro self-similar geometries where parts echo wholes, akin to fern fronds unfolding in recursive elegancia. Euro whisper of the ocean's innate order amid apparent randomness, a gentle explanation that reframes mystery as mindfulness, where the cucumber's methodical meander mirrors the meditative doodles of a restless hand at bedtime, inviting uplift. In life's unmarked flaws, what intricate designs might our subtle motions inscribe, visible only from afar, fostering a sense of purposeful play and the profound? Spirals trace. They radiate. They whisper. Shifting with the subtlety of a fading overtone, consider the underwater crop circles of shallower sands, those intricate Valentine geometries off Japan's coast, meticulously crafted by male pufferfish in reproductive rituals, their fins sweeping radial furrows over days to form 2-meter mandalas adorned with shell offerings, lures for females drawn by the design's vibrational hum. Through substrate conduction, a euro sound waves traveling bone-like through sand to announce the suitor's labor. These white-spotted puffers, inflating not in threat but deflation in courtship's close, excavate with pectoral precision, each groove a calculated art to channel currents into swirling invitations, a phenomenon unveiled by divers in 2013, transforming folklore's fairy rings into evolutionary poetry. The wonder, laced with relatable charm, lies in the fish's solitary devotion, a euro night spent in ceaseless sculpting, only to court briefly before the tide reclaims the canvas, a euro echoing the quiet crafts of human wooing, like letters folded with care or gardens tended unseen. And in this fleeting architecture, a reassuring motif emerges. Creation's value resides not in permanence but in the act's serene intent, repetition in seasonal redrawings, a rhythmic nod to renewal's gentle cycle. Furrows sweep. They invite. They renew. As these visual symphonies harmonize with sonic veils, our drift encounters the Bermuda Triangle's storied silences, that wedge of Atlantic where compasses falter and vessels vanish, reframed not as vortex of doom but a confluence of magnetic whispers and methane burps, where the agonic linear euro, that wobbly seam where the compass's magnetic north meets true north, like two paths converging in a foggy wood, confusing travelers with a playful twist. A euro confounds navigators with needle spasms, a declination dance explained as the planet's dynamo flux, iron core churning in convective ballets that nudge poles in millennial waltzes. Interlaced as seafloor seeps of frozen gas hydrates, a euromethane cages of water and gas, unstable under pressure's lift, erupting in bubble plumes that slash buoyancy for passing ships, turning steel to sudden sinkers like stones in a bubbling brook. These enigmas, mapped by side-scan sonars that paint seafloor reliefs in grayscale tapestries, invite not dread but awe at the triangle's layered Laria euro, from Columbus noting compass quirks to modern GPS dispelling ghosts, a euro philosophically underscoring how anomalies, when unraveled, reveal the sea's impartial physics, much as bedtime fears, examined in moonlight, dissolve into the ordinary's embrace, empowering tranquil navigation through night's own triangulated unknowns. Lines wobble, bubbles erupt, ghosts dispel. From magnetic murmurs, the narrative undulates toward the quasars of the deeper those high-frequency zips and whines peppering hydrophone logs, like the 52 Hz whale, the ocean's lone crooner whose song pitches above kin's baritone, a falsetto broadcast since 1989 across Pacific expanses, detected by U.S. Navy arrays originally tuned for Soviet subs, its isolation a poignant enigma, perhaps a hybrid of blue and fin, deformed vocal cords straining in ultrasonic solitude, or a last of its kind echoing into void, a call that travels hemispheric hops via sofa channels, a Euro sound fixing and ranging layers where temperature gradients refract tones like prisms bending light, trapping them in deep sound ducts for global relay. This bioacoustic outlier, nicknamed the loneliest whale, evokes the faint radio static of distant stations tuning in the night, a shared human ache for connection amid vastness, yet in its persistency a Euro-decades of unwavering refrain, a Euro lies uplifting resilience, songs sung true, even unheard, ripple onward, fostering quiet insight that our own off-key moments contribute to the world's polyphonic hush, a gentle repetition, call forth, and the blue carries, whether answered or not. Let that falsetto fade now, echoing softly into the blue. Songs call. They ripple. They persist. Let the 52 Hz lament inspire a sensory immersion, the imagined thrum vibrating through water's bulk modulus, a Euro its resistance to compression, allowing sound to propagate with crystalline clarity, like whispers amplified in a hall of mirrors, a Euro where dolphin clicks etch three-dimensional maps in echolocation artistry, their melon heads focusing beams into 20 kHz pulses that bounce back as portraits of prey, a natural sonar suite that paints the dark in acoustic hues. These odontocetes, from bottlenose orchestras to sperm whales, codus, a Euro-patterned click trains closing hunts like musical fermitas, a Euro interconnect pods across oceans, dialects varying by region like accents in a global chorus, their mysteries in dialect drift, a nod to cultural evolution underwater, reassuring in their social weave, even in the profound. Kinship resonates, much as bedtime stories bind generations in shared cadence, inviting a rhetorical whisper, what echoes of your lineage might pulse in the quiet, linking past to present in unbroken tone? Clicks etch. They map. They bind. Repetition builds in the sea's persistent hum, the omnipresent 50 Hz drone from shipping Lanise, a Euro, a man-made baseline underscoring nature's notes, like urban glow-tinting starfields, a Euro yet pierced by purer strains, such as the Antarctic's ice song, crevasses groaning in harmonic series as shelves flex under solar swells, their flexures propagating as Rayleigh waves through brine, a seasonal serenade that lulls Weddell seals into drifts. These flexural acoustics, modeled in finite element simulations, are Euro-computational meshes that predict vibrations like strings on a harp. Euro reveal how climate's warming quickens the tempo, a subtle shift from largo to allegro, philosophical in its implication. The ocean's voice, attuned to Earth's fevers, calls us to listen not in alarm but in attunement, where change's cadence invites adaptive harmony, empowering the spirit to harmonize with flux. Hums persist. Songs groan. Harmonies shift. As vignettes of vocal veils accumulate, painting the sea as an oral archive of the anomalous and the attuned, another enigma surfaces, the drowned town of Yonaguni, off Japan's southern fringe, where submerged terraces and ziggurats are Euro-carved basalt steps plunging 30 meters, aligned with solstice suns. Euro-spark debates of lost civilizations or natural fractals, wave-cut platforms sculpted by Pleistocene typhoons in jointed rock, their right angles a geological slight born of tectonic cleavage, like bookshelves hewn from cliff faces by relentless chisel. Divers tracing these ruins in current-swept silence hear only the bubbles hush, yet sonar surveys a Euro multibeam echoes mapping in bathymetric blues. A Euro affirm the formation's antiquity, some 20,000 years etched by sea levels rise post-ice age, a relic not of Atlantis but of exposure's patient erosion. In this submerged geometry, a light observational touch arises. Euro the irony of nature mimicking heart's intent, mirroring how our constructed worries, weathered by time, reveal underlying simplicities, fostering serene acceptance. Mysteries monumentalized become monuments to process, inviting you to envision wandering these halls in dream's weightless tread, where stone whispers of impermanence's grace. Steps carve. They align. They erode. From Yonaguni's silent stacks, our sonic drift meanders to the equatorial undercurrent's whoosh, that subsurface jet racing 14,000 meters wide beneath the Pacific's equator, a ribbon of swiftness at 100 meters depth, propelled by trade winds piling water westward in Ekman spirals. A Euro surface veers Coriolis-kissed, depths rebounding eastward in geostrophic balance, like a river reversing under pressure's QE. Euro its velocity humming at acoustic signatures that telegraph to far-flung atolls, influencing El Near ± O's feverish flips in butterfly cascades of warmth. This hidden highway, traced by current meters moored like patient sentinels, ferries nutrients in turbulent wakes, seeding phytoplankton blooms that tint the blue with emerald veils, a ripple underscoring the ocean's circulatory wisdom, flows unseen sustain surfaces seen, much as subconscious currents propel conscious calms. Repetition in equatorial fidelity, a rhythmic anchor amid seasonal shifts. Jets race. They hum. They seed. Yet amid these fluid fanfares, The unexplained lingers in the slowdown, a 1997 Pacific anomaly, a minutes-long deceleration of Earth's rotation, detected by atomic clock's unerring tick, hypothesized as oceanic angular momentum transfer, where winds whip gyres into torques that nudge the planet's spin like a skater drawing arms inward, a millisecond lag born of water's vast inertia. This geophysical whisper, modeled in general circulation simulations, vast computational oceans swirling in silicon seas, highlights the sea's gravitational dialogue with the core, a dance where tides tug the bulge and currents counterpoise, philosophical in its scale. Our blue mantle, in its subtle sways, tunes the world's clock, reassuring that even cosmic cadences bend to aqueous grace, inviting reflection on personal slowdowns, those deliberate pauses where haste yields to harmony, as in the breath before sleep's embrace. Spins slow, thoughts nudge, clocks tune. As these acoustic arabesques intertwine, from bloops to circles, triangles to towns, currents to clocks, building a chorus of the curious and the clarified, the ocean's subtle symphonies reveal themselves as invitations to deeper listening, where enigmas, whether ices crack or fishes fan, foster not fragmentation but unity, each note a ripple linking the listener to the whole in interconnected hush. These faint harmonies, so evocative in their elusiveness, fade now into the greater chorus of the sea's boundless story, a swelling refrain that draws us back toward the surface where all mysteries converge, their echoes lingering like aftertones in a vast hall, emphasizing the profound ripple on human tranquility. In pondering the blue's unsolved scores, we find permission to release our own unfinished phrases, letting them drift into the current's forgiving flow, where discovery's peace awaits, serene and encompassing, much as the final breath before dawn's quiet arrival. And so, with these symphonic whispers softening into ambient embrace, what broader implications might these ocean odes hold for the soul adrift, ready to surface in reflective renewal, tying depths to shallows in one luminous whole? Let that chorus swell now, fading into whole. Those broader implications, surfacing now like the first light tracing the horizon's curve after night's deepest vigil, reveal the ocean's odes not as isolated refrains but as a grand, unifying composition that cradles the human spirit in its vast, resonant arms, tying the shallow's shimmering dances to the abyss's silent guardians in one luminous whole, where every wave, glow, and echo speaks to our shared capacity for wonder, inviting us to release the fragments of the day into this endless blue, much as a river meets the sea and loses its name yet gains infinity. In pondering these mysteries from the surface's gentle currents that sink with our breaths to the deep's unyielding poise under pressure's embrace we glimpse the ocean's quiet role as Earth's steadfast companion, absorbing not just heat and carbon at the very worries that weigh upon us, transforming them through interconnected flows into the serene stability that allows life, in all its forms, to flourish and unfold, a philosophical mirror held to our own evenings, where letting go becomes not loss but the gateway to renewal, fostering that peaceful discovery where the soul, adrift no longer, finds its harbor in the hush. Let that surface rise now, light and unifying. Envision, then, the ocean's profound partnership with the atmosphere, a silent dialogue where surface waters drink in the sun's excess warmth like a vast, evaporative sponge, distributing it poleward through gyres and thermohaline rivers those deep conveyor belts of cooled brine sinking in polar sinks, resurfacing centuries later in equatorial upwellings, a global thermostat that tempers fevers and chills with impartial grace, much as a deep inhale draws in the day's tensions only to exhale them diffused into the night air. This meridional overturning circulation, often called the global conveyor, ferries dissolved gases and nutrients in balanced exchange, oxygenating the deep while sequestering carbon in abyssal vaults, where phytoplankton blooms those microscopic meadows tinting the blue with fleeting green fix atmospheric CO2 through photosynthesis's gentle alchemy, sinking it layer by layer into the sediment's embrace, a ripple effect that has buffered climates since the Cambrian's dawn, when early seas cradled the first sparks of complex life. In this exchange, explained simply as density-driven flows where salt and chill make water heavy enough to plunge, like autumn leaves settling in a still pond, lies a reassuring uplift. The ocean, covering 70% of our world, absorbs 90% of excess heat from human endeavors, a selfless guardianship that invites us to mirror its patience, releasing our own accumulated burdens into the flow of rest, where what sinks finds purpose in the greater cycle, empowering a sense of shared stewardship that soothes rather than overwhelms. Repetition in its millennial churn, a rhythmic affirmation of endurance's quiet power. Flows ferry. They balance. They guard. From this climatic cradle, our reflections lap toward the ocean's gift to mindfulness, how its mysteries those bioluminescent lanterns flickering in twilight hush or acoustic enigmas resonating through sound ducts serve as meditative anchors, drawing the mind from fragmented haste to the interconnected present, much like the steady lap of waves against a midnight shore that erases footprints in the sand, leaving only the essence of being. Consider the practice of blue mind, that serene state evoked by water's proximity, where studies gentle inquiries blending neuroscience and psychology reveal how ocean vistas quiet the default mode network, that brains wanderer prone to rumination, shifting focus to sensory immersion, the salt-kissed breeze on skin, the horizon's infinite line-easing perspectives pinch, a phenomenon rooted in evolutionary echoes, where our ancestors found solace in coastal refuges, the sea's rhythms sinking heart rates to theta waves, those languid pulses of creativity and calm that prelude sleep's velvet threshold. In contemplating the sargasso's patient eels or the pufferfish's mandala labors, we practice this attunement, their unhurried odysseys mirroring how mindfulness untangles the knots of overthought, inviting rhetorical whispers. What shallow drifts in your daily tide might yield to deeper observation, transforming fleeting worries into waves that crest and recede without residue? Here, the ocean's enigmas become tools for tranquility, their unresolved grace a reminder that not knowing fosters presence, where the 52 Hertz whale's solitary song, echoing unheard yet true, empowers us to voice our inner refrains without demand for reply, fostering quiet insight that true harmony arises not in resolution, but in the singing itself, a poetic flourish that ties the script's vignettes into a cohesive lullaby for the soul. Anchors draw. Mind's quiet. Presence blooms. Let this mindful merging draw us to vignettes of renewal, where the ocean's cycles echo sleep's restorative arc, from the daily vertical migrations of lanternfish ascending in trillion-strong clouds to fertilize surface blooms, a nocturnal nutrient rain that greens the dawn, to the seasonal pulses of krill swarms under Antarctic flows, their bioluminescent pulses syncing with ice's melt to seed the food web's chain, each phase a surrender and resurgence much like the body's glymphatic flush in slumber, the brain's nighttime cleanup crew where fluid waves sweep away the day's mental clutter, like a gentle tide rinsing beach sand, restoring clarity for the morrow. These parallels, grounded in accessible biology a euro, where adenosine buildup from wakeful labors cues the pineal gland's melatonin whisper, akin to the sea's circadian cues from light's fading veil a euro underscore the ocean's role as metaphor made manifest, its tides ebbing to reveal hidden flats teeming with life, then flooding back in nourishing rush, inviting us to embrace our own ebbs as fertile pauses, where the mind's marine snow of ideas settles into stratified dreams, birthing insights upon resurfacing. In the kelp forests sway or seagrass meadows' purifying grasp, we see this mirrored, carbon sponges absorbing excess, roots anchoring against erosion's pull, a resilient weave that reassures through everyday kinship a euro. If you've ever watched a stream polish stone smooth over seasons, or felt the post-storm clarity after rain's catharsis, you'll sense that shared rhythm, the way the ocean teaches release as replenishment, repetition of cyclic motifs building a cadence that lulls the listener deeper, empowering the realization that sleep, like the sea, is not escape but essential immersion, where mysteries dissolve into the whole serene embrace. Cycles ebb. They renew. They restore. As these ties illuminate the ocean's whisper to our inner worlds, consider the broader canvas of exploration's horizon, where humanity's gentle probes a Euro rose gliding like mechanical jellyfish into trench vaults, or autonomous gliders sampling currents in silent patrols. A Euro unveil not conquest but communion, expanding the known from a mere 5% to visions of the 95% blue still veiled in quiet potential, a frontier not of rivalry but of revelation, much as dreams probe the subconscious's uncharted bays, surfacing pearls of forgotten wisdom. Future fleets of undersea drones, powered by wave energy's endless nod, will map seafloor topographies in high-res bathymetric detail. A Euro-detailed underwater maps, sketched by sound pings like fingers tracing a lover's palm in the darker Euro, or deploy bioacoustic buoys to transcribe cetacean dialects in real-time symphonies, bridging species in shared sonic spaces. These endeavors, laced with ethical pauses for minimal disturbance, promise discoveries from novel extremophiles yielding medical marvels. Euro enzymes for resilient drugs, like those from Ventarkia that inspire heat-stable vaccines. A Euro to untapped carbon sinks that aid climate's healing hand, promising not just knowledge, but the soul's quiet thrill of belonging to something vaster, easing us toward rest's welcoming fold, a ripple effect where one submersible's gaze into the Hadal might inform global models of ocean health, fostering interconnected hope. In this unfolding, a subtle irony graces the scene. Our tools, born of curiosity's spark, return gifts of humility, reminding that the sea's vastness dwarfs our strides yet welcomes them as kin, much like the night's canopy, studded with stars we chart yet never own, invites stargazing's peaceful surrender. And as you drift now, envision joining this quiet vanguard, not in haste but in harmony, your contemplations a contribution to the collective dream, where exploration's awe empowers the individual to rest secure in the unknown's benevolent fold. Probes glide. They unveil. They connect. Shifting with the unhurried grace of a current rounding a cape, let us linger on the ocean's legacy for emotional tides, how its mysteries. Euro rogue waves curling from interferences chance ballet or mirages bending light in illusory paths. A Euro model resilience amid caprice, teaching that chaos, when viewed from afar, resolves into patterns of profound beauty, much as a fretful mind, observed without judgment, unwinds into clarity's calm. The Bermuda Triangle's methane veils or Yanogani's eroded ziggurats, once harbingers of dread, now stand as testaments to physics' impartial poetry, just as the triangle's methane veils once veiled dread but now unveil physics poetry, so do our tempests invite reframing, from storm to surf, where gas eruptions slash buoyancy like sudden sighs deflating a balloon, or wave-cut platforms mimic ancient intent through relentless chisel, inviting us to reframe personal tempests, those vanishing acts of confidence or submerged histories of heartache, not as losses but as invitations to deeper dives, where recovery blooms in the sediment's quiet hold. This reframing, rooted in cognitive parallels where exposure therapy mirrors the submersible's plunge into fear's domain, emerging with mapped mastery empowers a gently philosophical stance. The ocean's enigmas, in their dissolution, affirm that vulnerability is the vessel for strength. Repetition of ripple motifs reinforcing how one wave's caper influences the shore's subtle sculpt, just as a single evening's reflection reshapes the morrow's flow, fostering serene acceptance that life's mysteries, like the seas, are not to be solved but surfed, each crest a cue to lean into the ride with trusting poise. Tides model. They reframe. They empower. From emotional equanimity, our vignettes crest toward the ocean's inspirational breath for creativity's tide, where the twilight zone's lanternfish discos or comb jelly's prismatic trails spark the artist's muse, their fleeting illuminations akin to the eureka flashes that pierce the fog of blocked flow, turning void into vivid canvas. Writers and composers, from Melville's Leviathan-haunted prose to Debussy's La Mer evoking wave-woven symphonies, have drawn from this blue repository, its vastness a metaphor for the infinite within, where the colossal squid's elusive coil inspires narratives of hidden depths, or the sargasso's floating forest seed tales of nomadic souls finding rootless home. These borrowings, laced with wonder, remind that the sea's unsolved songs are the upsweep's volcanic whistle or the 52 Hz's lone aria fuel innovation's fire, much as a walk along the strand loosens the tongue's knots, words washing up like seashells in the surf. In this creative confluence, a light observational touch arises, the irony of the deep's darkness birthing light's legacy, mirroring how repose's blankness precedes dawn's inspired rush, and in envisioning your own dreams as abyssal explorations, feel the empowerment of untapped reservoirs, where the ocean's 95% unknown becomes a boundless palette, repetition of discovery's motif a soothing mantra, delve softly, and abundant surfaces, serene and self-renewing. Muses spark. Ideas crest. Canvas fills. As these threads weave toward culmination, picture the ocean's holistic hush enveloping the globe's rhythms, from coral polyps' nightly broadcasts to sperm clouds released in synchronized pulses under lunar Q, a mass conception veiled in Milky Veil to the thermohaline's millennial loops that knit hemispheres in thermal tapestries, each process a vignette of collective care, where individual acts a single dino flagellates phosphorescent spark or a copepod's dealer center sustain the symphony's swell. This interconnectedness, explained through simple ecology as trophic cascades where top predators prune the web for balance, like gardeners clipping for bloom, underscores the sea's motivational message. In unity's weave, fragility finds fortitude, inviting you to sense your place within it, breaths aligning with tidal heaves, worries absorbed like CO2 in algal feasts, a philosophical close that ties the script's arc from surface sighs to abyssal anthems, fostering awe at the blue's boundless gift, a mirror to the mind's own ocean, where mysteries cradle rather than confound, empowering release into the night's gentle current. Rhythms envelop, acts sustain, unity weaves. And so, as the vignettes converge in this reflective pool, their implications ripple outward to encompass the sleeper's sanctuary, where the ocean's odes become a blueprint for tranquil traversal. Let the waves' measured breath guide your inhales, the bioluminescent blooms illuminate inner shadows, the acoustic enigmas attune your ears to silence's song, and the deep's guardians remind you of unyielding grace beneath the surface calm. Feel now, as you drift in this imagined embrace, the water's cool kiss on sun-warmed skin, the horizon's haze blurring edges into oneness, each mystery a soft summons to surrender, not to oblivion, but to the profound peace of being held in the whole's whisper, where 95% unexplored invites not fear but endless invitation, a vastness as comforting as the familiar dark behind closed lids. In this luminous whole, tying shallows to depths in eternal flow, may these ocean lullabies linger like a favored melody half remembered in dawn's first light, carrying you gently into dreams where currents conspire in your favor, worries dissolved into salt-kissed serenity, and wonder, ever present, awakens refreshed in the morrow's tide. As we began with the ocean's breathing cradle, so we end in its boundless arms, worries smoothed like pebbles on that forgotten beach. Rest now, cradled in the blue's boundless arms, where every secret shared becomes a step toward that peaceful discovery, serene and eternal.
Welcome. Find a comfortable position, somewhere you can truly settle, where the weight of the day begins to dissolve like starlight fading into dawn. Tonight, we're embarking on a journey through one of the universe's most profound mysteries, black holes, and exploring the deep psychological currents that flow when we contemplate the vastness of space. This isn't just a story about cosmic phenomena. It's an invitation to release, to surrender into the infinite, to find peace in the very vastness that sometimes unsettles us. As you listen, allow your breath to slow, to deepen. There's nowhere you need to be, nothing you need to do. Just listen. Simply listen. Let the words wash over you like gentle waves, carrying away tension, carrying away the accumulated weight of 1,000 small concerns. We'll move slowly through the cosmos together, pausing often, allowing silence to speak as eloquently as words. Black holes. Even the name carries a certain gravity, doesn't it? A weight, a pull. These cosmic entities have captivated human imagination since their theoretical prediction emerged from Einstein's equations over a century ago. They represent boundaries, edges of understanding, thresholds between the known and the unknowable. And perhaps that's why they fascinate us so deeply, why they appear in our dreams and our fears, why they serve as perfect metaphors for the mysteries we carry within ourselves. But before we approach these cosmic thresholds, before we stand at the edge of event horizons and peer into singularities, we must understand where black holes come from. We must witness their birth. And that birth begins not in darkness, but in light, in the brilliant, burning life of stars. Imagine, if you will, a star. Not just any star, but a massive one, perhaps 20 times, 30 times, even 50 times the mass of our own sun. Picture it suspended in the velvet darkness of space, a sphere of incandescent plasma, burning with a fury that has persisted for millions of years. This star is a furnace, a cosmic forge where the simplest elements are transformed into more complex ones through the alchemy of nuclear fusion. Deep in its core, hydrogen atoms collide with such tremendous force that they fuse together, forming helium and releasing vast quantities of energy in the process. This energy, this outward pressure of radiation and heat, is what keeps the star from collapsing under its own immense gravitational weight. It's a delicate balance, a cosmic dance between the inward pull of gravity and the outward push of fusion. For millions of years, this equilibrium holds. The star shines steadily, a beacon in the darkness. Take a moment here, breathe with the rhythm of that stellar furnace. Inhale, the gathering of hydrogen, the compression, the building pressure. Exhale, the release of energy, the outward flow of light, the steady burning. Feel how your own body maintains its balances. Temperature, breath, heartbeat, just as the star maintains its equilibrium between collapse and explosion, but nothing lasts forever. Eventually, after millions or even billions of years, the hydrogen fuel in the star's core begins to run out. The fusion reactions that have sustained the star for so long start to wane, and when they do, the delicate balance shifts. Gravity, patient and inexorable, begins to win. As the core's hydrogen depletes, the star responds by contracting slightly, which increases the temperature and pressure in its core. This allows helium fusion to begin, helium atoms fusing into carbon and oxygen. The star enters a new phase of life, burning helium now instead of hydrogen. But this phase doesn't last as long. Helium burns faster, more furiously, and when the helium runs out, if the star is massive enough, it contracts again, heating up further, allowing carbon to fuse into heavier elements: neon, magnesium, silicon. Each successive stage of fusion happens more quickly than the last. A star might burn hydrogen for 10 million years, helium for 1 million years, carbon for 1,000 years, silicon for just a few days. It's like watching a cosmic clock wind down, each tick faster than the one before, each moment more urgent, more intense. In these final stages, the star develops a layered structure, like an onion. The outermost layers still contain hydrogen. Beneath that, a shell of helium, then carbon and oxygen, neon and magnesium, silicon and sulfur. And at the very center, in the core, iron begins to accumulate. Iron, in the cosmic economy of nuclear fusion, iron is bankruptcy. Fusing iron doesn't release energy, it consumes energy. When a massive star's core becomes predominantly iron, the game is over. There's no more fuel to burn, no more fusion reactions to generate the outward pressure needed to resist gravity's inward pull. Let your awareness settle on this moment of cosmic transition. The star has burned brilliantly for millions of years, transforming lighter elements into heavier ones, radiating light and warmth into the surrounding space. But now, with an iron core at its center, it stands at a threshold. The balance that has sustained it for so long is about to break. Gravity is about to claim its victory. And it happens fast, catastrophically fast. The iron core, no longer supported by fusion energy, begins to collapse. Not slowly, not gradually, but in a fraction of a second. Electrons are forced into protons, creating neutrons and releasing neutrinos in a process called neutronization. The core, which might have been roughly the size of Earth, collapses to a sphere perhaps 20 kilometers across, a neutron star, in less than a second. The collapse happens so rapidly that the outer layers of the star don't immediately realize what's occurring at the center. They're still falling inward, still being pulled by gravity, when suddenly they encounter the incredibly dense neutron core. It's like a cosmic traffic accident, matter falling inward at a significant fraction of the speed of light suddenly meets an immovable barrier. The result is a rebound, a shock wave that propagates outward through the star's layers with unimaginable violence. This is a supernova, one of the most energetic events in the universe. For a few weeks, this single dying star can outshine an entire galaxy of hundreds of billions of stars. The explosion hurls the star's outer layers into space at speeds of tens of thousands of kilometers per second, enriching the interstellar medium with all those heavy elements forged in the star's core. The carbon, oxygen, iron, and gold that will eventually become part of new stars, new planets, new life. But we're not here for the explosion, magnificent as it is. We're here for what remains behind. If the original star was massive enough, roughly 25 to 30 times the mass of the Sun or more, even the neutron core cannot withstand gravity's pull. The collapse continues. Neutrons themselves are compressed beyond their ability to resist. There is no known force in physics that can stop the collapse now. The core continues to contract, becoming smaller and denser until it crosses a threshold from which there is no return. It becomes a black hole. Breathe here. Let that transformation settle into your awareness. A star that once blazed with the light of millions of suns has collapsed into a region of space so dense, so gravitationally intense, that not even light can escape. From maximum luminosity to perfect darkness, from vast stellar sphere to infinitesimal point. It's a transformation as complete as any in nature, like the caterpillar that dissolves entirely within the chrysalis before reforming as a butterfly, except here, the butterfly is darkness itself. This is how stellar mass black holes are born, from the deaths of massive stars, from the surrender of matter to gravity's ultimate embrace. But there are other types of black holes, formed through different processes, existing at different scales. Stellar mass black holes, born from collapsing stars, typically range from about 5 to several dozen times the mass of our Sun. They're scattered throughout galaxies, invisible markers of stellar death, detectable only through their gravitational effects on nearby matter or companion stars. Then there are intermediate mass black holes, ranging from hundreds to thousands of solar masses. These are more mysterious, less well understood. They might form from the merger of smaller black holes, or from the direct collapse of very massive stars in the early universe, or through other processes we're still working to understand. Recent research from 2024 has identified several promising candidates for intermediate mass black holes in dense star clusters, suggesting they might be more common than previously thought. And then, at the other end of the scale, there are the supermassive black holes. These cosmic giants lurk at the centers of most large galaxies, including our own Milky Way. They contain millions or even billions of times the mass of the Sun. The supermassive black hole at the center of our galaxy, called Sagittarius A star, has a mass of about 4 million suns. The black hole at the center of the galaxy M87, famously imaged by the Event Horizon Telescope in 2019 and refined in subsequent observations through 2024, contains about 6.5 billion solar masses. How do supermassive black holes form? This remains one of the great questions in astrophysics. They might grow from stellar mass black holes that consume vast amounts of matter over billions of years. They might form from the direct collapse of enormous gas clouds in the early universe. They might grow through mergers, smaller black holes combining into larger ones. Recent gravitational wave observations from LIGO and Virgo detectors have confirmed that black hole mergers do occur, and sophisticated computer simulations in 2024 have shown how these mergers might build up supermassive black holes over cosmic time. Let your mind expand to hold these scales. From black holes just a few times the mass of our sun to monsters billions of times more massive, from objects a few dozen kilometers across to regions that would encompass our entire solar system. The universe operates at scales that dwarf human comprehension, and black holes exemplify this cosmic grandeur. But regardless of their size or origin, all black holes share certain fundamental properties. They all warp space-time around them. They all possess an event horizon, that boundary beyond which nothing can escape. And they all, at their centers, contain a singularity, a point where our current understanding of physics breaks down. Let's approach these features slowly, carefully, with the reverence they deserve. To understand black holes, we must first understand gravity, not as Newton conceived it, as a force acting at a distance, but as Einstein revealed it, as the curvature of space-time itself. Imagine space-time as a fabric, a flexible sheet stretched taut. In the absence of matter or energy, this fabric is flat, smooth, undistorted. But place a mass on this fabric, a star, a planet, even a person, and it creates a depression, a curvature. The more massive the object, the deeper the depression. This curvature is what we experience as gravity. When Earth orbits the sun, it's not being pulled by an invisible force. It's following the curved path through space-time created by the sun's mass. It's like a marble rolling around the depression created by a bowling ball on a stretched rubber sheet. The marble isn't being pulled by the bowling ball, it's simply following the curved surface. This is Einstein's great insight from his general theory of relativity, published in 1915 and confirmed through countless observations and experiments over the past century. Gravity isn't a force, it's geometry. Mass tells space-time how to curve, and curved space-time tells mass how to move. Now imagine increasing the mass of an object while keeping its size the same, or compressing the same mass into a smaller and smaller volume. The curvature of space-time becomes more pronounced, steeper, more extreme. A planet creates a gentle depression. A white dwarf star creates a deeper one. A neutron star creates a steep-sided pit. And a black hole? A black hole creates a curvature so extreme that space-time essentially folds in on itself, creating a one-way passage into a region from which nothing, not matter, not light, not information, can escape. Take a moment to visualize this. See the fabric of space-time, smooth and flat. Now watch as a massive star collapses, compressing its mass into a smaller and smaller region. Watch the depression in space-time deepen, the sides becoming steeper and steeper until finally they become vertical, infinite. The fabric doesn't just curve, it tears, creating a hole, a void, a place where the normal rules of space and time cease to apply in the ways we understand them. This is the event horizon, the boundary of no return. The event horizon is not a physical surface. You couldn't touch it, couldn't bounce a ball off it. It's a mathematical boundary, a point of no return defined by the escape velocity reaching the speed of light. Inside the event horizon, you would need to travel faster than light to escape. And since nothing can travel faster than light, nothing can escape. For a non-rotating black hole, what physicists call a Schwarzschild-Schwarzschild black hole, after Carl Schwarzschild-Schwarzschild, who found the first exact solution to Einstein's equations just months after general relativity was published, the event horizon is a perfect sphere. Its radius, called the Schwarzschild-Schwarzschild radius, depends only on the black hole's mass. For a black hole with the mass of our Sun, the Schwarzschild-Schwarzschild radius would be about 3 kilometers. For the supermassive black hole at the center of our galaxy, it's about 12 million kilometers, roughly 17 times the radius of the Sun. But most black holes aren't perfectly spherical. They rotate, sometimes very rapidly, because they form from rotating stars, and conservation of angular momentum means that as the star collapses, its rotation speeds up, like a figure skater pulling in their arms during a spin. A rotating black hole, called a Kerr black hole after Roy Kerr, who solved the equations for rotating black holes in 1963, has a more complex structure. It has an event horizon, but also an outer boundary called the ergosphere, where space-time itself is dragged around by the black hole's rotation. Imagine standing near a rotating black hole, outside the event horizon, but within the ergosphere. Space-time itself is being pulled around the black hole, and you're being pulled with it, like a leaf caught in a whirlpool. You could still escape. You're outside the event horizon, but you couldn't stand still. You'd be forced to move in the direction of the black hole's rotation, dragged along by the rotating space-time itself. This frame-dragging effect, predicted by general relativity and confirmed by observations of rotating neutron stars and black holes, is one of the most mind-bending consequences of Einstein's theory. It's not just that massive objects curve space. Rotating massive objects drag space-time around with them, like honey being stirred in a jar. Now, imagine crossing the event horizon. What would you experience? From your perspective, falling toward a black hole, something strange would happen. As you approach the event horizon, you'd notice that the black hole appears to grow larger, filling more and more of your field of view. The stars behind you would appear to shift and distort, their light bent by the black hole's gravity. If you looked carefully, you might even see multiple images of the same star, their light taking different curved paths through space-time to reach your eyes. Time would also behave strangely. According to general relativity, time passes more slowly in stronger gravitational fields, an effect called gravitational time dilation. As you fell closer to the event horizon, time for you would pass normally, but if you could somehow look back at the universe you left behind, you'd see it speeding up. Stars would age rapidly, galaxies would evolve, the universe would rush forward through time. And then you'd cross the event horizon. From your perspective, nothing special would happen at that exact moment. There'd be no barrier, no sensation of crossing a boundary. You'd simply continue falling. But you'd have crossed a point of no return. Every direction you could travel would lead further into the black hole. Even if you pointed yourself directly away from the center and accelerated at the maximum possible rate, you'd still be pulled inexorably inward. The future direction of time itself now points toward the singularity at the center. Let this sink in. Breathe with it. Inside the event horizon, the singularity isn't just in your future. It is your future. It's as inevitable as tomorrow, as unavoidable as the next moment. This is what it means for space-time to be curved so extremely that all paths lead inward. But what would an outside observer see? This is where things become even stranger. If someone watched you fall toward a black hole from a safe distance, they would never see you cross the event horizon. Never. As you approached the event horizon, they would see you moving more and more slowly, your image becoming more and more red-shifted as the light from your body struggled to escape the black hole's gravitational pull. You would appear to freeze asymptotically approaching the event horizon, but never quite reaching it, your image fading and reddening until it became invisible. This is why black holes were once called frozen stars, because from the outside, matter appears to freeze at the event horizon, never quite falling in. But this is an illusion created by the extreme time dilation. From your perspective, you'd cross the event horizon in a finite amount of time. From the outside perspective, it would take infinite time. Both perspectives are valid. They're simply different ways of slicing up the curved space-time around the black hole. This leads to a profound puzzle that physicists are still grappling with: the black hole information paradox. If matter falls into a black hole and, from the outside perspective, never quite crosses the event horizon, what happens to the information encoded in that matter? Does it remain somehow encoded on the event horizon? Does it get destroyed when it reaches the singularity? Or does it escape somehow, perhaps through Hawking radiation? Stephen Hawking's groundbreaking work in the 1970s showed that black holes aren't entirely black. Through quantum mechanical effects near the event horizon, black holes emit radiation, now called Hawking radiation, and slowly evaporate over time. For stellar mass black holes, this evaporation takes far longer than the current age of the universe, but for tiny black holes, it could happen quickly. Recent theoretical work in 2024 has refined our understanding of Hawking radiation and suggested possible ways that information might be preserved, perhaps encoded in subtle correlations in the radiation itself. But we're getting ahead of ourselves. Before we explore Hawking radiation and black hole evaporation, we need to understand what happens as you continue falling past the event horizon into the increasingly extreme gravitational field closer to the center. We need to talk about spaghettification. Gravity doesn't pull uniformly. If you're standing on Earth, your feet are slightly closer to Earth's center than your head, so they experience slightly stronger gravity. The difference is tiny, far too small to notice, but it's there. This difference in gravitational force across an object is called a tidal force, and it's what causes ocean tides on Earth. The moon's gravity pulls slightly more strongly on the side of Earth facing the moon than on the far side, creating a bulge of water, a tide. Near a black hole, tidal forces become extreme. Imagine falling feet first toward a stellar mass black hole. Your feet are closer to the black hole than your head, so they experience stronger gravity. They're pulled harder. The difference in gravitational force between your feet and your head becomes enormous, strong enough to stretch you, to pull you apart. This is spaghettification, sometimes called the noodle effect. As you fall toward a black hole, you'd be stretched lengthwise and compressed sideways, elongated like a piece of spaghetti. For a stellar mass black hole, this would happen well before you reached the event horizon. The tidal forces would tear you apart at the molecular level, then the atomic level, reducing you to a stream of particles spiraling into the black hole. It sounds horrific, but remember, we're exploring these cosmic phenomena not to frighten, but to understand, to find a strange peace in the universe's most extreme processes. Spaghettification is simply gravity doing what gravity does, creating order from chaos in its own inexorable way. Theoretical work refined our understanding of how black holes form and behave. But it wasn't until the 21st century that we obtained direct evidence. The detection of gravitational waves in 2015 provided the first direct observation of black holes, not through light they emitted or affected, but through the ripples they created in space-time itself. The Event Horizon Telescope image in 2019 showed the shadow of a black hole for the first time, confirming predictions made decades earlier. And the pace of discovery continues to accelerate. In 2024 alone, we've detected hundreds of gravitational wave events, imaged multiple black holes with increasing resolution, discovered new populations of intermediate mass black holes, and refined our theoretical understanding of quantum effects near event horizons. This progress is a testament to human curiosity, ingenuity, and persistence. Black holes, once purely theoretical, once thought to be unobservable, are now objects we can study in detail, can image, can use to test our most fundamental theories of physics. And we're not done. Future gravitational wave detectors, like the space-based LISA mission planned for the 2030s, will detect supermassive black hole mergers across the entire universe. Next-generation telescopes will image black holes in unprecedented detail. Advances in quantum gravity theory may finally resolve the singularity, may tell us what really happens at the center of a black hole. The universe is revealing its secrets, slowly, patiently, to those who ask the right questions and look carefully. And this process of discovery, this gradual illumination of cosmic mysteries, is itself a source of meaning and wonder. We live in an age of cosmic discovery. We're learning things about the universe that no previous generation could have known. We're seeing things, black holes, gravitational waves, the cosmic web of galaxies that were invisible to our ancestors. We're part of a grand human project of understanding, of pushing back the boundaries of ignorance, of bringing light to darkness. And you, by engaging with these ideas, by contemplating these cosmic phenomena, are part of that project. You're participating in the human endeavor to understand the universe. You're exercising the capacity for wonder and curiosity that makes us human. One of the deepest mysteries in physics is the arrow of time, why time seems to flow in one direction, from past to future, why we remember the past but not the future, why entropy disorder increases over time. Black holes are intimately connected to this mystery. In the 1970s, physicist Jacob Bekenstein and Stephen Hawking discovered that black holes have entropy, a measure of disorder or information content. Specifically, the entropy of a black hole is proportional to the area of its event horizon, not its volume. This was surprising and profound, suggesting deep connections between gravity, quantum mechanics, and thermodynamics. The second law of thermodynamics states that the total entropy of a closed system always increases over time. This is the arrow of time, the reason why eggs break but don't spontaneously reassemble, why heat flows from hot to cold but not the reverse, why we age and remember the past but not the future. Black holes fit into this picture in a remarkable way. When matter falls into a black hole, it might seem like entropy is decreasing. The matter becomes more ordered, compressed into a smaller region. But Bekenstein and Hawking showed that the increase in the black hole's entropy, the increase in the area of its event horizon, more than compensates for any decrease in the entropy of the matter. The total entropy still increases, and the second law is preserved. In fact, black holes are the most efficient entropy generators in the universe. A supermassive black hole has more entropy than all the stars in its galaxy combined. The ultimate fate of the universe, in some scenarios, is a state of maximum entropy, where all matter has either evaporated or fallen into black holes, and even the black holes have evaporated through Hawking radiation, leaving only a thin soup of radiation in an ever-expanding space. This might sound bleak, a heat death, a final state of maximum disorder and minimum structure. But it's also a kind of completion, a return to simplicity, a cosmic exhale after the long, complex inhale of structure formation. And even this might not be the end. Some theories suggest that quantum fluctuations in the far future could spontaneously create new universes, new big bangs, new cycles of complexity and simplicity. The universe might be eternal, not in the sense of lasting forever in one state, but in the sense of continually transforming, dying, and being reborn in an endless cosmic cycle. These are speculations, of course. We don't know the ultimate fate of the universe. But contemplating these possibilities, deep time, cosmic cycles, the arrow of entropy, can provide a profound sense of perspective. Your life, your concerns, your joys and sorrows, all of these are part of the universe's journey from low entropy to high entropy, from simplicity to complexity, and back to simplicity. You're a temporary eddy in the flow of entropy, a brief local decrease in disorder, your organized body and mind, that contributes to the overall increase in cosmic entropy. And there's something beautiful about that. You're not separate from the cosmic flow. You're part of it. Your existence, your consciousness, your capacity to wonder and love and create, all of this is the universe's way of exploring itself, of creating temporary pockets of order and meaning in the long journey toward maximum entropy. Breathe with this understanding. You're a wave in the cosmic ocean, a temporary pattern in the flow. And when the wave subsides, the ocean remains, ready to form new waves, new patterns, new expressions of its infinite creativity. We've touched on this theme several times, but let's explore it more deeply. The paradoxical comfort of cosmic insignificance. In our daily lives, we often feel pressure to be significant, to matter, to make a difference. We worry about our legacy, our impact, whether we'll be remembered. We compare ourselves to others, measure our achievements, strive for recognition and success. This pressure can be exhausting. It can lead to anxiety, burnout, a sense of never being enough. We're constantly trying to prove our significance in a world that seems to demand it. But what if we let go of that pressure? What if we accepted our cosmic insignificance, not as a source of despair, but as a source of freedom? From the cosmic perspective, nothing we do matters in any ultimate sense. The universe doesn't care whether you succeed or fail, whether you're remembered or forgotten. In 1 billion years, the sun will have expanded and engulfed Earth. In 1 trillion years, the stars will have burned out. In 100 billion years, even black holes will have evaporated. Nothing we build will last. Nothing we achieve will be remembered. This could be depressing, but it can also be liberating. If nothing matters cosmically, then we're free to decide what matters to us. Personally, locally, temporarily. We're free to create our own meaning, to choose our own values, to live according to our own lights rather than some cosmic standard. The existentialist philosopher Albert Camus wrote about the absurdity of existence, the gap between our human need for meaning and the universe's indifference. He argued that we should embrace this absurdity, should rebel against it by creating meaning anyway, by living fully and authentically, even in the face of cosmic meaninglessness. Modern psychology has found that this perspective can be healthy. A 2024 study in the Journal of Positive Psychology examined what the researchers called cosmic acceptance, the ability to accept one's insignificance in the cosmic scheme while still finding personal meaning and purpose. They found that people high in cosmic acceptance reported lower anxiety, greater life satisfaction, and more authentic living. They were less concerned with external validation and more focused on intrinsic values and relationships. The key, the researchers found, was balance. People who focused only on cosmic insignificance without finding personal meaning tended toward nihilism and depression. People who denied cosmic insignificance and insisted on cosmic importance tended toward grandiosity and anxiety. But people who could hold both perspectives, I'm cosmically insignificant and my life has personal meaning, showed the best psychological outcomes. This is the wisdom of cosmic perspective, to zoom out, to see yourself as a tiny, temporary part of a vast, ancient universe, and then to zoom back in, to embrace your brief existence, to find meaning and joy and connection in the here and now. You don't matter to the universe, but you matter to yourself, to the people you love, to the small corner of space-time you inhabit. And that's enough. That's more than enough. Let's explore some specific practices you can use to cultivate the sense of cosmic peace we've been discussing. These are practices you can return to whenever you need perspective, whenever you need to release anxiety, whenever you need to reconnect with the vastness. This is the practice we touched on earlier. Lie down or sit comfortably. Close your eyes. Imagine yourself from above, then zoom out progressively. Room, building, city, region, country, continent, Earth, solar system, galaxy, universe. Then zoom back in, returning to your body, your breath. Do this slowly, taking time at each level to really visualize and feel the scale. This practice helps train your mind to shift perspectives, to access the cosmic view when you need it. Go outside on a clear night, or simply imagine a starry sky. Choose a star. Remember that the light entering your eyes left that star years, or decades, or centuries ago. It traveled through the vacuum of space, through the atmosphere, to reach you. You and that star are connected by this light, by the photons that bridge the distance between you. Feel that connection. Extend it to all the stars you can see, to all the galaxies beyond. You're not isolated. You're connected to the cosmos by light, by gravity, by the atoms in your body that came from stars. Sit comfortably and breathe slowly. With each inhale, imagine breathing in deep time, the billions of years of cosmic history, the slow formation of galaxies and stars, the patient work of evolution. With each exhale, release your urgency, your impatience, your sense of time pressure. Let your breath slow to match the cosmic rhythm, slow, patient, unhurried. The universe has all the time in the world. So do you in this moment. This is a more advanced practice, useful for releasing difficult emotions or thoughts. Visualize a black hole, not as something frightening, but as a cosmic recycling center, a place where matter and energy are transformed. Now, imagine placing a difficult emotion, anxiety, anger, grief, near the event horizon. Watch it spiral inward, watch it cross the horizon, watch it disappear into the black hole. It's not destroyed, it's transformed, recycled, returned to the cosmic flow. You can let it go. The universe will take care of it. Place your hand on your chest, feeling your heartbeat. Remember that the atoms in your body were forged in stars, scattered by supernovae, gathered into the solar system, incorporated into Earth, cycled through countless organisms, and now temporarily organized into you. Feel gratitude for this improbable journey, for the cosmic processes that made your existence possible. You're not separate from the universe. You're a way the universe has organized itself to become aware of itself. How remarkable, how precious. These practices, done regularly, can help rewire your brain's response to cosmic contemplation, shifting it from anxiety to awe, from fear to peace. They're not escapes from reality, they're ways of seeing reality more clearly, more completely, from a perspective that includes both the immediate and the cosmic. One final theme to explore: the role of mystery in mental health and well-being. Modern culture often emphasizes certainty, control, and complete understanding. We want answers, solutions, explanations. We're uncomfortable with ambiguity, with not knowing, with mystery. But black holes remind us that mystery is fundamental to the universe. We don't fully understand what happens at the singularity. We don't know if information is truly preserved or destroyed. We don't know what dark matter is, or dark energy, or whether our universe is one of many in a vast multiverse. We don't know the ultimate fate of the cosmos. And that's okay. That's more than okay. It's wonderful. Mystery is what drives science, what motivates exploration, what keeps life interesting. If we knew everything, if there were no more questions to ask, existence would be boring, static, complete. Psychologically, learning to be comfortable with mystery, with not knowing, is a key component of mental health. Anxiety often stems from intolerance of uncertainty, a need to know, to control, to predict. But life is inherently uncertain. We can't know the future. We can't control most of what happens to us. We can't fully understand ourselves or others. Practices like mindfulness and acceptance-based therapies teach us to be okay with this uncertainty, to tolerate not knowing, to accept mystery as a fundamental part of existence. Research has consistently shown that people who can tolerate uncertainty have lower anxiety and better mental health. A 2024 study in behavior research and therapy examined the relationship between cosmic mystery acceptance, comfort with the fundamental mysteries of existence and mental health. The researchers found that people who could embrace cosmic mystery, who could be comfortable not knowing the answers to big questions, showed greater psychological flexibility, lower existential anxiety, and higher well-being. Black holes, in this sense, are perfect teachers. They embody mystery. They're places where our understanding breaks down, where we encounter the limits of knowledge, and they invite us to be okay with that, to appreciate the mystery rather than fear it, to find wonder in the unknown rather than anxiety. This doesn't mean we stop seeking answers. Science continues to probe the mysteries of black holes, and we continue to learn. But it means we can hold our knowledge lightly, can appreciate what we know while remaining open to what we don't know, can find peace in the journey of discovery rather than demanding the destination of complete understanding. We've journeyed far together, from the physics of black holes to the psychology of cosmic contemplation, from stellar collapse to human consciousness, from event horizons to mental health practices. Let's integrate these threads, bringing them together into a coherent whole. Black holes are real physical objects, extreme expressions of gravity and space-time curvature, born from the deaths of massive stars or the accumulation of matter in galactic centers. They're surrounded by brilliant accretion disks, emit Hawking radiation, merge and create gravitational waves, and slowly evaporate over cosmic time. They're objects of scientific study, windows into the most extreme physics in the universe. But they're also metaphors, symbols, teachers. They represent the unknown, the mysterious, the places where our understanding breaks down. They embody transformation, the death of stars giving birth to something new. They demonstrate the interconnectedness of the cosmos, their gravity reaching across space, their mergers sending ripples through the fabric of space-time itself. And contemplating them, contemplating black holes and the vastness of space, can be therapeutic. It can trigger awe, which reduces self-focus and increases well-being. It can provide perspective, helping us see our concerns within a larger context. It can connect us to something vast, addressing our need to be part of something larger than ourselves. It can teach us to be comfortable with mystery, with uncertainty, with not knowing. The key is approach. If we approach cosmic contemplation with fear, with a focus on isolation and meaninglessness, it can increase anxiety. But if we approach it with openness, with curiosity, with a willingness to feel awe and connection, it can bring peace. This is true not just for cosmic contemplation, but for life in general. Our experience is shaped not just by what happens to us, but by how we relate to what happens, by the perspective we bring, by the meaning we make. Black holes teach us that darkness and light are intertwined, that destruction and creation are part of the same cosmic dance, that endings are also beginnings. They teach us that we're small but connected, insignificant but precious, temporary but part of something eternal. And they teach us that the universe is far stranger and more wonderful than we can fully comprehend. And that's a source not of fear, but of endless wonder. As we come to the end of our journey, let yourself settle more deeply into rest. Your body is heavy, relaxed, supported. Your mind is quiet, spacious, at peace. You've traveled to the most extreme environments in the universe, to the event horizons of black holes, to the singularities at their centers, to the brilliant accretion disks that surround them. You've witnessed the deaths of stars and the births of black holes. You've felt the ripples of gravitational waves and contemplated the quantum whisper of Hawking radiation. And you've turned inward, exploring the psychology of cosmic contemplation, the fears and wonders that arise when we face the vastness of space, the practices that can help us find peace in that vastness. Now, let it all go. Let the concepts dissolve. Let the images fade. Return to simple awareness, simple presence, simple breath. You're here, now, in this moment. You're a temporary pattern in the cosmic flow, a brief eddy in the river of entropy, a way the universe has organized itself to become aware of itself. You're made of stardust, connected to everything, part of the vast web of matter and energy and space-time that encompasses all that is. And for this brief moment, this brief flicker of existence, you're here, breathing, aware, alive. That's enough. That's more than enough. That's everything. As you drift towards sleep, know that the universe holds you. The same gravity that creates black holes keeps you gently pressed against the earth. The same quantum fields that fill the vacuum of space fill every cell of your body. The same laws that govern the cosmos govern your heartbeat, your breath, your neural activity. You're not separate from the universe. You're an expression of it, a manifestation of its infinite creativity, a temporary form taken by the eternal dance of energy and matter. Rest in that knowledge. Rest in the cosmic embrace. Let yourself be held by the vastness, supported by the fabric of space-time itself. The black holes spin in their silent darkness, patient and eternal. The stars burn and die and are reborn. The galaxies wheel through space, following the curved paths laid down by gravity. And you rest, you breathe, you release into sleep. All is well. All is as it should be. The universe unfolds according to its own deep laws, and you're part of that unfolding, a necessary thread in the cosmic tapestry. Sleep now. Let go. Surrender to the darkness, not as something to fear, but as a place of rest, of renewal, of peace. Like matter crossing the event horizon, let yourself cross the threshold into sleep, into dreams, into the quiet darkness where consciousness dissolves and reforms. The cosmos continues its ancient dance. The black holes spin, the stars shine, and you rest in the heart of it all, held by gravity, connected by light, made of stardust. Sleep well, cosmic traveler. Sleep deeply. Sleep peacefully. And if you found some measure of peace in this journey, some perspective, some wonder, consider returning. Consider subscribing so we can explore more cosmic mysteries together, can find more ways to connect the vastness of space with the intimacy of human experience, can continue this shared journey of discovery and awe. But for now, simply rest. Simply breathe. Simply be. The universe is vast, but you are here. The cosmos is ancient, but this moment is now. The mysteries are deep, but your breath is simple, steady, present. Rest in that simplicity. Rest in that presence. Rest in the cosmic embrace. All is well. All is well. All is well. Silence. Deep, spacious silence. The silence of space. The silence of the mind at rest. The silence of the heart at peace. Let that silence hold you. Let it fill you. Let it
comfortable. You might be lying down, noticing how the surface beneath you quietly supports your weight. You might be seated, aware of the steadiness beneath your spine. There's nothing to do and nowhere to be. If you like, let the shoulders soften. The jaw loosen, the space around the eyes grow easy. You may notice a slow breath arriving on its own, cool at the tip of the nose, and then drifting out again, warm and unhurried. Perhaps another follows, as though the body knows the wire euro arriving, leaving, like a small tide. With each exhale, the day can rest a little farther from you. When it feels comfortable, allow the breath to settle into its own gentle rhythm. Unforced, effortless. We'll move together now, softly, into a quiet blue world below the waves, one of Earth's most mysterious and wondrous realms. Imagine, if you will, standing at the edge of the ocean on a clear, quiet evening. The sun has just dipped below the horizon, painting the sky in shades of deep purple and indigo. The water before you stretches endlessly, its surface catching the last glimmers of twilight. You know, as you stand there, that beneath those gentle waves lies a world so vast, so profound, that it contains more living space than all the forests, all the plains, all the mountains and valleys of every continent combined. The ocean covers nearly 3/4 of our planet's surface, and within its depths exists a realm that most humans will never see, a place where darkness reigns, where pressure builds to unimaginable intensities, where cold seeps into everything, and yet, remarkably, where life not only survives but flourishes in ways that seem almost magical. The deep sea. Even the words themselves carry a certain weight, a sense of mystery and wonder. When we speak of the deep sea, we're talking about the waters that lie beyond the reach of sunlight, below that bright, familiar surface zone where swimmers play and boats glide. We're venturing into regions where the sun's rays, no matter how brilliant they might be at the surface, simply cannot penetrate. This realm begins at around 200 meters below the surface, where the light starts to fade significantly, and it extends downward, deeper and deeper, through zones with names that sound like they belong in poetry rather than science. The Twilight Zone, or Mesopelagic, stretching from 200 to 1,000 meters. The Midnight Zone, or Bathypelagic, from 1,000 to 4,000 meters. The Abyssal Zone, from 4,000 to 6,000 meters. And finally, the Hadal Zone, named after Hades, the ancient Greek underworld, plunging into the deepest trenches, some reaching nearly 11,000 meters below the surface. To truly grasp the scale of these depths, consider this. If you were to take the tallest mountain on Earth, Mount Everest, with its peak reaching 8,849 meters above sea level, and somehow place it in the deepest part of the ocean, the Mariana Trench, the mountain's summit would still be covered by more than 2,000 meters of water. The deep sea is not just deep. It is profoundly, almost incomprehensibly deep. And within this vast vertical expanse, within this three-dimensional wilderness of water, creatures have evolved and adapted in ways that challenge our understanding of what life can be, what forms it can take, what strategies it can employ to persist in conditions that would seem, at first glance, utterly inhospitable. Let's pause here for a moment. Take another slow breath. Feel the air moving in and out of your lungs, so easy, so natural. Notice how your body knows exactly what to do, how to extract oxygen from the air, how to fuel every cell, every tissue, every organ. This automatic process, this gift of breath, connects you to every other breathing creature on this planet, including those in the deep sea, though their relationship with oxygen, with pressure, with temperature, differs dramatically from yours. Breathe in slowly, counting to 4. 1, 2, 3, 4. Hold gently for a moment. And release, counting to 6. 1, 2, 3, 4, 5, 6. Feel yourself sinking deeper into relaxation, just as we'll be sinking deeper into the ocean, exploring layer by layer, adaptation by adaptation, the remarkable ways that life has learned to thrive in the deep. The journey from the surface to the deep sea is not an abrupt transition but rather a gradual descent through changing conditions. At the surface, in what scientists call the epipelagic zone, sunlight floods the water, warming it, energizing it, powering the photosynthesis of countless microscopic plants called phytoplankton. These tiny organisms, invisible to the naked eye individually but visible in their billions as they color the water green or brown, form the foundation of the ocean's food web. They capture the sun's energy and transform it into living tissue, which is then consumed by small animals, which are in turn consumed by larger animals, and so on up the chain. The surface waters are relatively warm, their temperature varying with latitude and season but generally ranging from about 20 to 30 degrees Celsius in tropical regions. The pressure here is what we experience every day, 1 atmosphere, the weight of all the air above us pressing down at about 14.7 pounds per square inch, or 1 kilogram per square centimeter. But as you descend, everything begins to change. The light dims, the temperature drops, the pressure increases. For every 10 meters you descend, the pressure increases by approximately 1 atmosphere. At 100 meters depth, you're experiencing 10 atmospheres of pressure. At 1,000 meters, 100 atmospheres. At the deepest point in the ocean, the pressure reaches more than 1,000 atmospheres, or about 15,000 pounds per square inch. To put this in perspective, imagine the weight of a large elephant balanced on your thumbnail. That's the kind of pressure we're talking about. It's enough to crush most human-made vessels like tin cans, enough to compress air to a fraction of its surface volume, enough to fundamentally alter the behavior of water itself and everything dissolved or suspended within it. The temperature, too, drops steadily as you descend. In temperate and tropical oceans, there's often a layer called the thermocline, usually found between 100 and 500 meters depth, where the temperature decreases rapidly. Below this layer, in the deep sea proper, the water settles into a perpetual chill, hovering around 2 to 4 degrees Celsius, just above freezing. This cold is constant, unchanging, a feature as reliable as the darkness itself. There are no seasons in the deep sea, no summer warmth or winter chill, just an eternal, bone-deep cold that permeates everything. And then there's the light, or rather, the absence of it. Sunlight, as it enters the ocean, is absorbed and scattered by the water and the particles within it. Different wavelengths of light penetrate to different depths. Red light, with its longer wavelength, is absorbed first, disappearing within the first few meters. Orange follows, then yellow, then green. Blue light, with its shorter wavelength, penetrates the deepest, which is why the ocean appears blue when you look at it from above or swim in clear water. But even blue light has its limits. By the time you reach 200 meters, the light has dimmed to a twilight, a deep blue gloom where shapes become indistinct and colors fade to shades of gray. By 500 meters, the light is so faint that it's barely detectable, equivalent to the light of a single candle viewed from several kilometers away. And by 1,000 meters, the sunlight has been completely absorbed. Below this depth, the ocean is in absolute darkness, a blackness so complete that it's difficult for those of us who live in the lit world to truly imagine. Yet this darkness is not empty. It is not lifeless. In fact, the deep sea is home to an astonishing diversity of creatures, from the tiniest bacteria to some of the largest animals on Earth. And many of these creatures, perhaps most of them, have developed a remarkable ability, one that seems almost like magic, almost like something from a fairy tale. They can produce their own light. They are bioluminescent, living lanterns in the darkness, and their light serves purposes as varied as the creatures themselves. Some use it to hunt, to lure prey close enough to strike. Others use it to communicate, to find mates in the vast emptiness. Still others use it as a defense, to startle predators or to create decoys. And some, perhaps, use it simply because it's there, because evolution has given them this tool and they've found ways to make it work for them. Take another breath now. Slow and deep. Feel your body relaxing even further, your muscles softening, your mind quieting. As we continue our journey, we'll explore these adaptations in detail, we'll meet the creatures who possess them, and we'll come to understand how life, in its infinite creativity, has found ways to not just survive but to thrive in conditions that would seem impossible. The deep sea is not a barren wasteland. It is a thriving ecosystem, a world unto itself, and the creatures who live there are among the most fascinating, most beautifully adapted organisms on our planet. Now, let's descend together into the twilight zone, that layer between 200 and 1,000 meters, where the last traces of sunlight mingle with the first glimmers of bioluminescence, where the boundary between the lit world and the dark world blurs and shifts. This is where our story truly begins, in the dim blue depths where creatures have learned to make their own light, where eyes have grown large to capture every available photon, where bodies have become transparent or dark to avoid detection, where the rules of survival are written in light and shadow, in chemistry and physics, in the ancient language of adaptation that all life speaks, whether in the depths of the ocean or the heights of the mountains, whether in the heat of the desert or the cold of the polar ice. Life finds a way. Life adapts. Life persists. And in the deep sea, life has found some of its most extraordinary expressions. Let yourself sink deeper into comfort now, deeper into relaxation, as we sink deeper into the ocean, exploring the first of many remarkable adaptations that allow creatures to thrive in the deep. We'll start with light, with bioluminescence, with the ability to create illumination in a world of darkness. And as we explore this phenomenon, as we learn about the chemistry and the evolution and the purposes of biological light, you might find your own thoughts becoming clearer, your own inner light growing brighter, even as your body relaxes more and more, preparing for the deep, restorative rest that awaits you at the end of our journey together. The ocean is calling. The deep is waiting. And the creatures there have stories to tell, stories written in their very bodies, in their adaptations, in the ways they've learned to live in a world so different from ours. Let's listen to those stories now. Let's learn from them. Let's allow them to carry us gently into sleep, into dreams, into the peaceful darkness that mirrors the darkness of the deep sea, where rest and renewal happen in their own time, in their own way, just as life in the deep sea unfolds in its own time, in its own way, perfectly adapted, perfectly suited, perfectly at home in the darkness. Breathe, relax, and let's continue our descent. In the deep sea, where sunlight fades to nothing and darkness becomes the default state of existence, you might expect to find a world devoid of light, a realm of pure blackness where vision serves no purpose and eyes become vestigial, useless remnants of a brighter past. But the reality is quite the opposite. The deep sea is, in fact, filled with light. Not the steady, reliable light of the sun, but rather a different kind of light entirely, a light that flickers and flashes, that glows and pulses, that appears suddenly in the darkness and then vanishes just as quickly. This is bioluminescence, the production of light by living organisms, and it is one of the most widespread and important adaptations in the deep sea. Bioluminescence is not unique to the ocean. You've probably seen it yourself, perhaps on a summer evening when fireflies blink their yellow-green lights in the gathering dusk, each flash a signal, a message sent to potential mates. Or maybe you've noticed the faint glow of certain mushrooms in a dark forest, their caps emitting a ghostly green light that seems almost supernatural. But while bioluminescence occurs on land, it is relatively rare, limited to a few groups of insects, some fungi, and a handful of other organisms. In the ocean, however, bioluminescence is everywhere. It is, in fact, one of the most common adaptations in the marine environment, particularly in the deep sea. Scientists estimate that in the mesopelagic zone, the twilight region between 200 and 1,000 meters, approximately 76% of all animals are capable of producing light. Think about that for a moment. 3 out of every 4 creatures you might encounter in this zone can create their own illumination. And this percentage remains remarkably consistent as you descend deeper. Even in the bathypelagic zone, the midnight zone below 1,000 meters where no sunlight ever penetrates, the majority of animals are bioluminescent. This prevalence suggests that bioluminescence is not just a curious quirk of evolution but rather a fundamental adaptation, a crucial tool for survival in the deep sea. But what exactly is bioluminescence? How does it work? The answer lies in chemistry, in a reaction that was first described in detail by a French scientist named Raphael Dubois in 1887. Dubois was studying bioluminescent beetles and marine clams, and he discovered that the light they produced required 2 key components, which he named luciferin and luciferase. Luciferin, from the Latin word for light bearer, is a molecule that, when oxidized, releases energy in the form of light. Luciferase is an enzyme that catalyzes this reaction, speeding it up and making it more efficient. When luciferin combines with oxygen in the presence of luciferase, it undergoes a chemical transformation, and in the process, it emits photons, particles of light. The beauty of this reaction is its efficiency. Unlike the light produced by an incandescent bulb, which wastes most of its energy as heat, bioluminescence is what scientists call cold light. Nearly all of the energy released in the reaction is converted directly into light, with very little heat produced. This efficiency is crucial for deep-sea organisms, who live in an environment where energy is scarce and every calorie must be carefully conserved. Producing light without producing heat allows these creatures to communicate, hunt, and defend themselves without wasting precious resources. Now, here's something fascinating. The luciferin and luciferase that Dubois discovered are not universal. Different groups of organisms have evolved different versions of these molecules, different chemical pathways to produce light. In fact, scientists have identified at least 8 different types of luciferin used by various organisms, and each type requires its own specific luciferase enzyme. This diversity suggests that bioluminescence has evolved independently many times throughout the history of life on Earth. It's an example of what biologists call convergent evolution, where different lineages arrive at similar solutions to similar problems. In the case of the deep sea, the problem is darkness, and the solution, arrived at again and again by different groups of animals, is the ability to make light. Let's take a moment to breathe here. Inhale slowly, feeling your chest expand, your lungs fill. Hold for just a moment. And exhale, releasing any tension, any thoughts that might be pulling at your attention. As you breathe, imagine the chemical reactions happening inside your own body, the countless molecular interactions that keep you alive, that allow you to breathe, to think, to feel. Bioluminescence is just one of many remarkable chemical processes that life has discovered, one of many ways that organisms have learned to harness the power of chemistry to survive and thrive. And as we explore this phenomenon further, as we learn about the many ways that deep-sea creatures use their light, you might find yourself marveling at the creativity of evolution, at the endless ingenuity of life. The colors of bioluminescence in the deep sea are not random. Most bioluminescent organisms produce blue or blue-green light, with wavelengths around 470 to 490 nanometers. This is not a coincidence. Blue light travels farther in seawater than any other color. Red light, as we mentioned earlier, is absorbed quickly, disappearing within the first few meters. Green light penetrates a bit deeper, but it too is eventually absorbed. Blue light, however, can travel for hundreds of meters in clear ocean water before being absorbed or scattered. For creatures trying to communicate or hunt in the deep sea, blue light is simply the most practical choice. It's the color that will be seen from the greatest distance, the color that will carry their message or their lure the farthest. But there are exceptions. Some deep-sea creatures produce red light, and this adaptation is particularly clever. Most deep-sea animals have eyes that are sensitive only to blue light. They've evolved to detect the wavelengths that are most common in their environment, the blue of bioluminescence and the faint blue of residual sunlight in the upper mesopelagic zone. Red light, to these creatures, is invisible. It's as if it doesn't exist. So a predator that can produce red light has, in effect, a secret flashlight, a way to illuminate its prey without the prey knowing it's being watched. The dragonfish, a group of deep-sea predators, have evolved this ability. They have special organs beneath their eyes that produce red light, and they have eyes that can detect this red light. They can shine their red beam on potential prey, see them clearly, and approach without being detected. It's like having night vision goggles in a world where everyone else is blind to infrared. Another fascinating variation is found in the firefly squid, Wattersonia scintillans, which lives in the waters off Japan. These small squid, only about 3 inches long, are covered with thousands of tiny light-producing organs called photophores. They can control these photophores individually, creating complex patterns of light across their bodies. During the breeding season, which occurs in spring, millions of these squid gather in Toyama Bay, and the water becomes filled with their blue bioluminescence, creating a spectacle so beautiful that it has become a tourist attraction. People come from around the world to witness this natural light show, to see the water glowing with the combined light of countless squid, each one flashing and pulsing in its own rhythm, yet somehow creating a coordinated display that seems almost choreographed. The purposes of bioluminescence in the deep sea are as varied as the creatures that produce it. Let's explore some of these purposes, starting with one of the most important, finding a mate. In the vast, dark expanse of the deep sea, where individuals of the same species might be separated by kilometers of empty water, finding a mate is a significant challenge. Bioluminescence provides a solution. Many species have evolved species-specific light patterns, unique signatures that allow individuals to identify potential mates of their own kind. It's like having a secret code, a password that only members of your species know. The anglerfish, which we'll discuss in more detail later, provides a dramatic example of this. Female anglerfish are much larger than males, sometimes hundreds of times larger. The females have a bioluminescent lure that they use to attract prey, but this lure also serves to attract males. When a tiny male anglerfish encounters a female in the darkness, he bites onto her body and never lets go. Over time, his body fuses with hers, his circulatory system connecting to hers, until he becomes essentially a parasitic appendage, providing sperm whenever she needs it. It's a bizarre and extreme adaptation, but it solves the problem of finding a mate in an environment where encounters are rare. Other creatures use bioluminescence for courtship displays. The ostracods, tiny crustaceans sometimes called sea fireflies, are famous for this. Males release clouds of bioluminescent chemicals into the water while swimming in specific patterns, creating trails of light that females can see from a distance. Each species has its own unique pattern, its own signature display. Some swim in spirals, others in zigzags, still others in straight lines with regular pulses of light. Females watch these displays and choose mates based on the quality of the performance. It's underwater fireworks, a light show designed to impress, to attract, to signal fitness and health. Bioluminescence is also used for hunting, for attracting prey close enough to capture. The anglerfish, again, is the most famous example. The female anglerfish has a modified dorsal fin spine that extends forward over her head like a fishing rod, and at the tip of this rod is a fleshy bulb called the esker. Inside the esker live colonies of bioluminescent bacteria, and these bacteria produce a steady glow. The anglerfish can control the blood flow to the esker, effectively turning the light on and off, and she can move the esker around, dangling it in front of her enormous mouth. Small fish and crustaceans, attracted by the light, swim closer to investigate, thinking perhaps that they've found a meal of their own, a small glowing organism that they can eat. But as they approach, the anglerfish strikes, her jaws snapping shut with incredible speed, and the prey becomes the meal instead of the diner. This relationship between the anglerfish and her bacteria is an example of symbiosis, a close relationship between two different species where both benefit. The bacteria get a safe place to live, protected inside the anglerfish's esker, and they get a steady supply of nutrients from the anglerfish's blood. In return, they provide light, which the anglerfish uses to hunt. It's a partnership, a collaboration between two very different forms of life, and it's one of many such partnerships in the deep sea. In fact, some scientists estimate that about 10% of bioluminescent deep-sea fish rely on symbiotic bacteria for their light, rather than producing it themselves. The rest have evolved their own light-producing organs, their own photophores, which contain the luciferin and luciferase needed to generate light. But bioluminescence isn't just for attracting things. It's also used to repel them, to defend against predators. Many deep-sea creatures, when threatened, release clouds of bioluminescent material into the water. This serves several purposes. First, it can startle the predator, creating a sudden bright flash that temporarily blinds or confuses it, giving the prey a chance to escape. Second, it can act as a decoy, a false target that the predator attacks while the real prey swims away in the opposite direction. And third, it can act as what scientists call a burglar alarm, attracting larger predators to the scene. The idea is that if you're being attacked by a predator, you can use your bioluminescence to attract an even bigger predator, one that might eat your attacker. It's a risky strategy, but in the deep sea, where options are limited, it can be effective. The vampire squid, Vampiroteuthis infernalis, uses this strategy. Despite its fearsome name, the vampire squid is actually a relatively small and harmless creature, feeding primarily on marine snow, the constant rain of dead organic matter that falls from the upper layers of the ocean. But when threatened, the vampire squid can release a cloud of bioluminescent mucus from the tips of its arms. This mucus glows for several minutes, creating a glowing cloud in the water that distracts the predator while the squid escapes. It's like a smoke bomb, but instead of smoke, it's light. And unlike the ink that shallow water squid release, which would be invisible in the darkness of the deep sea, this bioluminescent mucus is highly visible, highly effective. Another defensive use of bioluminescence is counterillumination, a form of camouflage that's particularly clever. Many deep-sea fish and squid have photophores on their undersides, on their bellies. These photophores produce a light that matches the color and intensity of the faint downwelling light from above. When a predator looks up from below, it sees not a dark silhouette against the lighter water above, but rather a uniform glow that blends in with the background. The prey becomes effectively invisible, hidden not by darkness but by light. This strategy is so effective that it's been adopted by many different groups of deep-sea animals, from fish to squid to shrimp. It's another example of convergent evolution, different lineages arriving at the same solution to the same problem. Some creatures take counterillumination even further. The Hawaiian bobtail squid, Euprymna scolops, which lives in shallow waters but faces similar challenges, has a special light organ on its underside that houses colonies of bioluminescent bacteria. The squid can control the intensity of the light by adjusting the blood flow to the organ and by using a kind of shutter made of tissue that can cover or uncover the light. The squid even has a light sensor on its back that measures the intensity of the moonlight or sunlight from above, and it adjusts its belly light to match. If a cloud passes over the moon, dimming the light from above, the squid dims its belly light accordingly. It's an incredibly sophisticated system, a real-time camouflage that adapts to changing conditions. Let's pause again for a moment. Take a deep breath in, filling your lungs completely. Hold it gently. And release, letting all the air flow out, letting your body sink deeper into relaxation. As you breathe, think about the complexity of these adaptations, the intricate systems that have evolved over millions of years to allow creatures to survive in the deep sea. Each adaptation is a solution to a problem, each feature a response to a challenge. And together, these adaptations create a web of interactions, a community of organisms that depend on each other, that compete with each other, that eat and are eaten, that reproduce and die, all in the darkness of the deep sea, all using light as a tool, a weapon, a signal, a disguise. The evolution of bioluminescence is a story that spans hundreds of millions of years. The earliest bioluminescent organisms were probably bacteria, single-celled creatures that developed the ability to produce light as a byproduct of their metabolism. These bacteria still exist today, and they're found throughout the ocean, from the surface to the deepest trenches. Some float freely in the water, others attach to particles of organic matter, and still others, as we've seen, live in symbiotic relationships with larger animals. Over time, other organisms evolved their own bioluminescent systems, sometimes by acquiring the genes for luciferin and luciferase from bacteria through a process called horizontal gene transfer, and sometimes by evolving these systems independently. The result is a remarkable diversity of bioluminescent organisms in the ocean. Among the cnidarians, the group that includes jellyfish and corals, more than 97% of species observed in the deep sea are bioluminescent. Among the ctenophores, the comb jellies, the percentage is similarly high. Among the crustaceans, which include shrimp, crabs, and copepods, bioluminescence is common, though not universal. Among the fish, the percentage varies depending on depth and habitat, but in the mesopelagic zone, the majority of fish species are bioluminescent. And among the cephalopods, the group that includes squid and octopuses, bioluminescence is widespread, with many species having elaborate arrays of photophores that they can control with remarkable precision. This prevalence of bioluminescence in the deep sea tells us something important about the environment there. It tells us that light, even in a place where sunlight never reaches, is still a valuable resource, still a useful tool. It tells us that vision, far from being useless in the darkness, is actually crucial for survival. And it tells us that the deep sea, despite its darkness, is not a place of sensory deprivation, but rather a place of sensory richness, where creatures have evolved exquisitely sensitive eyes to detect the faintest glimmers of light, where they've developed complex behaviors to use light for communication and hunting and defense, where they've created, in effect, their own illuminated world in the midst of darkness. As we continue our journey deeper into the ocean, as we explore other adaptations that allow creatures to thrive in the deep sea, keep in mind this fundamental truth: life is creative. Life is adaptable. Life finds ways to persist, to flourish, even in the most challenging environments. The deep sea is not a hostile wasteland but a thriving ecosystem, and the creatures there are not struggling to survive but are, in many ways, perfectly suited to their environment, perfectly adapted to the darkness, the cold, the pressure. They are at home in the deep, just as we are at home in our own environments, and their adaptations, their strategies, their solutions to the challenges they face, are testaments to the power of evolution, to the endless creativity of life. Breathe deeply now. Feel the calm spreading through your body, the relaxation deepening with each breath. As we move forward, we'll explore another crucial adaptation, one that's perhaps even more fundamental than bioluminescence, one that allows creatures to withstand the crushing pressure of the deep sea, to maintain their cellular functions, to keep their proteins and enzymes working in conditions that would destroy most forms of life. We'll learn about the biochemical adaptations that make life possible in the deep, about the molecules and mechanisms that protect cells from pressure, about the ways that evolution has solved one of the most challenging problems in the ocean. And as we learn, as we understand, you might find yourself drifting, your thoughts becoming softer, your awareness turning inward, your body preparing for the deep, restorative sleep that awaits. The deep sea is calling, the darkness is welcoming, and the creatures there have more stories to tell, more secrets to share, more wonders to reveal in the profound darkness, and that its tissues were filled with Tmao to help it survive. There's a limit to how much Tmao can help, though. At the very deepest depths, even Tmao can't fully protect proteins from pressure. Scientists have calculated that there's a theoretical maximum depth for fish, based on the amount of Tmao they can accumulate and the pressure tolerance of their proteins. This maximum is somewhere around 8,000 to 8,500 meters. Below this depth, the pressure is simply too great for fish to survive, even with all their adaptations. And indeed, the deepest living fish ever recorded, a snailfish from the genus Pseudoloparis, was found at a depth of about 8,000 meters in the Mariana Trench. Below this depth, the only vertebrates found are much simpler organisms, like amphipods and sea cucumbers, which have different body plans and different strategies for dealing with pressure. But it's not just proteins and membranes that need to be protected from pressure. Entire cellular processes, entire metabolic pathways, need to function properly under high pressure. And deep-sea organisms have evolved adaptations at every level, from the molecular to the cellular to the organismal, to make this possible. For example, the enzymes involved in energy production, in the breakdown of glucose and the synthesis of ATP, the molecule that powers most cellular processes, have been fine-tuned to work efficiently under pressure. The ion pumps that maintain the proper concentrations of sodium, potassium, and other ions inside and outside cells have been adapted to function under pressure. Even the DNA replication machinery, the complex of enzymes that copies the genetic material when a cell divides, has been adjusted to work properly in the deep sea. One particularly interesting adaptation involves the way that deep-sea organisms regulate their metabolism. Metabolism is the sum of all the chemical reactions that occur in an organism, and it requires energy. In most organisms, metabolic rate is closely tied to temperature. Warmer temperatures speed up chemical reactions, increasing metabolic rate, while cooler temperatures slow them down. But in the deep sea, where temperatures are constantly cold, hovering around 2 to 4 degrees Celsius, metabolic rates are generally low. Deep-sea organisms tend to be slow-moving, slow-growing, and long-lived. They conserve energy, living life in the slow lane. This slow metabolism is partly a response to the scarcity of food in the deep sea. In the surface waters, where sunlight powers photosynthesis, there's an abundance of food. Phytoplankton grow rapidly, zooplankton feed on them, small fish feed on the zooplankton, and so on up the food chain. But in the deep sea, there's no photosynthesis. The only food that reaches the deep sea is what falls from above, the constant rain of dead organic matter called marine snow. This marine snow consists of dead plankton, fecal pellets, discarded mucus-feeding webs, and other organic debris, and it falls slowly through the water column, taking weeks or even months to reach the deep sea floor. By the time it arrives, much of it has been consumed or decomposed by organisms in the upper layers, so what reaches the deep sea is relatively sparse and low in nutritional value. Given this scarcity of food, deep-sea organisms can't afford to waste energy. They need to be efficient, to conserve every calorie. And one way to do this is to have a slow metabolism, to reduce the rate at which they burn energy. This means moving slowly, growing slowly, reproducing infrequently. It means having a body that's adapted for efficiency rather than speed. And it means having biochemical pathways that are optimized for low energy expenditure. Scientists have studied the metabolic rates of deep-sea fish and compared them to shallow water fish, and the differences are striking. Deep-sea fish have much lower metabolic rates, sometimes only a fraction of what you'd expect for a fish of their size living in warmer, shallower water. Their muscles have fewer mitochondria, the cellular structures that produce energy, and the mitochondria they do have are less active. Their hearts beat more slowly. Their gills extract oxygen from the water less vigorously. Everything about their physiology is tuned for low energy consumption. But this doesn't mean that deep-sea fish are sluggish or incapable of movement. When they need to, when they're hunting or escaping from a predator, they can move quickly, at least for short bursts. But most of the time, they're conserving energy, drifting slowly through the water, waiting for food to come to them rather than actively searching for it. It's a strategy that works in an environment where food is scarce and energy is precious. Take another deep breath now. Feel your body relaxing even more, your muscles softening, your mind quieting. As you breathe, think about the deep-sea creatures we've been discussing, about their slow, patient lives in the cold, dark depths. There's something almost meditative about their existence, something peaceful in their slow movements, their low metabolism, their patient waiting. They're not rushing, not hurrying, not wasting energy on unnecessary activity. They're simply being, existing in harmony with their environment, perfectly adapted to the conditions they face. And perhaps there's a lesson in that for us, a reminder that sometimes the best strategy is to slow down, to conserve our energy, to be patient and wait for the right moment. As we continue our journey through the deep sea, as we explore more adaptations and meet more creatures, keep in mind this theme of efficiency, of conservation, of doing more with less. The deep sea is a place where resources are limited, where every adaptation is a response to scarcity, where survival depends on being smart, being efficient, being perfectly tuned to the environment. And the creatures there, with their pressure-resistant proteins, their fluid membranes, their tmao-filled tissues, their slow metabolisms, are masterpieces of adaptation, examples of evolution at its finest. Breathe, relax, and let's continue deeper into the realm of vision, into the world of eyes adapted to darkness, into the fascinating ways that deep-sea creatures have learned to see in a place where there's almost nothing to see. In the deep sea, where light is scarce or absent, you might expect that eyes would be useless, that vision would be abandoned in favor of other senses. And indeed, some deep-sea creatures have reduced eyes or no eyes at all, relying instead on touch, smell, or the detection of vibrations to navigate and find food. But surprisingly, many deep-sea creatures have eyes, and not just any eyes, but some of the most remarkable, most specialized eyes in the animal kingdom. These eyes are adapted to detect the faintest glimmers of light, to distinguish between different sources of illumination, to see in conditions that would leave us completely blind. They are testaments to the importance of vision even in the darkest places on Earth. Let's start by considering what it means to see in the deep sea. In the mesopelagic zone, the twilight zone between 200 and 1,000 meters, there's still some residual sunlight, though it's extremely faint. By the time sunlight has penetrated to 500 meters, it's been reduced to about 1/10 millionth of its intensity at the surface. That's roughly equivalent to the light of a single candle viewed from several kilometers away. And this light is almost entirely blue, because blue wavelengths penetrate water more effectively than other colors. So any creature trying to see by sunlight in the mesopelagic zone needs eyes that are extremely sensitive to blue light, eyes that can detect and process the tiniest amounts of photons. Below 1,000 meters, in the bathypelagic zone and deeper, there's no sunlight at all. The only light comes from bioluminescence, from the flashes and glows produced by other organisms. This light is also predominantly blue, for the same reason that sunlight in the mesopelagic zone is blue. Blue light travels farthest in water. So deep-sea eyes need to be sensitive to blue light, whether that light comes from the sun or from bioluminescence. How do you build an eye that's sensitive enough to see in near total darkness? The answer involves several adaptations, working together to maximize the amount of light captured and the efficiency with which that light is converted into neural signals. Let's explore these adaptations one by one. First, size matters. A larger eye can capture more light than a smaller eye, simply because it has a larger aperture, a larger opening through which light can enter. This is the same principle that applies to camera lenses and telescopes. Bigger is better when it comes to gathering light. And indeed, many deep-sea creatures have disproportionately large eyes relative to their body size. The giant squid, Architeuthis dux, has the largest eyes of any animal on Earth, with a diameter of up to 27 centimeters, about the size of a dinner plate. These enormous eyes are thought to be adapted for detecting the faint bioluminescence produced by the movements of the squid's main predator, the sperm whale, at distances of more than 100 meters. But having large eyes comes with costs. Eyes are expensive to build and maintain, requiring a lot of energy and resources. And large eyes are heavy, which can be a disadvantage for a creature that needs to be neutrally buoyant, to float effortlessly in the water column without sinking or rising. So there's a trade-off between the benefits of large eyes and the costs, and different species have struck different balances depending on their lifestyles and ecological niches. Some deep-sea fish have found a clever solution to this trade-off. Instead of having large, spherical eyes like most animals, they have tubular eyes, eyes that are shaped like cylinders or barrels. These tubular eyes are pointed upward, looking toward the surface, and they have large lenses at the front that gather light from above. The advantage of this design is that it allows for a large lens, which gathers a lot of light, without requiring a large, heavy eyeball. The tubular shape is more compact, more efficient, than a spherical shape for gathering light from a specific direction. Barrel-eye fish, also known as spookfish, are famous for their tubular eyes. These fish, which live at depths of around 600 to 800 meters, have transparent heads, and their tubular eyes are visible inside, pointing upward. The eyes are filled with a clear, jelly-like substance, and they're incredibly sensitive to light. The fish use these eyes to look upward, searching for the silhouettes of prey against the faint downwelling light from the surface. When they spot a potential meal, they rotate their eyes forward and swim upward to intercept it. It's a remarkable adaptation, a specialized eye design for a specific hunting strategy. Another adaptation for increasing light sensitivity is to have a larger pupil, the opening in the center of the eye through which light enters. A larger pupil allows more light to reach the retina, the light-sensitive tissue at the back of the eye. Many deep-sea fish have very large pupils relative to the size of their eyes, maximizing the amount of light that can enter. Some species have pupils that are so large that they can't be closed, meaning the eye is always wide open, always gathering as much light as possible. But gathering light is only the first step. Once light enters the eye, it needs to be focused onto the retina, and then the retina needs to convert that light into neural signals that the brain can interpret. Both of these processes have been optimized in deep-sea eyes. The lens of the eye is responsible for focusing light onto the retina. In most animals, the lens is a flexible structure that can change shape to focus on objects at different distances. But in fish, The lens is rigid and spherical, and focusing is achieved by moving the lens forward or backward, closer to or farther from the retina. Deep-sea fish have lenses that are optimized for the wavelengths of light they're most likely to encounter, which is blue light. The refractive index of the lens, the degree to which it bends light, is tuned to focus blue light precisely onto the retina. The retina itself is where the magic happens, where light is converted into neural signals. The retina contains photoreceptor cells, specialized cells that contain light-sensitive pigments called opsins. When a photon of light hits an opsin molecule, it triggers a cascade of chemical reactions that ultimately result in an electrical signal being sent to the brain. There are two main types of photoreceptor cells in most animals: rods, which are sensitive to low light levels and are used for night vision, and cones, which are less sensitive but can detect color and are used for day vision. In deep-sea fish, the retina is dominated by rods. Cones are rare or absent because there's not enough light for color vision to be useful. The rods in deep-sea fish are often larger and more densely packed than in shallow water fish, maximizing the number of photons that can be captured. And the opsins in these rods are tuned to be most sensitive to blue light, matching the wavelengths that are most common in the deep sea. But some deep-sea fish have taken this adaptation even further. They have what's called a banked retina, where the rods are arranged in multiple layers, stacked on top of each other. This increases the optical path length, the distance that light travels through the photoreceptor layer, which increases the probability that a photon will be absorbed and detected. It's like having multiple chances to catch the same photon. Some deep-sea fish have retinas with 6, 8, or even more layers of rods, creating an incredibly sensitive light-detecting system. The escalar, Lepidosibium flavobruneum, a deep-sea fish that lives at depths of 200 to 500 meters and migrates to the surface at night, has a banked retina with 6 to 8 layers of rods. Scientists have studied the vision of this fish in detail, and they've found that it has extremely high sensitivity to light, able to detect light levels that are far below what humans can see. But this sensitivity comes at a cost. The escalar has relatively poor spatial resolution, meaning it can't see fine details very well. Its vision is optimized for detecting the presence of light, for seeing whether something is there or not, rather than for seeing what that something looks like in detail. This makes sense for a fish that lives in dim light and needs to detect the silhouettes of prey against the faint background light from above. Another fascinating adaptation in deep-sea eyes is the presence of a tapetum, a reflective layer behind the retina that bounces light back through the photoreceptors, giving them a second chance to absorb photons. You've probably seen the effect of a tapetum if you've ever shone a flashlight at a cat or dog at night and seen their eyes glow. That glow is light reflecting off the tapetum. Many deep-sea fish have tapeta, and they serve the same purpose, to increase light sensitivity by reflecting light back through the retina. Some deep-sea creatures have even more unusual eye adaptations. The cockeyed squid, Histiotoothes heteropsis, has two eyes of very different sizes. One eye is large and bulbous, pointing upward, while the other is small and normal-sized, pointing downward. Scientists have studied the behavior of these squid using underwater video, and they found that the squid typically swims with its body tilted so that the large eye is always oriented upward and the small eye downward. The large eye is adapted for detecting the faint downwelling sunlight and the silhouettes of prey or predators against that light. The small eye is adapted for detecting bioluminescence in the darker water below. It's a remarkable example of asymmetry, of having two eyes specialized for different tasks, and it shows how evolution can create unexpected solutions to the challenges of life in the deep sea. The giant squid, which we mentioned earlier, has eyes that are not only enormous but also highly specialized. Recent research has suggested that these giant eyes are not primarily for detecting prey or mates, which would be too small to see at great distances, but rather for detecting very large objects, specifically sperm whales, which are the giant squid's main predators. Sperm whales hunt in the deep sea, diving to depths of 1,000 meters or more to feed on squid. As they swim through the water, they disturb bioluminescent plankton, creating a faint glow around their bodies. The giant squid's huge eyes, with their enormous lenses and sensitive retinas, are thought to be able to detect this glow from distances of more than 100 meters, giving the squid enough warning to escape before the whale gets too close. It's a predator-prey arms race, with the squid evolving ever larger eyes to detect the whale earlier, and the whale evolving better hunting strategies to catch the squid despite its vigilance. Let's pause here for a moment and take a breath. Inhale slowly, feeling the air fill your lungs, feeling your chest expand. Hold for a moment, and exhale, releasing any tension, any thoughts that might be pulling at your attention. As you breathe, think about the eyes we've been discussing, about the incredible adaptations that allow creatures to see in near total darkness. These eyes are marvels of evolution, finely tuned instruments for detecting the faintest glimmers of light. And they remind us that even in the darkest places, even in environments that seem utterly inhospitable, life finds a way to perceive, to sense, to interact with the world. Vision, that most precious of senses, persists even in the deep sea, adapted and refined to meet the challenges of that unique environment. As we continue our journey, we'll explore other aspects of deep-sea life, other adaptations and strategies that allow creatures to thrive in the darkness. We'll learn about metabolism and energy conservation, about feeding strategies and reproductive behaviors, about the complex web of interactions that connects all the creatures of the deep sea into a functioning ecosystem. And as we learn, as we understand, you might find yourself drifting deeper into relaxation, your body becoming heavier, your mind becoming quieter, your thoughts becoming softer and more distant, like the faint light in the deep sea, present but barely perceptible, there but not demanding attention. The deep sea is a place of wonders, a place of mysteries, a place where life has pushed the boundaries of what's possible. And the creatures there, with their remarkable eyes, their pressure-resistant proteins, their bioluminescent displays, are ambassadors from that world, messengers bringing news of a realm that most of us will never visit but can still appreciate, can still marvel at, can still learn from. Let's continue our exploration, deeper and deeper, into the heart of the ocean, into the realm where darkness and light dance together, where pressure and life coexist, where adaptation and survival are written in every cell, every molecule, every creature. Breathe, relax, and let's descend further into the deep. In the deep sea, where food is scarce and energy is precious, every aspect of an organism's biology is shaped by the need to conserve resources. We've already discussed how deep-sea creatures have slow metabolisms, how they move slowly and grow slowly, how they're adapted for efficiency rather than speed. But let's explore this theme more deeply, looking at the specific strategies that deep-sea creatures use to minimize their energy expenditure and maximize their chances of survival in an environment where every calorie counts. One of the most striking features of many deep-sea creatures is their body composition. Unlike the muscular, dense bodies of many shallow water fish, deep-sea fish often have soft, flabby bodies with watery flesh and weak bones. Their muscles are poorly developed, their skeletons are thin and fragile, and their bodies are often gelatinous, filled with water and low-density compounds. This might seem like a disadvantage, but in the deep sea, it's actually an adaptation. The reason has to do with buoyancy. In the ocean, an organism can sink, float, or remain neutrally buoyant, neither sinking nor floating. Neutral buoyancy is ideal because it allows the organism to maintain its position in the water column without expending energy swimming. But achieving neutral buoyancy is not easy. Most biological tissues, like muscle and bone, are denser than seawater, so they tend to sink. To counteract this, many fish have a swim bladder, a gas-filled sac that provides buoyancy. But swim bladders have a problem in the deep sea. As pressure increases with depth, the gas in the swim bladder is compressed, reducing its volume and its buoyancy. To maintain neutral buoyancy, the fish would need to constantly add more gas to the swim bladder, which requires energy. Deep-sea fish have largely abandoned swim bladders. Instead, they achieve neutral buoyancy by reducing their overall density. They do this by having watery, gelatinous tissues that are less dense than muscle, by having thin, lightweight bones, and by accumulating low-density compounds like lipids and oils. Some deep-sea fish have large livers filled with oil, which provides buoyancy. Others have gelatinous layers under their skin or in their body cavities. The result is a body that's neutrally buoyant without the need for a swim bladder, without the need to expend energy maintaining buoyancy. This strategy has a trade-off, though. Gelatinous, watery bodies are not good for fast swimming. They lack the muscle mass and the structural rigidity needed for powerful, sustained movement. But in the deep sea, where food is scarce and encounters with prey or predators are infrequent, fast swimming is not as important as energy conservation. It's better to drift slowly, to wait patiently, to conserve energy until the moment when action is necessary. And when that moment comes, when a prey item appears or a predator threatens, deep-sea fish can still move quickly for short bursts, using what muscle they have to strike or escape. The gelatinous bodies of deep-sea creatures also have another advantage: they're less affected by pressure. Solid tissues, like muscle and bone, are relatively incompressible, but they can still be affected by pressure in subtle ways, as we discussed earlier. Gelatinous tissues, which are mostly water, are even less affected by pressure because water is nearly incompressible. So a gelatinous body is, in a sense, a pressure-neutral body, one that doesn't require special adaptations to withstand the crushing weight of the deep sea. Many deep-sea jellyfish and ctenophores, the comb jellies, have taken this strategy to an extreme. Their bodies are more than 95% water, with only a thin layer of tissue providing structure. They drift through the water like living ghosts, their translucent bodies nearly invisible, their movements slow and graceful. They feed on small prey that they encounter by chance, capturing them with tentacles or sticky surfaces, and they expend minimal energy in the process. It's a lifestyle that's perfectly suited to the deep sea, where patience and efficiency are more valuable than speed and strength. Another strategy for conserving energy in the deep sea is to reduce metabolic rate, to slow down all the chemical processes that keep an organism alive. We've mentioned this before, but let's look at it in more detail. Metabolic rate is the rate at which an organism consumes energy, and it's influenced by many factors, including body size, temperature, and activity level. In general, smaller organisms have higher metabolic rates per unit of body mass than larger organisms, and warmer organisms have higher metabolic rates than cooler organisms. In the deep sea, where temperatures are constantly cold, metabolic rates are generally low. But deep-sea organisms have evolved metabolic rates that are even lower than you'd expect based on temperature alone. Their cells are less active, their enzymes work more slowly, their hearts beat less frequently, their gills extract oxygen less vigorously. Everything is tuned for low energy consumption. Scientists have measured the metabolic rates of deep-sea fish and compared them to shallow water fish of similar size, and the differences are dramatic. A deep-sea fish might have a metabolic rate that's only 10 to 20% of what you'd expect for a shallow water fish of the same size living at the same temperature. This means the deep-sea fish needs only a fraction of the food that the shallow water fish needs to survive. In an environment where food is scarce, this is a huge advantage. But how do deep-sea fish achieve such low metabolic rates? Part of the answer lies in their muscles. Muscles are one of the most metabolically active tissues in the body, consuming a large fraction of the energy an organism uses. Deep-sea fish have less muscle mass than shallow water fish, and the muscle they do have is less active. Their muscle cells contain fewer mitochondria, the cellular structures that produce energy, and the mitochondria they do have are less densely packed with the enzymes needed for energy production. The result is a muscle that's capable of movement but that consumes very little energy when at rest. The hearts of deep-sea fish are also adapted for low energy consumption. The heart is a muscle, and like other muscles, it consumes energy with every beat. Deep-sea fish have hearts that beat more slowly than those of shallow water fish, reducing the energy cost of circulation. And their blood has a lower oxygen carrying capacity, which might seem like a disadvantage but is actually consistent with their low metabolic rate. If you're not consuming much oxygen, you don't need to transport much oxygen, so you can get by with less hemoglobin, the protein that carries oxygen in the blood. Even the brains of deep-sea fish are adapted for low energy consumption. The brain is one of the most metabolically expensive organs in the body, consuming a large fraction of the energy an organism uses even when at rest. Deep-sea fish have relatively small brains compared to shallow water fish, and their brains are less active. This doesn't mean they're less intelligent or less capable of complex behaviors, but it does mean they're more efficient, using less energy to perform the same functions. Let's take a moment to breathe and reflect on these adaptations. Inhale slowly, feeling the air fill your lungs. Hold for a moment, and exhale, releasing any tension. As you breathe, think about the deep-sea creatures we've been discussing, about their slow, patient lives, their low metabolic rates, their efficient use of energy. There's something almost Zen-like about their existence, something that speaks to the value of slowing down, of conserving resources, of living within one's means. In a world that often values speed and productivity above all else, the deep-sea creatures remind us that there's another way, a slower way, a more sustainable way. Another important aspect of energy conservation in the deep sea is feeding strategy. In an environment where food is scarce, you can't afford to be picky. You need to eat whatever you can find, whenever you can find it. And you need to be efficient about it, expending as little energy as possible in the search for food. Many deep-sea fish are what scientists call sit-and-wait predators. Instead of actively swimming around searching for prey, which would expend precious energy, they remain motionless in the water, their sensitive eyes scanning the darkness for any hint of movement or bioluminescence. When prey comes within range, they strike with explosive speed, their attack powered by specialized muscle fibers that can contract with tremendous force despite the fish's generally sluggish metabolism. This strategy of patient waiting, punctuated by brief bursts of intense activity, is perfectly suited to an environment where food is scarce and unpredictable. The visual systems of deep-sea creatures also reveal fascinating examples of evolutionary trade-offs. Some species have sacrificed visual acuity for sensitivity, developing eyes that can detect incredibly dim light but cannot form sharp images. Others have maintained better acuity but at the cost of reduced sensitivity, able to see details but only when light levels are relatively high. Still others have abandoned vision entirely, their eyes reduced to vestigial structures or absent altogether, relying instead on other senses to navigate and find food in the darkness. The deep-sea environment has also given rise to some of the most unusual eye structures in the animal kingdom. Certain species of deep-sea fish have tubular eyes that point upward, allowing them to scan the waters above for the silhouettes of prey against the faint downwelling light. These tubular eyes sacrifice peripheral vision for increased sensitivity in a narrow field of view, a specialization that makes sense in an environment where threats and opportunities are most likely to come from above. The barrel-eye fish, which we will explore in more detail later, takes this adaptation to an extraordinary extreme, with tubular eyes housed inside a transparent, fluid-filled dome on top of its head. Some deep-sea creatures have evolved the ability to see polarized light, adding another dimension to their visual perception. Polarization patterns in light can reveal information about objects and organisms that would otherwise be invisible, allowing these creatures to detect transparent prey or to communicate with each other through polarized bioluminescent signals. The mantis shrimp, though not exclusively a deep-sea dweller, possesses perhaps the most complex visual system known, with the ability to see not only polarized light but also a far broader spectrum of colors than humans can perceive, including ultraviolet and infrared wavelengths. The study of vision in the deep sea continues to reveal surprises and challenge our assumptions about the limits of sensory perception. Each new discovery, each unusual adaptation, expands our understanding of how life can perceive and respond to its environment, reminding us that evolution is endlessly creative, finding solutions to challenges that seem insurmountable. The eyes of deep-sea creatures, whether enormous and sensitive or reduced and vestigial, whether detecting bioluminescence or the faint glow of downwelling light, all tell stories of adaptation, of survival, of the remarkable ways that life persists in the darkness. As we consider these visual adaptations, we might reflect on our own perception, on the ways that our senses shape our understanding of reality. We live in a world of bright light and vivid colors, where vision is our primary sense, and it can be difficult to imagine perceiving the world differently. But the deep-sea creatures, with their specialized eyes adapted to detect the faintest glimmers in near-total darkness, remind us that perception is not universal, that different organisms experience different realities based on their sensory capabilities. In the darkness of the deep sea, a world invisible to us is revealed to those with eyes adapted to see it, a hidden realm of bioluminescent signals and subtle movements, of predators and prey engaged in an eternal dance of survival. In the deep sea, where food is scarce and every calorie counts, creatures have evolved remarkable metabolic strategies that allow them to survive on minimal resources. These adaptations represent some of the most elegant solutions to the problem of existence in a world where the next meal might be weeks or even months away. Consider the metabolism of deep-sea fish, which operates at a pace that would seem impossibly slow to surface dwellers. Their metabolic rates can be up to 50% lower than their shallow water relatives, a profound adaptation that allows them to conserve precious energy in an environment where food arrives unpredictably, like rare gifts falling from above. This metabolic slowdown affects every aspect of their biology, from the beating of their hearts to the firing of neurons in their brains, creating creatures that exist in a state of perpetual energy conservation, always ready to spring into action when opportunity presents itself, but otherwise maintaining a state of profound stillness. The biochemistry underlying this metabolic efficiency is fascinating in its complexity. Deep-sea creatures produce specialized enzymes that function optimally in cold temperatures and high pressures, molecular machines that have been fine-tuned over millions of years to extract maximum efficiency from every chemical reaction. These enzymes work more slowly than their warm water counterparts, but they work with remarkable precision, ensuring that no energy is wasted in the biochemical processes that sustain life. The proteins that make up these enzymes are themselves adapted to the deep-sea environment, with molecular structures that remain stable and functional under conditions that would denature and destroy the proteins of surface-dwelling organisms. Many deep-sea fish have reduced their muscle mass to an absolute minimum, carrying only the muscles necessary for brief bursts of activity. Their bodies are often gelatinous, with high water content and minimal skeletal structure, reducing the metabolic cost of simply existing. Some species have bones that are barely calcified, more cartilage than true bone, flexible and light, requiring far less energy to maintain than the robust skeletons of their surface-dwelling cousins. This reduction in structural complexity might seem like a weakness, but in the deep sea, where there are no waves to fight against and no need for rapid, sustained swimming, it represents a profound adaptation to an environment where efficiency matters more than strength. The digestive systems of deep-sea predators reveal another aspect of metabolic adaptation. Many species have expandable stomachs that can accommodate prey larger than themselves, allowing them to take full advantage of rare feeding opportunities. When a deep-sea anglerfish encounters prey, it can consume fish up to twice its own size, storing this massive meal in a stomach that stretches to accommodate the bounty. The digestion process then proceeds slowly, over days or even weeks, extracting every possible nutrient from the captured prey. This ability to feast when food is available and then survive for extended periods without eating is crucial in an environment where the next meal is never guaranteed. Some deep-sea creatures have taken energy conservation to even more extreme lengths. Certain species of deep-sea octopus brood their eggs for years, the longest known brooding period of any animal on Earth. During this time, the mother octopus does not eat, surviving entirely on stored energy reserves while protecting her developing offspring. One remarkable individual was observed guarding her eggs for 4.5 years, a testament to the extraordinary metabolic efficiency that allows such prolonged fasting. The energy required to maintain basic life functions during this extended period is minimal, a metabolic feat that would be impossible for most surface-dwelling creatures. The cardiovascular systems of deep-sea fish also reflect adaptations for energy conservation. Many species have relatively small hearts and low blood pressure, reducing the energetic cost of circulating blood through their bodies. Their blood often contains specialized hemoglobin proteins that bind oxygen more efficiently than those of surface fish, allowing them to extract maximum oxygen from each breath. Some species have reduced their red blood cell counts, relying instead on oxygen dissolved directly in their blood plasma, a strategy that works in the cold, oxygen-rich waters of the deep sea and further reduces metabolic demands. Breathe in slowly, feeling the cool air fill your lungs. Hold for a moment, sensing the oxygen diffusing into your bloodstream. Exhale gently, releasing tension with each breath. Continue this rhythm, allowing your own metabolism to slow, your heartbeat to steady, finding your own state of peaceful conservation. Breathe in. Hold. Breathe out. Rest in this moment of stillness. The nervous systems of deep-sea creatures also show adaptations for energy efficiency. Brain tissue is metabolically expensive, requiring significant energy to maintain, so many deep-sea species have relatively small brains compared to their body size. However, these compact brains are highly specialized, with neural circuits optimized for the specific tasks necessary for survival in the deep sea. The sensory processing centers are often enlarged, particularly those dealing with chemical detection and pressure sensitivity, while areas devoted to complex social behaviors or rapid decision-making may be reduced or absent. This neural specialization ensures that every neuron serves a critical function, with no energy wasted on unnecessary cognitive processing. Some deep-sea creatures have evolved symbiotic relationships that help them conserve energy. Certain species of deep-sea fish harbor chemosynthetic bacteria in specialized organs, similar to the bioluminescent bacteria we discussed earlier. These bacteria can provide their hosts with nutrients synthesized from chemicals in the environment, supplementing the fish's diet and reducing their dependence on captured prey. This internal farming of bacteria represents a remarkable adaptation, turning the fish into mobile ecosystems that carry their own food source within their bodies. The reproductive strategies of deep-sea creatures also reflect the constraints of energy conservation. Many species produce relatively few, large eggs, investing significant energy in each offspring to give them the best possible chance of survival. This contrasts with the strategy of many surface fish, which produce millions of tiny eggs, relying on sheer numbers to ensure that some offspring survive. In the deep sea, where finding a mate is difficult and energy is precious, quality matters more than quantity. The large eggs contain substantial yolk reserves, providing developing embryos with the energy they need to grow without feeding, sometimes for months or even years. Some deep-sea fish have evolved a reproductive strategy called parasitic mating, most famously seen in certain species of anglerfish. In these species, the tiny male fish, sometimes 100 times smaller than the female, attaches himself permanently to the female's body, fusing with her tissues and becoming essentially a parasitic appendage. The male loses most of his organs, including his eyes and digestive system, receiving all his nutrients from the female's bloodstream. In return, he provides sperm whenever the female is ready to reproduce. This bizarre arrangement solves the problem of finding a mate in the vast darkness of the deep sea while minimizing the metabolic cost of maintaining a separate male individual. The growth rates of deep-sea creatures are typically very slow, another reflection of their low metabolic rates. A deep-sea fish might take decades to reach maturity, growing incrementally year after year in the cold, food-poor environment. This slow growth means that deep-sea ecosystems are particularly vulnerable to overfishing, as populations cannot quickly recover from depletion. The ancient fish pulled up from the depths might be older than the fishermen who catch them, individuals that have survived for a century or more in the eternal darkness, their slow metabolism allowing them to persist through decades of scarcity. The lipid composition of deep-sea creatures also reveals metabolic adaptations. Many species store energy in the form of specialized fats and oils that remain liquid at cold temperatures, unlike the saturated fats that would solidify in the frigid deep-sea environment. These lipids serve multiple functions, providing energy reserves, contributing to buoyancy, and insulating vital organs. The chemical structure of these fats is precisely tuned to the deep-sea environment, with molecular arrangements that maintain fluidity and accessibility even at temperatures just above freezing. Some deep-sea creatures have evolved the ability to enter states of dormancy or torpor when food is particularly scarce, further reducing their already minimal metabolic rates. During these periods, their bodily functions slow to barely detectable levels, their hearts beating only a few times per minute, their breathing reduced to occasional, shallow movements. They drift in the darkness, suspended between life and death, waiting for conditions to improve, for food to arrive, for the opportunity to resume active life. This ability to pause, to wait, to endure, represents perhaps the ultimate adaptation to an environment defined by scarcity and patience. The mitochondria within the cells of deep-sea creatures, the tiny organelles responsible for producing energy, show their own adaptations to the deep-sea environment. These cellular power plants are often more numerous in deep-sea species, compensating for their slower operation with greater numbers. The inner membranes of these mitochondria, where energy production occurs, may have specialized lipid compositions that maintain their function under high pressure. The enzymes within the mitochondria are adapted to work efficiently in cold temperatures, ensuring that energy production continues even in the near-freezing waters of the abyss. The immune systems of deep-sea creatures also reflect metabolic constraints. Maintaining a robust immune system is energetically expensive, requiring the constant production of immune cells and antibodies. Some deep-sea species have reduced immune function compared to their surface-dwelling relatives, a calculated trade-off that frees up energy for other essential functions. However, the cold temperatures and high pressures of the deep sea may also reduce the activity of pathogens, making a less robust immune system a viable strategy in this environment. As we contemplate these metabolic adaptations, we begin to understand that life in the deep sea is fundamentally about efficiency, about doing more with less, about surviving in a world where every calorie is precious and waste is not an option. These creatures have stripped away everything unnecessary, refining their biology to its essential core, becoming living examples of elegant simplicity. In their metabolic strategies, we see a kind of wisdom, a patient acceptance of limitation, a willingness to slow down, to wait, to persist through scarcity with grace and resilience. Among the countless species that inhabit the deep sea, certain creatures stand out for their remarkable specializations, their unique adaptations that push the boundaries of what we thought possible in living organisms. These are the specialists, the extremophiles, the creatures that have evolved to occupy ecological niches so specific, so demanding, that they represent the pinnacle of adaptation to the deep-sea environment. Let us begin with the barrel-eye fish, a creature so unusual in its appearance that it seems almost alien. This small fish, typically only about 6 inches long, possesses one of the most extraordinary visual systems in the animal kingdom. Its eyes are tubular, pointing upward through a transparent, fluid-filled dome that covers the top of its head. This dome, made of transparent tissue, protects the delicate eyes while allowing the fish to see through the top of its own head, scanning the waters above for the silhouettes of prey or the bioluminescent displays of other creatures. The eyes themselves are packed with rod cells, the photoreceptors specialized for detecting dim light, giving the barrel-eye exceptional sensitivity in the darkness of the mesopelagic zone. But the truly remarkable feature of the barrel-eye is its ability to rotate its eyes within its transparent head. When the fish spots prey above, it can rotate its tubular eyes forward, allowing it to see where it's going as it swims upward to capture its meal. This flexibility, discovered only recently through observations of living specimens, reveals a level of visual sophistication that scientists had not previously imagined. The barrel-eye's transparent head, once thought to be a fixed structure, is actually a flexible adaptation that allows the fish to switch between upward-looking surveillance mode and forward-looking hunting mode, a remarkable solution to the challenge of finding food in the three-dimensional darkness of the deep sea. Consider next the vampire squid, a creature whose name evokes horror, but whose reality is far more fascinating than frightening. Despite its name, the vampire squid is not actually a squid, nor does it feed on blood. Instead, it occupies its own unique taxonomic position, the sole surviving member of an ancient lineage that diverged from other cephalopods millions of years ago. The vampire squid lives in the oxygen minimum zone, a layer of water where oxygen concentrations are so low that most creatures cannot survive. Here, in this suffocating environment, the vampire squid has found a refuge from predators, adapting to conditions that would be lethal to most other animals. The vampire squid's adaptations to low oxygen are remarkable. Its blood contains specialized hemocyanin proteins that bind oxygen with exceptional efficiency, allowing it to extract every available oxygen molecule from the depleted water. Its metabolic rate is extremely low, reducing its oxygen requirements to a minimum. When threatened, the vampire squid can invert its webbed arms over its body, transforming itself into a spiky ball covered with fleshy projections called cirri, which may confuse or deter predators. The inside surfaces of its arms are studded with photophores that can produce disorienting flashes of bioluminescent light, and the squid can also eject a cloud of bioluminescent mucus rather than ink, creating a glowing decoy that distracts predators while the squid escapes into the darkness. Perhaps most remarkably, the vampire squid is a detritivore, feeding on marine snow, the constant rain of organic particles that falls from the surface waters. It uses two specialized filaments, retractile structures that can extend to many times the length of its body, to collect particles of marine snow. These filaments are covered with tiny hair-like projections that trap particles, which the squid then draws back to its mouth, scraping off the collected food with specialized appendages. This feeding strategy, unique among cephalopods, allows the vampire squid to survive in an environment where active predation would be too energetically expensive. The giant squid, perhaps the most famous of deep-sea creatures, has captivated human imagination for centuries, appearing in sailors' tales and maritime legends long before scientists confirmed its existence. These enormous cephalopods can reach lengths of over 40 feet, with eyes the size of dinner plates, the largest eyes in the animal kingdom. These massive eyes are adapted to detect the faint bioluminescence of prey and the subtle disturbances created by the movement of large predators, particularly sperm whales, which hunt giant squid in the deep ocean. The giant squid's body is a marvel of engineering, with powerful tentacles lined with hundreds of suction cups, each ringed with sharp, tooth-like structures that grip prey with incredible force. The squid's beak, made of chitin and harder than most metals, can slice through flesh and bone, allowing it to consume large prey. Despite their size, giant squid are thought to be ambush predators, drifting in the darkness and striking with explosive speed when prey comes within range. Their bodies are neutrally buoyant, filled with ammonium chloride solution that is less dense than seawater, allowing them to hover effortlessly in the water column without expending energy on swimming. Breathe deeply, imagining yourself suspended in that same darkness, weightless and still, waiting with infinite patience. Feel the water around you, the pressure, the cold, the absolute silence. Breathe in the mystery, exhale the need to understand everything immediately. Rest in the wonder of these creatures, these specialists of the abyss. The gulper eel, also known as the pelican eel, represents another extreme of deep-sea specialization. This creature is almost all mouth, with enormous jaws that can open to incredible angles, creating a cavernous maw that can engulf prey much larger than the eel itself. The gulper eel's body is long and whip-like, tapering to a thin tail tipped with a complex photophore that produces bioluminescent light. Scientists believe this tail light may serve as a lure, attracting prey toward the eel's waiting mouth, or perhaps as a decoy, drawing predators' attention away from the eel's vulnerable head. The gulper eel's stomach is highly expandable, allowing it to store large meals that can sustain it through long periods of fasting. Its skeleton is reduced to a minimum, with lightweight bones that reduce the energetic cost of maintaining body structure. The eel's tiny eyes suggest that vision is not its primary sense. Instead, it likely relies on detecting vibrations and chemical signals to locate prey in the darkness. The gulper eel's extreme specialization for consuming large, infrequent meals represents an adaptation to an environment where food is scarce and unpredictable, where the ability to take advantage of rare opportunities can mean the difference between survival and starvation. The fangtooth fish, despite its fearsome appearance, is actually quite small, typically only about 6 inches long. But what it lacks in size, it makes up for in dental equipment. The fangtooth has the largest teeth relative to body size of any fish in the ocean, with 2 enormous fangs on its lower jaw that are so long that the fish has special sockets in its upper jaw to accommodate them when its mouth is closed. These teeth are used to impale prey, which the fangtooth hunts by swimming through the water with its mouth open, relying on chance encounters in the darkness. The fangtooth lives at depths where pressure is immense and food is scarce. Its body is covered with small, sharp scales, and its bones are honeycombed with cavities that reduce their weight while maintaining structural integrity. The fish's lateral line system, a series of sensory organs that detect vibrations and pressure changes in the water, is highly developed, allowing it to sense the movements of prey and predators in the absolute darkness of its habitat. Young fangtooth fish look completely different from adults, with different body shapes and living at different depths, a phenomenon called ontogenetic migration that allows the species to exploit different ecological niches at different life stages. The tripod fish represents a different kind of specialization, adapted not for swimming through the water column but for standing on the seafloor. This fish has elongated rays on its pectoral and caudal fins that it uses like stilts, propping itself up above the muddy bottom of the abyssal plain. In this elevated position, the tripod fish faces into the current, using its sensitive lateral line system and specialized sensory organs to detect tiny crustaceans and other prey drifting past in the water. When it detects prey, it strikes with remarkable speed, capturing the food and then returning to its stationary position. The tripod fish's lifestyle is one of extreme energy conservation. By remaining stationary and letting food come to it, the fish minimizes energy expenditure, a crucial adaptation in the food-poor environment of the abyssal plain. Some tripod fish are hermaphrodites, possessing both male and female reproductive organs, an adaptation that may help solve the problem of finding mates in the vast, sparsely populated expanses of the deep seafloor. When two tripod fish do encounter each other, they can both produce eggs and sperm, doubling the reproductive output of the meeting. The Dumbo octopus, named for the ear-like fins that protrude from its head, resembling the ears of Disney's flying elephant, is one of the deepest living octopuses, found at depths of up to 23,000 feet. These small octopuses, typically only about 8 to 12 inches long, use their ear-like fins to propel themselves through the water, flapping them like wings to swim gracefully through the darkness. These ear-like fins not only allow for efficient swimming but also help the Dumbo octopus maneuver with precision in the tight spaces of the deep sea, avoiding obstacles and positioning itself for hunting. The octopus feeds primarily on small crustaceans and worms, using its beak to crush prey and its arms to manipulate food. Unlike many shallow water octopuses, the Dumbo does not rely on jet propulsion but instead uses its fins for a more energy-efficient form of locomotion, conserving precious energy in the cold, food-scarce depths. The skin of the Dumbo octopus is highly adaptable, capable of changing texture and color, though in the darkness of the deep sea, color changes serve more for communication or camouflage against faint bioluminescent light than for visual display. The octopus can also release a cloud of bioluminescent mucus as a defense mechanism, similar to the vampire squid, creating a distraction that allows it to escape predators. This combination of graceful movement, efficient energy use, and defensive adaptations makes the Dumbo octopus a perfect resident of the abyssal depths, thriving where others cannot. Another remarkable specialist is the Yeti crab, Kiwa hirsuta, discovered in 2005 at a hydrothermal vent in the South Pacific. This crab is covered in long, hairy filaments on its claws and body, giving it a ghostly, yeti-like appearance. These hairs are actually sensory organs packed with chemosensory bacteria, allowing the crab to detect chemicals in the vent environment and to cultivate its own food source. The Yeti crab waves its claws in the vent fluids, farming the bacteria that grow on the hairs, then brushes the bacteria into its mouth, a unique form of chemosynthetic nutrition that supplements its diet of mussels and other vent organisms. The Yeti crab's adaptations to the extreme conditions of hydrothermal vents are profound. Its shell is reinforced to withstand the high temperatures and pressures, and its metabolism is tuned to function in the toxic, sulfide-rich waters. The crab's symbiotic relationship with the bacteria on its hairs represents a form of horizontal symbiosis, where the crab provides a habitat and the bacteria provide food, allowing the crab to thrive in an environment where traditional photosynthesis-based food chains do not exist. This discovery expanded our understanding of life at vents, showing how even crustaceans can evolve such intimate partnerships with microbes. The snipe eel, with its long, thin body and beak-like jaws, is another deep-sea oddity, adapted for a life of probing the darkness for prey. This eel can reach lengths of over 6 feet, but its body is so slender that it resembles a living needle. The snipe eel's jaws are equipped with tiny, backward-pointing teeth that prevent prey from escaping once captured, and it feeds on small fish and crustaceans that it encounters while drifting in the water column. Its eyes are small, suggesting reliance on other senses, but recent studies have revealed that it possesses electroreceptors, allowing it to detect the electrical fields generated by the muscle contractions of nearby prey. This electrosensory ability is a common adaptation in the deep sea, where visibility is limited, and it allows the snipe eel to hunt effectively in total darkness. The eel's body is gelatinous and flexible, reducing its density and allowing neutral buoyancy, while its slow metabolism enables long periods without feeding. The snipe eel's lifestyle of patient drifting and opportunistic strikes embodies the deep-sea ethos of energy conservation, waiting for prey to come close before expending the minimal effort needed to capture it. The sea pig, Scotoplanes globosa, a type of sea cucumber, is a humble but essential inhabitant of the abyssal plain. These small, pinkish creatures, about 4 inches long, waddle across the seafloor on tube feet, their bodies raised slightly above the sediment. Sea pigs are detritivores, feeding on organic detritus in the mud, using their tube feet to lift and process sediment, extracting nutrients from the marine snow that reaches the bottom. Their movements create small depressions in the seafloor, aerating the sediment and facilitating the breakdown of organic matter, making them key players in nutrient cycling. Despite their unassuming appearance, sea pigs are abundant in the deep sea, forming herds that traverse the abyssal plains in search of food. Their bodies are soft and inflatable, filled with water for buoyancy, and their slow, deliberate movements conserve energy in an environment where food is sparse. The sea pig's role in the ecosystem underscores the importance of seemingly ordinary creatures whose patient foraging and biodiversity activities support the entire deep-sea food web. Let's pause here for a breath. Inhale slowly, drawing in the calm of the deep. Hold gently, feeling the expansion. Exhale, releasing the day's currents. As we rest, consider these specialists, each a unique solution to the deep sea's challenges, each a story of adaptation and survival. These remarkable creatures, from the barreleye with its see-through head to the yeti crab farming bacteria on its claws, illustrate the boundless creativity of evolution in the deep sea. Each adaptation is a response to specific pressures: darkness, cold, scarcity, toxicity, refining form and function to perfection. In their strangeness, they reveal the familiar, the drive to survive, to reproduce, to connect with their environment in ways that sustain life. Now, let us turn to the broader tapestry of life in the deep sea, to the interconnections that bind these specialists into functioning ecosystems. The deep sea is not a collection of isolated oddities but a complex web of relationships, where energy flows from the surface to the abyss, where organisms depend on each other for food, habitat, and survival. At the base of most deep-sea food webs lies marine snow, the steady rain of organic particles from the sunlit surface. This detritus, dead plankton, fecal pellets, discarded molts, sinks slowly through the water column, providing the primary energy source for deep-sea life. As it falls, it is colonized by bacteria and small invertebrates, which break it down and make its nutrients available to larger consumers. By the time it reaches the seafloor, much of the energy has been transferred through multiple trophic levels, but enough remains to sustain the abyssal communities. Detritivores, such as sea cucumbers and brittle stars, are the primary consumers of marine snow on the seafloor. These creatures process vast quantities of sediment, extracting organic matter and excreting the inorganic remnants, which enrich the seafloor and support bacterial growth. Sea cucumbers, with their vacuum-like mouths, swallow sediment and pass it through their digestive tracts, where symbiotic bacteria help break down the organic content. The excreted material is finer and more accessible, facilitating further decomposition and making nutrients available for uptake by plants and microbes where they can be used by other organisms. Their feeding activities also biotubate the sediment, mixing and oxygenating it, creating a more hospitable environment for other creatures. Filter feeders, such as glass sponges and certain types of sea anemones, strain particles from the water column, capturing marine snow as it falls. These sessile organisms, attached to the seafloor or to hard substrates, create three-dimensional structures that provide habitat for other creatures. A single large glass sponge can host dozens of species of small invertebrates and fish, creating a biodiversity hotspot in the otherwise sparse abyssal plain. The predators of the deep sea, from small fish to large squid, form the upper levels of the food web. These creatures consume the detritivores and filter feeders, as well as each other, transferring energy up through the trophic levels. However, the efficiency of energy transfer in the deep sea is low, as it is in all ecosystems, with only about 10% of the energy at one trophic level being passed on to the next. This means that top predators in the deep sea are relatively rare, as there is simply not enough energy to support large populations of high-level consumers. Scavengers play a crucial role in deep-sea ecosystems, consuming the carcasses of dead organisms that sink to the seafloor. When a whale dies and sinks to the deep ocean floor, it creates what is known as a whale fall, a massive input of organic matter that can sustain a specialized community of scavengers and decomposers for decades. Hagfish, sleeper sharks, and various crustaceans are among the first to arrive at a whale fall, consuming the soft tissues. As the carcass is stripped of flesh, other organisms move in, including bone-eating worms called osedacs that bore into the whale's skeleton and extract lipids from the bone matrix. A whale fall progresses through several stages, each characterized by different communities of organisms. The initial scavenging stage, where large predators consume the soft tissues, may last for months or years. This is followed by an enrichment stage, where the seafloor around the carcass is enriched with organic matter, supporting dense populations of worms, crustaceans, and other invertebrates. Finally, in the sulfophilic stage, bacteria break down the lipids in the whale's bones, producing hydrogen sulfide that supports chemosynthetic bacteria and the specialized fauna that depend on them, similar to the communities found at hydrothermal vents. Hydrothermal vents represent another type of interconnection in the deep sea, one based not on energy from the sun but on chemical energy from the Earth's interior. The chemosynthetic bacteria that form the base of vent food webs convert chemicals in the vent fluids into organic matter, supporting dense communities of specialized organisms. These vent communities are oases of life in the deep sea, with biomass densities far higher than in the surrounding abyssal plain. The organisms living at hydrothermal vents are interconnected in complex ways. Giant tube worms, which can grow to over 6 feet long, have no mouth or digestive system. Instead, they harbor chemosynthetic bacteria in a specialized organ called a trophosome, providing the bacteria with hydrogen sulfide and oxygen and receiving organic compounds in return. This symbiotic relationship allows the tube worms to thrive in an environment where most organisms cannot survive. Vent mussels and clams also harbor chemosynthetic bacteria, either in their gills or in specialized tissues. These bivalves position themselves at the boundaries between vent fluids and normal seawater, where they can provide their bacterial symbionts with both the chemicals needed for chemosynthesis and the oxygen needed for respiration. The bacteria, in turn, provide the bivalves with nutrition, allowing them to grow to large sizes despite the absence of photosynthetically derived food. Breathe slowly, contemplating these interconnections, the way that life in the deep sea is woven together in a tapestry of relationships. Breathe in connection, exhale isolation. Rest in the understanding that no organism exists alone, that all life is part of larger patterns, larger systems, larger communities. The predators at hydrothermal vents, including specialized fish, crabs, and octopuses, feed on the abundant vent fauna, transferring energy from the chemosynthetic base of the food web to higher trophic levels. Some of these predators are found only at vents, while others also occur in the surrounding deep sea, moving between vent and non-vent habitats. This movement of organisms between habitats creates connections between the vent ecosystem and the broader deep-sea ecosystem, linking these seemingly isolated communities. Cold seeps, areas where methane and other hydrocarbons seep from the seafloor, support communities similar to those at hydrothermal vents, based on chemosynthetic bacteria that oxidize methane. These seep communities include mussels, clams, and tube worms that harbor chemosynthetic bacteria, as well as specialized predators and scavengers. Cold seeps are more widespread than hydrothermal vents, occurring on continental margins around the world, and they may play an important role in connecting deep-sea populations, serving as stepping stones that allow larvae to disperse across the deep ocean. The vertical migrations of organisms between the deep sea and surface waters create another type of interconnection, linking the deep sea ecosystem to the sunlit surface. Many species of fish, squid, and crustaceans migrate vertically each day, spending the daylight hours in the deep sea to avoid predators and moving up to surface waters at night to feed. These vertical migrants transport energy and nutrients from the surface to the deep sea, both through their own metabolism and excretion and through their eventual death and sinking. The magnitude of this vertical migration is staggering. The deep scattering layer, a layer of organisms that appears on sonar as a false bottom, is composed primarily of vertically migrating fish and crustaceans. This layer can be hundreds of feet thick and extends across entire ocean basins, representing one of the largest migrations of biomass on Earth. The organisms in the deep scattering layer consume vast quantities of plankton in surface waters each night and transport a significant fraction of this energy to the deep sea, where it supports deep-sea predators and scavengers. The interconnections in deep-sea ecosystems extend beyond direct feeding relationships to include more subtle interactions. Some organisms provide habitat for others, like the glass sponges that host diverse communities of small invertebrates. Others modify the physical environment in ways that benefit other species, like the biodebating activities of sea cucumbers that oxygenate sediments. Still others engage in symbiotic relationships, like the chemosynthetic bacteria that live inside vent organisms or the bioluminescent bacteria that inhabit the light organs of fish and squid. Competition and predation structure deep-sea communities, determining which species can coexist and in what abundances. The scarcity of resources in the deep sea means that competition for food can be intense, favoring species that are most efficient at finding and consuming scarce resources. Predation pressure shapes the evolution of defensive adaptations, from the bioluminescent decoys of the vampire squid to the gelatinous, unpalatable bodies of many deep-sea creatures. The deep-sea ecosystem is also connected to human activities in ways that are becoming increasingly apparent. Deep-sea fishing has depleted populations of some species, disrupting food webs and altering community structure. Bottom trawling, a fishing method that drags heavy nets across the seafloor, destroys habitat and kills non-target species, with effects that can persist for decades or centuries. The dumping of waste in the deep ocean, including plastics and other pollutants, introduces contaminants that accumulate in deep-sea food webs, potentially affecting organisms at all trophic levels. Climate change is also affecting the deep sea, though the impacts are complex and not fully understood. Changes in surface ocean temperature and productivity alter the flux of organic matter to the deep sea, potentially affecting food availability for deep-sea organisms. Ocean acidification, caused by the absorption of carbon dioxide from the atmosphere, may affect deep-sea organisms with calcium carbonate shells or skeletons. Changes in ocean circulation could alter the distribution of oxygen in the deep sea, expanding or contracting oxygen minimum zones and affecting the organisms that live in or near these zones. Mining for minerals in the deep sea, particularly at hydrothermal vents and on abyssal plains rich in polymetallic nodules, represents a new and potentially devastating threat to deep-sea ecosystems. The removal of mineral deposits would destroy habitat and kill organisms directly, while the sediment plumes created by mining operations could spread over vast areas, smothering organisms and disrupting food webs. The slow growth rates and low reproductive rates of many deep-sea species mean that recovery from such disturbances could take centuries or millennia, if it occurs at all. Understanding the interconnections in deep-sea ecosystems is crucial for their conservation and management. The deep sea is not a frontier to be exploited without consequence, but a functioning ecosystem that provides important services, from carbon sequestration to nutrient cycling to the maintenance of biodiversity. The creatures of the deep sea, connected to each other and to the surface world in myriad ways, remind us that all parts of the ocean are linked, that disturbances in one area can have far-reaching effects, and that the health of the deep sea is intimately connected to the health of the entire planet. As we emerge from our journey through the deep sea, rising slowly through the layers of the ocean like a deep-sea creature ascending toward the light, we carry with us new understanding, new wonder, and perhaps new questions about life, adaptation, and our own place in the natural world. The deep sea, in all its darkness and mystery, has revealed itself to be not a barren wasteland but a realm of extraordinary life, where creatures have evolved remarkable adaptations to survive and thrive in conditions that seem impossible. In the bioluminescent displays of deep-sea organisms, we have seen how life creates its own light in the darkness, how communication and survival can occur through the language of living light. In the pressure-resistant proteins and specialized biochemistry of deep-sea creatures, we have witnessed the molecular innovations that allow life to persist under crushing pressure. In the enormous eyes and specialized visual systems of deep-sea fish, we have discovered how vision can be maintained even in near-total darkness, how evolution can push the boundaries of what seems physically possible. We have explored the metabolic strategies that allow deep-sea creatures to survive on minimal resources, the elegant efficiency of organisms that have stripped away everything unnecessary, reducing their biology to its essential core. We have met specialized creatures whose bizarre forms and unique adaptations expand our understanding of what life can be, from the transparent-headed barrel-eye fish to the parasitic male anglerfish, to the deepest living snailfish. We have considered the sensory world of the deep, the alternative ways of perceiving reality through pressure waves, chemical trails, electrical fields, and touch, reminding us that our own perception is just one of many possible ways of experiencing the world. We have contemplated the challenges of reproduction in the deep sea, the patient, slow rhythms of life cycles that unfold over decades or centuries, the diverse strategies that ensure the continuation of species despite darkness, distance, and scarcity. And we have traced the interconnections that link deep-sea organisms to each other and to the broader ocean ecosystem, revealing the deep sea not as an isolated realm, but as an integral part of the planetary system, connected to surface waters, to human activities, and to the global climate. What can we learn from the deep sea, from these creatures that live in eternal darkness, under crushing pressure, in cold and scarcity? Perhaps we can learn about resilience, about the ability of life to adapt to even the most extreme conditions, to find solutions to seemingly impossible challenges. The deep-sea creatures, thriving in an environment that would kill us instantly, demonstrate that life is not fragile but remarkably robust, capable of persisting in places we never imagined it could exist. We might also learn about patience, about the value of slow growth, slow metabolism, slow reproduction in a world that often seems to demand speed and urgency. The deep-sea fish that takes decades to mature, the octopus that broods its eggs for years, the ecosystems that recover from disturbance over centuries, all remind us that some processes cannot be rushed, that patience and persistence have their own wisdom. The deep sea teaches us about efficiency, about doing more with less, about the elegance of simplicity. In a world where we often equate more with better, where consumption and waste seem to be the norm, the deep-sea creatures show us an alternative, a way of life based on conservation, on using only what is necessary, on making every resource count. Their metabolic efficiency, their reduced body structures, their patient waiting for food, all speak to a different relationship with resources, one based on respect for scarcity and appreciation for what is available. We might also learn about interconnection, about the way that all life is linked in webs of relationship and mutual dependence. The deep-sea ecosystem, with its food webs, its symbioses, its habitat-creating species, and its nutrient cycles, reminds us that no organism exists in isolation, that we are all part of larger systems, larger communities, larger patterns. The health of the deep sea affects the health of the entire ocean, and the health of the ocean affects the health of the planet, including our own well-being. Breathe deeply now, feeling yourself connected to the deep sea, to the creatures we have met on this journey, to the vast ocean that covers most of our planet. Breathe in wonder, exhale certainty. Rest in the mystery, in the knowledge that there is still so much to discover, so much to learn, so many secrets hidden in the darkness of the deep. The deep sea also invites us to humility, to recognition of how much we don't know, how much remains to be discovered. Despite decades of exploration and research, we have explored less than 5% of the ocean floor. Vast areas of the deep sea remain completely unknown, never visited by humans or human technology. New species are discovered regularly, and each discovery raises new questions, reveals new mysteries. The deep sea reminds us that the world is larger and more complex than we can fully comprehend, that there are realms beyond our direct experience, realities different from our own. This humility extends to our relationship with the natural world. The deep-sea creatures, with their ancient lineages and their slow life cycles, have persisted for millions of years, surviving mass extinctions and climate changes that wiped out countless other species. Yet now, in the span of just a few decades, human activities threaten deep-sea ecosystems in ways they have never been threatened before. Overfishing, pollution, climate change, and the prospect of deep-sea mining all pose risks to creatures and ecosystems that have endured for eons. The deep sea asks us to consider our responsibilities, to think about the consequences of our actions, to recognize that our choices affect not just ourselves and our immediate surroundings but the entire planet, including realms we may never see. The creatures of the deep sea, living their lives in darkness thousands of feet below the surface, might seem remote from our daily concerns, but they are part of the same planetary system we inhabit, and their fate is intertwined with our own. Perhaps the deep sea can also inspire us, showing us that adaptation is possible, that life finds ways to persist even in the most challenging circumstances. As we face our own challenges, from personal struggles to global crises, the resilience of deep-sea life offers a kind of hope, a reminder that solutions exist, that creativity and flexibility can overcome obstacles, that life is fundamentally persistent and adaptable. The bioluminescence of deep-sea creatures, creating light in the darkness, might serve as a metaphor for human creativity and innovation, our ability to find solutions, to create beauty, to communicate and connect even in difficult circumstances. The pressure-resistant adaptations of deep-sea organisms might remind us of our own capacity to withstand stress, to develop resilience, to adapt our strategies when circumstances change. The efficient metabolism of deep-sea creatures might inspire us to consider our own use of resources, to find ways to do more with less, to live more sustainably. As we conclude this journey through the deep sea, we might take a moment to appreciate the privilege of learning about these remarkable creatures, of glimpsing a world that few humans will ever see directly. The scientists who study the deep sea, who design and operate the submersibles and remotely operated vehicles that explore the abyss, who analyze samples and data to piece together the story of deep-sea life, have given us a gift, expanding our understanding of life on Earth and our place within it. The deep sea, in all its strangeness and wonder, is part of our planet, part of our home. The creatures that live there, adapted to darkness and pressure and cold, are our distant relatives, sharing with us the fundamental characteristics of life, the ability to grow, to reproduce, to respond to the environment, to evolve. In their alien forms and remarkable adaptations, we see not otherness but kinship, not monsters but fellow travelers on the journey of life. As you prepare to return to your own world, to the surface realm of light and air, carry with you the lessons of the deep sea. Remember the bioluminescent creatures creating their own light in the darkness, and consider how you might bring light to dark places in your own life. Remember the pressure-resistant organisms thriving under crushing weight, and reflect on your own resilience, your own capacity to withstand stress and difficulty. Remember the efficient metabolism of deep-sea creatures, and think about how you might live more simply, more sustainably, using only what you need and appreciating what you have. Remember the patient reproduction of deep-sea species, the slow growth, the long lives, and consider the value of patience in your own life, the wisdom of allowing things to unfold in their own time. Remember the interconnections of the deep-sea ecosystem, the way that all organisms are linked in webs of relationship, and reflect on your own connections to other people, to other species, to the planet that sustains us all. And remember the mystery of the deep sea, the vast unknown that still awaits exploration, and let that mystery inspire wonder, curiosity, and humility. The world is larger and more complex than we can fully understand, full of hidden realms and undiscovered species, and that is something to celebrate, not to fear. The unknown invites us to keep learning, keep exploring, keep asking questions, keep opening ourselves to new experiences and new understanding. As you drift now towards sleep, let the images of the deep sea accompany you, the bioluminescent displays, the strange and beautiful creatures, the vast darkness punctuated by points of living light. Let the rhythm of your breathing match the slow metabolism of deep-sea organisms, your heartbeat slowing, your body relaxing, your mind settling into stillness. Feel yourself suspended in the darkness, weightless and peaceful, like a deep-sea creature drifting in the water column, conserving energy, waiting patiently, existing in a state of profound calm. The deep sea is always there, beneath the surface, beneath the waves, a realm of mystery and wonder that persists regardless of whether we think about it or not. The creatures of the abyss continue their lives in the darkness, hunting and hiding, glowing and sensing, reproducing and dying, part of the endless cycle of life that has continued for billions of years and will continue long after we are gone. In their persistence, in their adaptation, in their remarkable diversity, they remind us that life is resilient, creative, and endlessly fascinating. Thank you for joining this journey into the deep sea, for opening your mind to these remarkable creatures and their extraordinary adaptations. If you found wonder in these depths, if you discovered something new, if you felt a sense of connection to the hidden realms of our ocean, consider sharing this journey with others. Like and subscribe to continue exploring the natural world together, to keep learning about the incredible diversity of life on Earth, to maintain our sense of wonder about the planet we call home. May your dreams be filled with bioluminescent displays, with strange and beautiful creatures, with the peaceful darkness of the deep sea. May you rest well, sleep deeply, and wake refreshed, carrying with you a new appreciation for the hidden wonders of our world, the remarkable adaptations of life, and the interconnections that link us all. Good night, and may the mysteries of the deep sea inspire your dreams and enrich your waking life. Breathe slowly, deeply, peacefully, and rest. Hello there, and welcome to a quiet corner of the cosmos, where the stars seem to whisper just for you. Wherever you find yourself tonight, whether tucked under soft covers or simply easing into the hush of evening, let this be your gentle invitation to unwind. The solar system, that grand, swirling family of worlds orbiting in eternal harmony, holds secrets that can soothe the busiest mind, reminding us of our place in something far vaster and more tender than the day's fleeting worries. Imagine it now, a delicate ballet of light and shadow, where each planet traces its path like a leaf carried on an unseen current, all bathed in the steady glow of our shared star. To wonder these facts is to invest in a deeper calm, a way to let curiosity cradle you towards sleep, turning the unknown into a soft, enveloping dream. If these starry musings spark a flicker of peace in your evening, consider lending a quiet like or subscribing €1. It helps others stumble upon this serene path too, one drifting soul at a time. But for now, settle deeper into the moment. Breathe in the vastness, exhale the ordinary, and let us begin this slow, luminous journey through the heart of it all, starting with the sun itself, that radiant constant at the center of our celestial home. The sun, our eternal companion, rises each dawn not as a mere ball of fire but as a living testament to the universe's patient artistry, a sphere of plasma so immense it cradles the entire solar system in its gravitational embrace. Born from the collapse of a vast nebula some 4.6 billion years ago, it emerged from cosmic dust and gas, swirling slowly into form like a dreamer coalescing from scattered thoughts, its core igniting in a hush of nuclear fusion that has burned steadily ever since. This star, average in the grand tapestry of the galaxy yet profoundly generous to us, commands 99.8% of the solar system's mass, a quiet dominance that holds wandering comets and distant worlds in check without a whisper of effort. Picture it there, a golden orb 1,392,000 kilometers across, wide enough to swallow over 1 million Earths whole, yet so distant euro 93 million miles away euro that its light reaches us in just 8 serene minutes, a delay that feels like the universe pausing to catch its breath. In this vast symmetry, the sun's surface churns with plasma flows that ripple like silken waves on an unseen ocean. Each arch and flare forms a fleeting sculpture of ionized elegance. Creation dances on, even in stillness. And in this hushed glow, consider how the sun's heart beats with a rhythm older than mountains or rivers. Its core, a furnace of 15 million degrees Celsius, merges hydrogen atoms in pairs. This releases energy that sustains life across billions of miles. The process is so efficient it will endure for another 5 billion years. It expands gently into a red giant, not in fury, but in a slow, inevitable sigh. This fusion, the alchemy of stars, converts a mere 4 million tons of matter into light and heat each second. It leaves behind helium as a subtle legacy. Layer by layer, it builds like a patient architect shaping the void into possibility. Just as a single candle can warm a quiet room on a winter night, so does this stellar heart nurture the distant wanderers, offering a steady warmth that echoes in every sunrise we share. As the sun's warm light bathes our wandering thoughts, let us linger on its corona, that ethereal halo visible only during the moon's rare embrace in eclipse. A crown of plasma threads stretches millions of kilometers into space. It burns hotter than the surface itself at 2 million degrees. This defies our earthly intuitions with its paradoxical fire. Here, particles escape as the solar wind. This gentle stream of charged ions flows outward at 400 kilometers per second. It sculpts the heliosphere euro, a vast bubble shielding our system from interstellar geyser euro like a protective veil woven from starlight. This wind, born of the sun's quiet exhalations, carries magnetic fields that tangle and twist. Occasionally, it unleashes coronal mass ejections, not as tempests, but as luminous veils. These dance across auroras on distant worlds. They paint the skies in greens and purples, as if the heavens themselves blush in shared wonder. Think of it like the faint breeze through an open window on a summer evening, carrying scents from the garden beyond a euro, subtle, yet alive with possibility. In the sun's surface layers, sunspots emerge as cooler islands amid the photosphere's blaze. Dark blemishes cycle every 11 years in a predictable ebb and flow. Each one is a magnetic knot where fields emerge and reconnect. This releases bursts of radiation that subtly influence Earth's climates and technologies. It reminds us of our delicate tether to this stellar pulse. These spots, vast enough to eclipse entire planets, fade and reform like breaths on a windowpane. Their presence is a subtle irony in a star that seems so constant. Yet it reveals its inner churn through these fleeting shadows. And consider the granulation. Those rice grain-sized cells of rising hot gas on the photosphere bubble like a vast, slow-boiling pot, over which the universe simmers. Each granule is a momentary upwelling that carries energy from below. It paints the sun's face in a textured mosaic of warmth and motion. Much like the gentle rise and fall of your own chest as you settle into rest, these cells breathe life into the star's calm facade. The sun's equator spins faster than its poles. A differential rotation completes a turn in 25 days at the middle. The poles languish in 35. This stretches its magnetic fields into twisted helices over time. A cosmic yoga that builds tension until it snaps free and flares. Not with violence, but with a release as soft as a sigh held too long. This spin, born from the star's fluid nature, creates bands of latitude where winds race at up to 700 kilometers per hour. They carve rivers of plasma that flow in opposite directions north and south. An equatorial river and polar countercurrent. These whisper of hidden currents deep within. In this layered dance, the chromosphere glows with spicules. Slender spikes of gas shoot upward like fleeting fountains. Each one is a brief eruption that arches and falls. It adds filigree to the solar portrait. Picture them as the brief spark of fireflies on a midsummer night, rising and fading without fanfare, yet enchanting in their transience. Imagine the sun's neutrino output. Those ghostly particles born in the core's fusion-forged stream through space at light speed. They pass harmlessly through matter. Trillions pierce your body each second without a touch. Carriers of stellar secrets, they travel undisturbed for 8 minutes to reach us. An invisible rain that connects the heart of the star to your quiet breath. Detectors buried deep in Earth's crust capture these elusive messengers. They reveal the sun's inner workings with precision that humbles our instruments. Each detection is a pinpoint of light in the dark. It affirms the star's steady labor beneath its serene facade. And in the hush of solar minimums, when spots dwindle and the corona smooths, the system basks in a calmer radiance. Fewer disruptions ripple outward. This allows satellites and grids a brief respite. As if the sun itself pauses to listen to the silence it illuminates. The sun's mass, 1.99 times 10 to the 30th kilograms, exerts a gravity so profound it flattens itself ever so slightly at the poles. A subtle abruptness measurable only by our keenest probes. A whisper of imperfection in its near-spherical grace that speaks to the balance of forces holding it whole. This gravity, gentle yet unyielding, shepherds the planets in their ellipses. Each orbit is a testament to Newtonian whispers refined by relativity's curve. Time dilates faintly near the sun's edge. Clocks tick slower by nanoseconds, in a profound reminder that even duration bends to stellar will. Just as a parent's hand guides a child's first steps with unhurried care, so does this pull nurture the family's wandering paths, inviting us to trust in the steady rhythm of the whole. As we trace the sun's limb, that glowing edge where light scatters into the corona's haze, faculae brighten the scene like hidden lanterns. Magnetic bright spots herald active regions. Their increased intensity is a counterpoint to spots' shade, balancing the photosphere's ledger in a symphony of contrasts. These faculae, visible in high-resolution glances from space, flicker with the stars' moods. Their collective glow contributes to total solar irradiance variations of just 0.1%, enough to nudge Earth's seasons subtly, a delicate influence that weaves solar cycles into the fabric of our days. In this interplay, the sun's temperature profile reveals layers of transition. The photosphere at 5,500 degrees, cooling to 4,000 at sunspot umbra, then leaping to 10,000 in prominences. Each stratum is a chapter in the star's thermal poetry, inviting us to ponder the gradients that birth auroral symphonies far from home. The sun's helioseismology, the study of its surface vibrations like a stellar seismograph, maps internal waves rippling through plasma. P modes and G modes echo like distant thunder in a vast hall. They reveal a core of pure fusion, radiative zones of slow diffusion, and convective outer realms where energy bubbles upward in granules. These oscillations, detected as Doppler shifts in spectral lines, pulse with periods from minutes to hours. A resonant hum that underscores the sun's living architecture. Much like the subtle rhythms of waves lapping a lakeshore at dusk, these vibrations invite a deeper listening to the star's inner song. And consider the sun's escape velocity, 618 kilometers per second at its surface, a threshold where gravity yields to speed, allowing solar wind to flee into the void. Yet for us bound below, it anchors our world in elliptical devotion. The orbital resonance of planets is a choral response to its mass. This velocity, born of the star's density Euro averaged at 1.4 grams per cubic centimeter, lighter than water yet compressed to nuclear extremes at Centera Euro, defines the boundary where atmospheres dissipate, explaining Mercury's bare rock while Venus clings to its shroud. In this gravitational poetry, the sun's tidal forces, though faint at distance, subtly elongate the sun itself along the ecliptic, a diurnal flex that aligns with planetary pools, a mutual shaping where the center yields ever so slightly to its family. As you let this thought settle, envision the quiet pool that holds the morning dew on a spider's web Euro unseen, yet essential to the morning's grace. The sun's spectral signature, a G2V main sequence type, paints its light with absorption lines from iron and calcium, a barcode of elements forged in earlier stars and recycled in this one. Each dip and peak is a story of nucleosynthesis, tracing cosmic evolution back to the Big Bang's echo. This spectrum, peaking in yellow-green at 550 nanometers, bathes Earth in colors that stir our souls. From dawn's rose to sunset's amber, a chromatic gift that artists and dreamers alike have chased across canvases and skies. Feel the serenity in knowing this light, filtered through our atmosphere, carries not just energy but the subtle imprint of solar rotation. Red shifted at limbs and blue at center, a Doppler lullaby sung across the void. As the sun's magnetic carpet weaves arches and loops in prominences, a Euro-cooler plasma suspended in hot corona, lasting days in twisted grace before collapsing in cascades. A Euro, these solar roses bloom and wither. Their falls sometimes spark radio bursts that hum through space like distant melodies. These structures, observed in H-alpha glow, trace field lines where particles spiral in helical paths. A magnetic ballet that shields or storms as needed, reminding us of the star's innate balance, where chaos births order in endless renewal. In quieter moments, the sun's quiet sun network of tiny magnetic flux tubes peppers the photosphere like a field of wildflowers. Each one is a fleeting polarity island, contributing to the global field. Their collective whisper sustains the dipole that reverses with inexorable calm, like the faint pattern of veins in a leaf, holding the green life steady against the wind. The sun's angular diameter, half a degree from Earth, spans 32 arc minutes, a visual constancy that frames eclipses in perfect symmetry. The moon's disk aligning just so in a coincidence of scales that feels almost destined. A cosmic poetry where shadow and light entwine. This apparent size, unchanging over human history, offers a fixed point in our turning world. A reference for calendars and compasses, grounding wanderers under shifting skies. And in the sun's photospheric convection, where granules rise and sink in 5-minute cycles, carrying heat like buoyant lanterns through stratified layers, each cell is a hexagonal tile in a mosaic of motion. We glimpse the engine of luminosity, a distributed forge where energy migrates outward in ripples of plasma, sustaining the glow that touches every leaf and wave. As these patterns unfold, let the image linger in your mind, much like the way sunlight filters through morning mist, softening the edges of the day ahead. Finally, as we bask in the sun's total irradiancy, a Euro 1366 watts per square meter at Earth's orbit, the solar constant that powers our blue marbly Euro, the subtle 11-year variations of 0.1% weave into climate tapestries. A faint modulation that echoes in tree rings and ice cores, linking stellar whim to terrestrial tale. This energy, 99% absorbed or reflected by our atmosphere, fuels winds and rains in a cascade of conversions. A stellar endowment that ripples through ecosystems like a pebble in a pond. Each photon is a thread in the web of life. In this generous outpouring, the sun reveals its role not as a distant tyrant but as a nurturing elder. Its light is a bridge across the gulf, inviting us to dream of the worlds it shepherds beyond our gaze. And in this moment of shared light, remember how it warms the soil where we plant our gardens, a quiet gift that roots us all in the same gentle cycle. As the sun's radiant stories settle like stardust on the edges of your thoughts, let us allow our attention to drift gently inward, toward the rocky sentinels that circle closest to this luminous heart, worlds of stone and silence where the star's influence burns most intimate, whispering of extremes and hidden resiliences in the quiet dawn of our solar family's tale. These inner companions, forged in the nebula's first embers alongside their stellar sibling, trace swift ellipses in the sun's unyielding gaze, their surfaces etched with the patient scars of cosmic time, inviting us to ponder the delicate balance between fire and frost that defines their eternal vigil. Here, in the hush of proximity, Mercury and Venus emerge not as harsh outposts but as serene testaments to the universe's subtle artistry, their orbits a rhythmic prelude to the symphony of worlds beyond, each revolution a soft echo of the gravitational poetry that binds us all. As you let this inward pull guide your mind, envision the faint warmth of a hearth fire on a crisp evening, a euro close enough to comfort, yet holding stories of endurance in its steady flame. Mercury, the swift messenger of the gods reimagined in stone, huddles nearest to the sun at an average of 58 million kilometers, completing its elliptical journey in a mere 88 Earth days, a fleeting waltz that spans just 0.39 astronomical units, as if the planet itself yearns for the star's constant companionship. This proximity gifts it the title of our system's innermost world, a diminutive sphere just 4,880 kilometers across, small enough to slip into the space between Earth's equator and the Moon's orbit, yet dense with iron at its core, 5.4 times that of water, a heavy heart that pulls it into a near-perfect roundness despite its battered exterior. Imagine standing on its equator, where the sun looms twice as large as from our home, its disk swelling to fill the sky in a golden hush, casting shadows that stretch long and languid across plains of regolith, fine dust that clings like whispered secrets to every bootfall in our dreams of exploration. Much like the way sand sticks to your skin after a beach walk, warmed by the afternoon sun, this regolith holds the memory of countless micrometeorite kisses, a soft archive of the cosmos's gentle touch. And in this intimate orbit, Mercury's surface unfolds as a canvas of ancient calm, pocked with craters from eons past, basins like the vast Calorissa euro 1,500 kilometers wider euro born from an impact so profound it rippled waves through the planet's molten youth, freezing into concentric rings that now cradle frozen lava flows, a frozen symphony of violence turned to repose. These scars, numbering in the hundreds of thousands, mirror the moon's quiet patina yet glow with a subtle iridescence under the unfiltered solar glare, their rims softened by micrometeorite gardening that sifts and smooths the regolith over billions of years, turning sharp edges into gentle undulations like dunes shaped by an unseen wind. Feel the reassurance in this slow erosion, how even the fiercest blows of the cosmos yield to time's tender hand, leaving behind a landscape of subtle beauty where scarps rise a kilometer high, cliffs thrust upward as the planet cooled and contracted, a 3-mile shrinkage that folded its skin like parchment in a forgotten drawer. Just as an old book Euro TMS pages yellow and curl with years of reading, so do these folds tell tales of Mercury's quiet contraction, inviting us to turn them with care. Mercury's days and nights stretch in extremes that evoke the quiet poetry of solitude. A single solar day lasting 176 Earth days Euro 2 full orbits Euro as the planet's 3 to 2 spin orbit resonance locks it in a resonant embrace with the Sun, rising and setting with deliberate grace, the star halting at the horizon before tracing a figure 8 loop across the sky, a celestial arabesque that defies our earthly intuitions. During its protracted dawn, temperatures climb to 430 degrees Celsius, hot enough to melt zinc in a sigh, while twilight plunges to -173, a frost that ices volatiles in shadowed craters at the poles, pockets of eternal shade where water ice gleams like hidden pearls, undisturbed for billions of years, a serene reservoir whispering of potential oases in the system's scorched frontier. This thermal ballet, the widest swing in our solar neighborhood, arises from the absence of a substantial atmosphere, just a whisper-thin exosphere of sodium and helium atoms that drift lazily, scattered by solar wind like autumn leaves in a breeze, offering scant insulation yet enough to birth faint auroras when magnetic storms stir, pale glows dancing in the tenuous veil. Think of it as the fleeting glow of embers in a dying campfire, brief and beautiful against the encroaching night. Consider the Caloris Basin's antipodal ridges, those peculiar hills opposite the Great Impact site, buckled by seismic waves that traveled through Mercury's nascent crust, converging on the far side in a crumple of stone that now stands as muted waves, a subtle irony in a world so small that violence echoes across its entirety, leaving no corner untouched yet transforming fury into form. These features, mapped by orbiting eyes like messenger, reveal a history of volcanism long quelled, smooth plains of basalt poured from fissures in the planet's youth, now etched with ghost craters half erased by later flows, a layered archive where each stratum speaks of cooling epochs and quiet consolidations. In this geological hush, lobate scarps snake for hundreds of kilometers, thrust faults where contraction wrinkled the surface like cooling wax, their shadows pooling in the low sun as elegant invitations to trace the planet's slow contraction, a gentle yielding to gravity's persistent nudge. As we follow these wrinkles together, let the lines remind you of the faint creases in your palm, maps of a life unfolding with patient grace. Mercury's magnetic field, a relic dynamo from its fluid core frozen in time, wraps the world in a dipole 1% the strength of Earth's, yet sufficient to sculpt the solar wind into a teardrop bow shock, a protective comet tail of plasma that trails sunward, deflecting charged particles in a serene standoff against the stellar gale. This field, tilted just slightly from the rotational axis, generates mini auroras in the exosphere, sodium atoms excited to green luminescence, faint veils that flicker like distant fireflies against the black, a subtle reminder that even in bareness, there lingers a spark of defiance. And the planet's density, highest among terrestrial kin at 5.4 grams per cubic centimeter, hints at a mantle of silicates veined with sulfides, an iron-rich enigma that puzzles astronomers, perhaps the remnant of a stripped outer layer vaporized in the system's violent dawn, leaving behind a core that comprises 60% of its radius, a heavy secret pulsing faintly beneath the regolith's calm. Much like the weight of a well-loved stone in your pocket, smoothed by years of carry, Mercury's core anchors its swift world in enduring poise. As Mercury's swift silhouette fades into the solar haze, our gaze lifts ever so slightly to its neighbor, Venus, the veiled sister that mirrors Earth's form yet cloaks herself in mysteries of heat and haze, orbiting at 108 million kilometers from the Sun in a 225-day circuit, a graceful arc that renders it the third brightest object in our night sky after the Moon and the evening star itself. This world, 1,204 kilometers smaller than home yet nearly identical in mass at 0.815 Earths, spins with a lethargic elegance, its retrograde rotation completing